of freedom of railway vehicles such as longitudinal, lateral, vertical, rolling, pitching, and yaw make its analysis more and more complex as the speed of the vehicle increases. Moreover, the coupling of these motions pose further complexity to design the systems. As a result, the safety and control becomes extremely difficult. There is a need to design and simulate to evaluate the behavior of these high-speed vehicles to have better control and safety of this system on which a majority of our transport depends. Numerous industrial and engineering applications require high heat transfer rates like cooling of hot metal specimens, cooling of electronic devices such as processors, cooling of gas turbine blades and combustors, dyeing of paper, food and textile products, heat transfer by jet impingement by controlling the parameters like jet Reynolds number, jet outlet to target wall distance, nozzle geometry, turbulence intensity of the jet, and surface enlargement elements of the target wall can achieve the required high heat transfer rate. Recent advancements in nanotechnology has made it the new frontier of mechanical engineering. Nanotechnology is helping to considerably improve, even revolutionize many technologies and industry sectors, information technology, homeland security, medicine, transportation, energy, food safety, and environmental safety. The application of nanotechnology is numerous. A few among them are development of new materials. It is possible to tailor the structures of a material at extremely small scale to achieve specific properties, thus greatly extending the material science toolkit. Using nanotechnology, materials can effectively be made stronger, lighter, more durable, more reactive, more civil-like, or better electrical conductors, among many other factors. For example, the outer surface of teeth is enamel, which is composed of prismatic hydroxyapatite crystallate, whereas the inner part of the teeth is of dentin, which is composed of collagen fibrils and hydroxyapatite. Enamel is hard, brittle, and wear resistant, which is required as far as function of teeth is concerned, while dentin is softer and flexible. A functionally graded material with constituent phases as enamel and dentin, the volume fractions being varied continuously from form the junction region. Such a requirement can be met by nanotechnology with minimum cost. Nanotechnology has got numerous applications in electronics and IT industry also. For example, during the year 2000, a typical transistor was 130 to 250 nanometer in size, but in 2014, Intel created a 14 nanometer transistor. Then IBM created 7 nanometer transistor in 2015. Then Lawrence Berkeley National Lab demonstrated a 1 nanometer transistor in 2016. Smaller, faster, and better transistors may mean that soon our computer's entire memory may be stored on a single teeny chip. To add a few, we have now magnetic random access memory computers, which is able to boot the computer almost instantly. MRAM is enabled by nanometer scale magnetic tunnel junctions and can quickly and effectively save data during a system shutdown or enable resume play features. Medical and healthcare applications like nanoscale titanium oxide and zinc oxide have been used for years in sunscreen to provide protection from the sun while appearing invisible on the skin. Renewable energy applications like nanotechnology can be incorporated into solar panels to convert sunlight to electricity more efficiently, promising inexpensive solar power in the future. Nanostructured solar cell could be cheaper to manufacture and easier to install, since they can use print-like manufacturing processes and can be made in flexible rolls rather than discrete panels. Newer research suggests that future solar converters might even be paintable. Nanotechnology is already being used to develop many new kinds of batteries that are quicker charging, more efficient, lighter weight, have a higher power density, and hold electrical charge longer. An epoxy containing carbon nanotubes is being used to make windmill blades that are longer, stronger, and lighter weight than other blades to increase the amount of electricity that windmills can generate. Regarding transportation, nanotechnology has also got numerous applications. Nanotechnology offers the promise of developing multifunctional materials that will contribute to building and maintaining lighter, safer, smarter, and more efficient vehicles, aircraft, spacecraft, and ships. In addition, nanotechnology offers various means to improve the transportation infrastructure. And which is the most important, that is application of nanotechnology in environmental safety. So these are a few I will just say to ignite your mind. Engineers have developed a thin film membrane with nanopores for energy efficient desalination. This molybdenum disulfide membrane filtered 2 or 5 times more than current conventional filters. Many airplane cabin and other types of air filters are nanotechnology based filters that allow mechanical filtration, in which the fiber material creates nanoscale pores that trap particles larger than the size of the pores. The filters also may contain charcoal layers that removes odors. And it has also got applications in our robotics. The recent advancement in robotics has led to its application from industry to medical and marine applications. The application is also seen in service sector with the advancement in sensor technology, artificial intelligence, and machine learning. Biotribology has also played an important role to tackle the diseases related to joints like hip, knee, and skin and oral systems consisting of teeth, chin, palate, tongue, and glands. The research on the joint materials, the synovial fluids, has revealed their properties, and now we are in a position to replace the joints with longer lives and no pain during physical activity. Industry 1.0 are setting up manufacturing plants with the help of hydro and steam power towards end of 18th century. Industry 2.0 as setting up assembly line for mass scale production with the help of electrical energy towards end of 19th century. And after that, Industry 3.0 setting up automation plants for enhanced production with the help of electronics and IT. And finally, now Industry 4.0 with cyber physical systems enabling conditions monitoring, structural health monitoring, remote diagnosis, and remote control to have better control, longer life, and safety of this system. So these are a few igniting words when you will come across the talks of our eminent speakers. I am sure it will help you to take away some useful inputs which will help you in your future research assignments. With this, I end my speech. Thank you all. Hope you are safe at home. Thank you. It's over to Kanchan, madam.
Yes, sir. Thank you so much for the valuable input, sir. Now I am requesting our Honorable Principal, Sir, Professor Dr. Ranjan Kumar Soy, sir, to inaugurate the 3 days National Seminar on Future Trends in Mechanical Engineering, NSFTME 2020. Over to you, sir.
Good morning to all. I, on behalf of PMC, welcoming all the esteemed speakers of the national seminar on
Sorry
future.
to interrupt, sir. It is not audible.
Hello, hello, hello. Am I
Yes,
audible?
sir.
Am I audible now?
No, sir. Better you remove that.
Which one? Hello, hello.
Yes, sir, you are audible, sir.
Good morning to all. I, on behalf of PNEC, welcoming all the participants, eminent speakers to this national seminar on future trends in mechanical engineering. Parla Maharaja Engineering College is established in the year 2009 by Government of Odisha, and also it is the constituent college of the Patna Technical University. This college offering undergraduate program in 9 disciplines and postgraduate in 5 specializations in 3 departments. This college is located in the city of Barampur, which is an age-old city and is known for its silk all over the world. I congratulate the coordinators, Dr. Kanchan Kumari and Mr. Sandeep Kumar Bhoi. Though they are suffering with fever, they are able to start this seminar in time. Here I want to highlight one thing, that mechanical engineers are those who converts the energy into work. They are the basic purpose. So in the present context, it's a more challenging, where in every field we want the final product from the raw material. It should be economical, it should be environmental friendly, and the material should be biodegradable. If all these things will take into account, it's a challenging thing present in front of us. Taking the advancement in different areas of engineering and science and bringing them into a basket where we can apply the principles to make the things more environmental friendly, using green technology and sustainable. The sustainability is the most important part now, because if we focus on the present condition, the environmental degradation is in a very fast rate. It will be a threat for the sustenance of the mankind on this globe. So we have to think in a such a way that we can make the entire activity as maximum possible carbon neutral, particularly in combustion regions. And if we see the development in the field of solar energy conversion, if we will take the example of photovoltaic, the efficiency has initially from 8% when it is commercially used, then now it is gradually increasing, and as the researchers telling, once graphene is used as the material in the solar photovoltaic cells, the efficiency can go up to 75%. So that's the challenge we, the technocrats and the scientists, have to take and bring as well as possible the technology which will be most environmental friendly and acceptable by all and lead to a sustainable growth in future. Then I once again thanks all the participants, esteemed galaxy of speakers for this 2-day seminar, and the coordinators and the others, those who are involved to make this program a successful one. Thank you all, and wishing the seminar a grand success. Thanks all.
Thank you, sir. Now I am requesting Sandeep sir to address the gathering.
Good morning, all. And thank you, respected Principal Sir. Thank you, respected HOD Sir, Dr. Tilochan Raut Sir. And thank you, Kanchan Madam, for this inauguration session. And thank you all the participants. And so before we start, so I would like to introduce the schedule for the whole 3-day seminar. So in the first day today, we have 4 speakers. So first speaker will be Professor Suryakant Pal sir from IIT Kharagpur, and the second speaker will be Professor AP Harsha sir from IIT BHU, and the third speaker will be Santosh Kumar Sahu sir from IIT Indore, and the fourth speaker for today is Professor Subrat Kumar Panda sir from NIT Raulkela. So in the second day, Professor Panduranga from IIT Bhubaneswar and Professor PC Misra from KIT University Bhubaneswar. In the third day, we have also 2 speakers with us, Professor Arun Kumar Samantray sir and Professor Niranjan Sahu sir from IIT Guwahati. So coming to this, to the first speaker, so let me introduce Professor Paul sir. Professor Pal was born on February 20, 1969. He completed his graduation from Government Engineering College, Jalpaiguri, West Bengal in 1991, MTech from IIT Kanpur 1993, and PhD from IIT Kharagpur in 1999 in Mechanical Engineering. Professor Pal has done 3 years of postdoctoral research from University of Sheffield, UK. His specialization is manufacturing science. He was working with Grasim Industries Limited as well in Engineering and Development Division from 1994 to 1995. He also started teaching at IIT Guwahati from July 2002 to July 2004, and then joined IIT Kharagpur, where he is presently working as a professor in Department of Mechanical Engineering. Professor Pal has published 257 research articles, which include 154 international journal papers, 3 national journal papers, 90 conference papers, and 10 international book chapters. He also has filed 10 patents under his esteemed supervision. 17 doctoral scholars have completed their degree. At present, 16 doctoral scholars are working under his guidance. Professor Pal has also supervised nearly 60 MTech students so far. Professor Pal has built a state-of-art friction stir welding laboratory and metallurgy laboratory at IIT Kharagpur. His research interests include stir welding, Industry 4.0, modeling and simulation of manufacturing processes, and rolling. Professor Pal has been awarded with the prestigious Lord Kumar Bhattacharya Chair Professor in Manufacturing for excellent contribution and fostering the industry, academia collaboration in advanced manufacturing. Professor Pal was appointed as the Vice Chairman of IIT JEE in 2013 and 2014. He has served as the Chairman of Hall Management Center, Chairman of Steel Technology Center, and Executive Advisor to Science and Technology Entrepreneurs Park of IIT Kharagpur. At present, he is Associate Dean of Alumni Affairs and Professor in charge of Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur. Now I request Professor Pal to start his presentations.
Yeah. Can you hear me?
Yes, sir.
Yeah. So good morning to all the students and coordinators, Dr. Kanchan Kumari, Professor Sandeep Bhoi, and I was present when Dr. Trilochan Raut was, the mentioning about various aspects of the manufacturing, future trends in manufacturing, and also I listened to the principal of Parala Maharaja Engineering College. So it was a very nice introduction about the future trends of manufacturing, where we are leading to. And so we have given a very long description about me. So I mean, I'm not that the great person. It's a small person with a little bit of understanding of some manufacturing process. And so what I would request is that if any one of you can present my slide. I think Dr. Kanchan Kumari is coordinating that.
Yes, sir. Sir, I'm doing.
Yeah.
Doing.
So first of all, I thank the coordinators to come up with this sort of the webinars, which is very relevant as far as today's days are concerned, and with lot of having lot of difficulties, you have come up with this the seminar webinar, so which is a wonderful thing. So I'll talk about the industry 4.0. Before that, I would like to mention it's just just 10 o'clock in my mobile. So we have started exactly on time. That's a wonderful thing. And so I'll talk about the industry 4.0, how it's relevant in manufacturing, what is it and how it is relevant in manufacturing. And also I'll introduce our newly developed or set up Center of Excellence in Advancement. Yeah, please next slide, please. As mentioned that this is I am Surjapal. You can note down this email ID if you'd like to interact with me in the future. And this is also the website web link where you can also get all the information about our activities, research activities on friction stir welding, on Industry 4.0 and other areas of manufacturing. I'll be more than happy if you interact and if I could help you in your endeavor, future endeavor, that would be wonderful. So, when you talk about this Industry 4.0, we should have a brief understanding about how the evolution of manufacturing took place. So, if we look back and move, in anti-clockwise direction, if we unwind the situation, the history, we'll see that the evolution of the manufacturing, and also we'll see that how the fourth industrial evolution, which we call as the Industry 1.0, came up. And when it has just started its journey, then it faced a lot of difficulties. So we are passing through a very difficult time at this moment. So our approach should be how to make use of these the concepts in manufacturing to tackle the pandemic, the COVID-19. So in that way, I thought the slides should be arranged, and so this has been prepared by. Yeah, I'll request that those audience, those who are having microphone on, please switch off the microphone and also switch off the video. Yeah, otherwise this will distract me. Yeah, please switch off the microphone, all of you. Sadan Teja, yeah, please. Yeah, so the journey of manufacturing. So can you go back to go to the next slide, please? The journey of manufacturing, started, if you look back, it started during the Stone Age. So at that period of time, the people used to, use the stones as the cutting tool. If you look into this, and it went for a long time. So it has got, even the Stone Age has got the different periods, which we technically call them the Paleolithic age, and the Mesolithic age, and the Neolithic age. You do not need to, worry about that. But you will see that over these ages, the dimension of the tool, which was made out of the stone, has got changed. That means they initially started with some geometry. Gradually, they experienced that the geometry which they have considered is not giving the full purpose, so it has to be changed. So they gradually, from the blunt edge to try to convert it to the surface, and then they thought that holding the stone itself is a difficult thing. So they tried to put handle to the stone so that they can be effectively used. Now I understand that the concept of the rectangle in the cutting tool has got started, from the Stone Age itself, because they experienced that the nose radius has to be as low as possible so that it can be very, very sharp and it can cut the required job very effectively. So they use these stones as one of the cutting tools. Next slide, please. Then came the bronze age. That means now they depend on the metals, not the copper, pure metal. They they use bronze. That means it's an alloy. So they understood that to make a material harder than the copper, we have to mix something. So in copper they have mixed tin, and along with some other the alloying elements, so that they can come up with a harder tool. So again, in that also they tried different geometry. They not only the geometry, they also felt that the tool has to be properly held, and they came up with the concept, the put the handle on the metal, and then came up with a better tool. Next slide, please. Then they thought that the tool which was made out of the bronze material, which is again not able to cut all sorts of materials they want to cut. So they thought of using some other material, which is the iron. And iron is stronger than the bronze. And so the people, and with this invent of the new material, which is the iron, they moved from the farms to develop cities. Initially, they were mainly concentrated on the farming. Now they moved from farming to developing the cities. So the iron replaced bronze. So in that way, they got the better tool material. Now, having that tool material, they thought that how to come up with more energy. So they use the domestic, the animal, the power. Next slide, please. So if you look into this, the slide. So initially they use this animal power because there are some jobs which is very difficult to get, by human, the being. So they engage the animal power, the animals to come up to as a source of the power. But they also realize that the animal cannot be used to, the power cannot be derived from the animals for all the applications. So they also engage the human powers. They gradually coming towards the mechanisms. And the next one, please. Then they invented the steam. So when steam got invented, that's the boom of industrial revolution. And from there, we say that the industrial revolution, that industry 1.0 came up in the picture. That from that day itself, that period itself, we call that the industry 1.0 is started. So next slide, please. So industrial, when we talk about this industrial revolution, the industry 1.0, next slide, please. Industry 1.0 is it talks about the mechanizations. And for these mechanizations, they use the steam power. Around 100 years later, when the electricity got used in the production line, and then it was used as an assembly or the mass production. So life became much, the smoother, much easier when electricity got used in the manufacturing sector. And as a result, because if you look into the steam powered industry 1.0, the factory has to be built close to the source of energy. That is where the steam is getting produced. Steam cannot be transported to a long distance, whereas electricity can be transported. So that's why the industrialization starts getting spreaded across the globe when electricity got used in the manufacturing sector. Then close to 100 years later, around 1969, yeah, next clip, please. The robots came into the picture. Robots, got used in the manufacturing sector, and this was for the automation. So large number of jobs can be produced. We all know what is robots and what is the usage. So the precision people thought that the manual, the skill, the labor, it is good, but to come up with the same type of product with the same accuracy is not possible by the human being. Sometimes it may be possible by one generation of the human being, but that generally that doesn't get percolated to the next generation. So it is very difficult by the manual power or manual skill. So the automation has to be brought in. So in 1969, the year when I was born, at that year only, the robot came into the manufacturing sector. Now today, from 2014 onwards, we call this era, this particular, the time as the industry 4.0. That means the fourth industrial revolution, because of the cyber physical systems. That means because of the networks, internet. Because of the utilizations of the network or the implementation of the network, lots of things we are getting to know out of this manufacturing process, and that is helping not only the manufacturers, also the consumers. And how it is helping, what is it, and where it is getting stored. So the next slide will speak about all these things. So this is the journey, like the industry, we talk about the industrial revolution. Now look at this. This is a very, the interesting thing. iPhone, iPad, Kindle, 4G, Uber, Airbnb, Android, Instagram, and WhatsApp. All these things were not there in 13, 14 years back. Today, we are so much glued to WhatsApp, so much glued to Instagram, so much, the used to accessing the Uber or the Ola service and for booking the cars, and also using the Airbnb for booking the hotels and all. We cannot, these days, the kids, I would say the adults, the older persons, everybody is very much conversant in using the WhatsApp. Every moment we are clicking something and sending it to our near and dear, the friends or the persons, and information is getting percolated so fast. So the life has got changed in 13, 14 years. I mean, these 13, 14 years, very, very quickly. Next slide, please. I'll show you another interesting things. You see, the telephone got invented in 1874, and it started using 1877. It took 75 years to reach 100 million customers. 75 years to reach 100 million customers. And if you look into the x-axis, the wave got invented in 1980. It took 7 years to reach to 100 million customers. Then Facebook got, came into our life in 2003, and it took only 4 years to reach 100 million customers. Instagram got invented in 2010, only 2 years. Next is the most important thing, is the Pokemon Go. Pokemon Go, it took, can you guess how much it took to reach to 100 million customers? So the next click will tell the time. It took only 1 month of time. You please click that one. 1 month of time to reach to 100 million the customers. It means that over the period, the gadgets which are coming up, or the technology which is getting the developed or the invented, we are getting ourselves so much accustomed that it is the usage is increasing highly. That means there is no other way out. We have to adopt these technologies. That means we have to move with the time. So the mandate or the saying is that samay ke saath chalo. So Industry 4.0 is, as you know, in a nutshell, whatever we have mentioned, that the evolution of the manufacturing, starting from the Stone Age to Bronze Age to Iron Age to Machine Age to the modern age, and then the Industry 1.0, 2.0, 3.0, and 4.0. Every moment, our target is to ensure the quality. Target is to, come up with a better, the productivity and all. Yeah, next. So, and obviously, if we increase our productivity, the cost will also be reduced. So, the ensuring quality, precision, and increase of the productivity, it was there in the minds of the people who were present or who brought up the manufacturing and then helped in the evolution of the manufacturing in the starting age, like the Stone Age, Bronze Age, and then Iron Age, and even to some extent in the the Machine Age. But when Industry 4.0, this revolution, the industrial revolution came into picture, since it is a network-based Industry 4.0, lot of sensors are getting used. That means you can monitor the process. You can acquire large number of data. You can use the attributes or the modules of the Industry 4.0 for its better prediction. And because of these technologies, you can also come up with the digital versions of the machines or the process, which we call as the digital twin. I'll also explain that one, what is it later on, for predictive maintenance and all, and also for the other things. So if we look into the component of the Industry 4.0, there are actually 9 components, but in this figure we have mentioned the 10 components. So the components are like the cloud computing, big data, simulation, Internet of Things, augmented reality, robotics, additive manufacturing, and cyber security. So all these 9 components can be clubbed together and then form a complete one module, which is called the system integration. Now, what is cloud computing? How the big data is important in today's manufacturing? Why do we need the simulation? What is the importance of the Internet of Things in manufacturing? What is the purpose of this augmented reality for in today's manufacturing perspective? How much robot can help in this Industry 4.0? How to take the additive manufacturing forward in the manufacturing? And while using all these network-based, the modules, how can we secure our data, that is the cyber security? And how all these modules can be implemented together and to come up with an integrated system for the implementation of the Industry 4.0. So Industry 4.0 is not a catchy, the word. It is the agglomeration or the confluence of the techniques or the modules that I have mentioned there. So the major targets in Industry 4.0 applications is that the collection of the data. As I mentioned that large number of sensors are getting engaged in the systems, you can acquire large number of the data for monitoring of the process. And that monitoring can also be done remotely. Based on the data that you are collecting, you can do lots of analytics on that, lot of analysis on that, by using the signal processing techniques, by using the image processing techniques, by implementing the artificial intelligence, and so on and so. So when you get large number of data, if you can analyze that, and then gradually what is happening is that you are, commenting on how the process is running, what is the health of the machine. If you think carefully, the signal processing is there with us for a long time. Today, it is becoming more and more important when we think of when we talk more on the Industry 4.0. But think of a stethoscope. Stethoscope, what the doctor does, doctor places the stethoscope on your heart and then gets the sound, and from that sound, he or she applies the medical concept to get to know that what is the condition of the heart. So there, the processing is getting done in the brain of the doctor. Signal is getting acquired by the stethoscope. So the signal process, so the sensors, which is the stethoscope, and the processing, which is the brain of the doctor. So that itself is called, it was there from the very beginning. It was there for a long time. Similarly, the measuring the blood pressure and all. Similarly, all of you might be, the heard the name of the, the investigation called the Holter monitoring, where the 24 hours you can check the quality of your, performance of the heart, by engaging the two different sensors. So it is there with us for a long time. Today we are in the manufacturing sector. We are trying to implement. Yeah, please, Subhasis Mahapatra or others, please do not never ever switch on the video when someone is speaking. Okay, so because that distracts a lot. One day when you'll come to my stage, you will understand that. So these sort of, what I was telling is that the sensors or the concept was there for a long time. Now we are trying to implement those in case of the manufacturing, so that the process, we can get to know more about the process, more about the health of the machine, and if we know something is going wrong, how can we control that? So the digital version of the machine or the process can be done by using the sensors data, which we call the digital twin. So it can be the data driven, it can be the simulation based. But alarming situation is that, yeah, next slide please. We started with, as I mentioned, the Stone Age, then we moved to the Bronze Age, then to the Iron Age, Machine Age, Modern Age, then Industry 1.0, 2.0, 3.0, 4.0. So all this, till 2014, if you look at it, just stay back to the slide. If you look into this, the journey, evolution of the manufacturing, every step there was a development. That means the manufacturing, the technology got improved grossly, and it gave a lot of benefits to us. When we started using the concept of the Industry 4.0, came up in 2014 in Germany, and then people have lots of debates how much it would be effective, what is the need and all, whether it is needed for all sectors of the manufacturing and all. So lots of debates were going on, lots of discussion are going on, and people were coming to a conclusion that it is very much effective, it is to be needed. At that moment of time, in 2019, 1st of December, the first outbreak of corona took place in Yuan in China. Okay, so in fact, personally, this could be around 9th or the 10th seminar I am talking about the Industry 4.0. See, being a small person, if I present 9th or the 10th webinar or the seminar on the Industry 4.0, that means you can think of that throughout the globe, there are a large number of people, big people are there. So how much discussion is taking place on Industry 4.0, to bring it to the manufacturing in the platform. But at that moment only, just stay back to the next, please go back to the next slide. At that moment only, the 2019, the outbreak took place, and it was declared by the WHO as a pandemic by March. And from later March, the lockdown period started all over the country, all over the globe, in fact, and we are gradually getting accustomed with the new normal situation. I would not term it as the abnormal situation. Let us call this as a new normal situation from the March 25. So we need to very carefully think that how the modules or the attributes which I have mentioned, that how they can be used in our manufacturing sector and also our day-to-day lives to make our lives smoother, to make our manufacturing sector better and better. Next slide, please. So what are the threats this COVID-19 is giving to us? So, when something comes up, we always think about ourselves first. Like, how am I going to get changed, affected because of the COVID-19? First, we think of ourselves, then we think of that in a broader sense. That's the common, human psychology. if I think, the personally that how am I going to get affected, how I'm affected at this moment, I'd say that my life was, the full of, interaction with the students. So I'm missing my doctoral scholars, very much. I am unable to socialize with them. I am unable to, have the evening snacks at my lab with my doctoral scholars. I like biking, so I'm unable to go outside with my bullet. So all these things have, that affected me grossly. So I'm pretty sure that your life has also got changed. But having these situations, how can I think positively and take it forward? Next slide, please. So when having this, concept known to me, if I look into the manufacturing sector or the industrial sector, how the industries are getting affected. There are, the different types of, the changes that took place. There are some short-term effects, the long-term effects. Because of this, the pandemic, we all, irrespective of the generation, irrespective of our financial capacity, we panicked and bought so many things for our day-to-day purpose, which was actually not needed. So people, the purchased a lot. Because of this sudden rise in the demand, the industries could not meet the demand. Why? Because they did not have the manpower. And because of the drop in the demands in other sectors, so pharmaceutical sectors and the personal care sectors, there is a huge demand. But if you look into the other sectors, there is the immense drop in demand. So because of this, the non-sync between the demand and then supply, and which got affected because of the non-availability of the workforce, the entire industries got affected, the largely. Next slide, please. If you look into this long-term effect, now what happens is that now most of the migrant workers, any industry, they, if you want to come up with a precision in the job, and that too, if it is a manual base, then you need to have the skilled workers. Skilled workers, if you manufacture it, the company at the, at your place, that is the Behrampur, and it's very difficult to get the skilled man, if it is not fully automated, then it's very difficult to get all the skilled manpower from the nearby place of Behrampur. You have to depend on the migrant workforce, and migrant workforce come from the different, as it's migrant, that means it comes from the different parts of the country. Now they are having fear. They are having fear because they are getting scared whether they will get the accommodation in the city of the workplace or not, where they used to stay. Even the landlord will be refusing give tenancy to this sort of people, and there is a restriction of the travel as well. There are not lots of trains, flights are also not flying, and all these things. So there is a huge, the shortage of the manpower. Even go back to the next slide, please. Yeah. Even in the workplace itself, we need to maintain the physical distancing. Actually, the social distancing terms is not good in my understanding. So I will say, though I have mentioned social distancing, I'll mention it as, call it as a, physical distancing. Physical distancing need to be enforced, for quite some time in the shop floor. Now, if you would like to engage or enforce the physical distancing in the, the shop floor, then you cannot operate all the machines all the time. Then you have to think for the shifting. Now, when you think for the calling the manpowers in different shifts and all, your production may not be continued in full-fledged. So there would be loss of, the supply or very reduction in the supply. Next slide, please. So the manufacturers at this stage, what they need to think, there are 3 different phases. First thing is that they need to survive. Initially, the all manufacturing sector is grossly, they are already affected. But they need to survive first. So they need to take necessary steps so that they can overcome these challenges. Now, while getting, the survive, when they are getting, the recovered, they need to think that how fast, what should be the proactive, the active proactive steps so that they can recover very quickly. Once the second phase is over, they've recovered, they need to think that how they can change that manufacturing scenario so that they can become more resilient and agile. More resilient and agile means that they can produce different types of the jobs having the same infrastructure. And or they can revamp up, that with a little change of the infrastructures, they can bring different types of the job along with their main production. Having the main production line intact, they can produce something, the extra, which can meet the societal need for a greater cause. Now, while doing this analysis, the survival, recovery, and then in the future business, the fundamental questions come up in the minds that what were the weaknesses? Why did we fail? What are the costly decisions we have made and why? If I have taken some decisions, which is a very hard decisions, why did I take that hard decisions? Will that be, had it been possible if I could have think it a different way? What should be our different steps, so that, we should not face this sort of, the difficult stages in the manufacturing, even though some other pandemic comes up in future. Now, one important, you have to very, very positive in mind. Now, one important quote, given by the Thomas Alva Edison, that whenever he failed, he used to think that I have not failed. I have just found 10,000 ways that won't work. If you know, when you are inventing something, this I would like to tell to all the students, some of you might be interested in the startup, or let's say that in future research and all, or developing some products or something like this. All the time, you try, keep on trying. When you try something and fail, you try to understand that why did you fail. Always believe yourselves and go ahead. That believe yourselves, for your sincerity and dedication. If you are very much sincere, if you know that you are sincere and you are putting, you are strong, you are fully dedicated to it, just go ahead even if you have failed. When you fail, you try to analyze that one, why did you fail? In that way, if you fail many times, then what will happen is that you get to know that there are some ways, or there is a way, if you take that path and you are going to reach the success. So this quote is very, very useful, and lot of the great people have they told that. So that means you have to be very, very positive. No matter when you are failing, and no matter what your near or dear one tells you about your the endeavor, you just go ahead. Next slide, please. So, but grossly, the things which I have mentioned is true to all the industrial sectors. But if we look into the overall manufacturing, the sector, Indian manufacturing sector is grossly dependent on the MSMEs. That means it's the medium, small, and micro enterprises. They are the backbone of the industrial sector. They supply the manpower. They supply the product to the larger the industry. If you take about very the big industries like any automobile industry, they don't manufacture anything. They just get the supply and assembly. You take any automobile sector. So very small portions, very small job is getting done, but most of the jobs are outsourced. So they just check the quality, that whether it is up to the mark, and if it is up to the mark, they just take those products and assemble it and then put the stamp of that company and then sell it in the market. So the manufacturing sector, these MSME sectors are to be energized a lot, and that the energy activation can be given largely by the usage of these, the modules or the attributes of the Industry 4.0. Next slide. Next, just click that one. Click, please. So the manufacturing, these MSME sectors, they have the less migrant or the skilled workforce. There is a low adaptability of the new technology due to the shortage of the funds and lack of guidance in research and innovation, which is very, very true. They have the skilled manpower, but very less in number. So they need to be educated so that they can make use of this, the attributes. But there is a caution that these attributes which I have mentioned of the Industry 4.0, they are costly. So the small industrial sectors, they cannot, adopt these technologies because of the less of the fund. So our approach with the researchers or the academician, our approach should be how to leverage those modules or the attributes and come up with a very low cost solution so that it can reach to the MSME sectors, or it can be adopted by the MSME sectors very quickly. Next slide, please. So these lessons is that, next slide, yeah. So as we have mentioned that it is not an abnormal situation, it is a new normal situation. We need to understand that how we can work from the remote places. Today, mostly our IIT is locked down, for 7 days, and it's very, I think it's all over the country, all IITs, they have started taking the online classes, which is very much necessary these days to avoid the physical, the interaction between the teacher and the students, because everybody is a vulnerable, the scenario. So it is better to have the online classes and online the seminars. We all are getting benefited by the BC mode. Today you see that 76, my computer says that the 76 people are attending this webinar, and we are all sitting at different places and attending this one. Though I could have, if I would have been present at the Parala Maharaja Engineering College, I would have enjoyed a lot. But at the same time, it is my saving for the traveling, and that traveling time I am utilizing for some other purpose. Because I am not traveling, it is also I am helping the globe to reduce the carbon footprint. So the physical distancing is to be maintained as much as possible, because there are some jobs which can be done even in the industry, not only the work of places, that the physical distancing can be maintaining the physical distancing, we can go ahead with our job if we adopt the digital tools. So we have to be very, very proactive and progressive in thinking, in adopting these digital tools. So our world is experiencing the pandemic. So all of us are passing through the critical time. So my message is that, and it is not my message, it is the message from everybody, every corner, that we have to stay at home and stay safe first. Health is the most important thing. I'm pretty sure that if we stay at home but fully engage ourselves in the academics and the research activities which we are concerned to, which we are entitled to, then very soon we'll break the chain of the spread of the COVID or the corona, the disease. Next slide, please. So how Industry 4.0 can help? So you see that as I mentioned, the physical distancing is to be maintained. But if we maintain the physical distancing, having the manpower, the manual process, we cannot meet up the demand. So we have to energize. At the same time, we have to produce. We have to come back to the original, the production rate. That can be automated or done by using these AGVs or the robots or the drones. While using the digital twin means the replica. When you say the digital twin, that means the digital replica. Replica of what? Replica of the physical system. That means if you have got a machine, so if you are acquiring the information from the different parts of the machine, and then you can see that how the machine is working. If I take the human body, if I take the human body, and we do have the different the health components like the heart, kidney, lungs, and the other things. And if we engage sensors, independent sensors for those for different components, then we'll get to monitor what is the condition of the heart, what is the condition of the liver, what is the condition of the lung. So 24 hours you can monitor. Once you can monitor, then you'll get to know what is the level of degradation taking place in the performance of the heart, taking the performance of the lung, and so and so. And from there, you'll be able to predict where it is leading to. So that digital model is nothing but the digital twin of the physical system, which is our human body. Similarly, it can be for our machine. Once you engage different sensors on the different machines and all, and then you'll get to know that what is the utilizations of a particular machine in a particular shop floor. How long the machine is getting utilized? How much is the power consumption? Can I make use of that machine for the different purposes? So the parallel work, and which I have mentioned that we have to be proactive in thinking. The industries need to be proactive in thinking for the agile business, that means the secondary the products. If a robot is getting used for a primary product in a manufacturing process, and if it is not used for a long time, the robots are designed to work continuously. So if a particular robot is not used for continuously or for a long time, it can, for a particular job, primary job, that means it can be used for the secondary job. And in that way, the industry can come up with a secondary product, and it would be more, the resilient and agile. So primary product will go on, but the secondary product is also coming up with the same infrastructure. So this information, this is possible if and only if we engage the tools of the Industry 4.0. And that can be done by using the artificial intelligence or the machine learning or the deep learning or the completely new manufacturing paradigm, which is the additive manufacturing. So next slide, please. So let us visualize the utility of these tools. Next slide, please. If you always, as a human being, the most important thing, it doesn't matter whether you are going for research or whether you are adopting the Industry 4.0 or not. I would say I'm not, I don't think I'm the most aged person in this seminar today. But in my, the understanding, realization, I would say that you have to be positive in every step of your life. If something is happening before you, try to analyze or try to think that how we can, the study and take the best part of it and go ahead with that. So always open your mind and listen to what others are saying. It doesn't matter what is the age of that, the person. Try to listen to that and try to see that how you can learn out of it and take it forward. As a teacher, when I interact with my intern students, what I do is that I listen carefully, and sometimes they are, some of the students are brighter than me, so smarter than me, because of some reasons or the other, maybe because of their intellect, maybe because of the age they are born in the Industry 4.0 era or something like that. So I born in the Industry 3.0 era. So there is a generation gap, and so people are smarter and all. But you have to be very, very positive so that you can learn something out of it. So you see, that's the thing. Ashok Shinde, you do not present, this one. So why use robots? The students, what I'd say is that your approach, I'm teaching in IIT for a long time. It's more than more than 18 years in IIT system. You know, when a teacher is telling something, you know, speaking something, giving a lecture, you should be attentive. If you are not interested, you can leave the classroom, but never ever disturb the teacher. Okay. So now let us go back to the usage, which is the robots. We all know that how robots can be utilized. We know that its power, its efficacy. It is you know, it helps the process. It can come up with the accurate thing. But our approach would be that how fast it can be brought into the manufacturing sector at a low cost. Okay, so the robots can be utilized for automating several jobs in the industry. A usefulness is that help with the unavailability of the workers and help in increasing the productivity. Earlier, we used to take the example of China all the time, and this time, you know, after COVID-19, God knows, you know, why, when you speak something about the China, people are not taking in a good spirit. So, but I would like to technologically, I would like to mention that they have used robots almost in different places, you know, starting in the hospital specifically for delivering everything like food, medicine, and disinfecting the rooms, and even surprising to know that some level of competency for people in quarantine. Next slide, please. As you know, the cloud is that you know, that has come up, so that means it has helped ourselves or the manufacturing sectors to you know, to make use of the large number of the data and monitor the process remotely. So that means if a process or the machine is engaged with large number of sensors, you know, and those sensors data can be collected and sent it to a common platform which is called the cloud. The advantage is that the remote access of this server or the computing system, which is the cloud computing or the cloud server, is possible. So that means at the central place, all the informations are coming up, and with this central database, you can do the analysis, making use of the lots of the tools like AI, artificial intelligence, you know, the machine learning or the deep learning, and then you can come up what is going on and what is the problem with the process of the machine, whether it is going in the right direction, whether if I can make use of the better directions or not. Yeah, next slide, please. So as I mentioned that the use of the AI, ML, and the DL, these are having very high potential at, you know, to make use of to come up with the digital twins and the real time predictive the maintenance schedules and all. Next slide, please. Now I'll talk about very briefly about this additive manufacturing. People are using this, you know, the new manufacturing paradigm, where you can come up with, you know, the very easily you can fabricate the job which is very intricate in nature, very complex in nature. And so if you have got something in your mind and if you have designed something, by using this technology, you can print and you can have a prototype. So having a prototype will give you the feel, what is the problem, what is the performance of that product. When you have come up with this, you know, the new prototype or the prototype of your, you know, the product quickly, so that means you'd be able to come up launch your product in the market very soon. So people are making use of this, the 3D printing, you know, the technology or additive manufacturing technology in preparing the PPE kits and all. Next slide, please. This is a very interesting thing. Even the 3D printing, you know, is getting used for the construction. World's first 3D printed office in Dubai came up in 2016. The building, just listen to me carefully or read this slide, and this will definitely amaze you. The building has been printed in Shanghai, shipped to Dubai and assembled on site. It's a total area of, the floor area is 2,600 square feet. Number of days printing, 17. Number of days to assemble, 2. That means a building took only 17 days to print in a different location, got shipped to some other location, and on site it took only 2 days to assemble to come up with an office like this. So it reduced the construction waste, from 30 to 60%, and reduced the labor 50 to 80%. So you see the potential of this technology. So initially it came up in printing only the polymeric, the plastic-based objects and all. Now it is getting used for the metals. Not only metals, it is getting also used for the construction materials as well. Even if it is a metal, it is used for the different, mixing of the different types of materials and all. Yeah, next slide, please. You see, these are also the building. 3D printed building in China 2015. Total area is 11,840 square feet, printed on site. 3D printed 2-story building in Beijing, China 2016. So 2015 and 16, in this era, in this period, the construction of the building by 3D printing technology, that means just printing layer by layer the construction material to come up with the, as per the CAD design of the model, the CAD design of the building has come up. Now people are talking about the augmented reality or the virtual reality. These are also very much the useful in coming days. Especially this is also not only in the manufacturing sector and also for the educational sector. Virtual reality will give you the feel of the real world in the virtual domain. That means when you adopt this technology, virtual reality, as if you are interacting with the physical system. So that this technology can be useful for giving the training to the people, even seated, the remotely. So it has got application in the manufacturing sector, it has got application in the education sectors and also in the healthcare. At the same time, the advanced version of the virtual reality is the augmented reality. That means you have got this, the physical system. If you are designing something, designing means if you are simulating something and you would like to see that how that simulated portion can get itself adapt or how does it perform with the physical system. I'll give you a very, very simple example like that. If you have got a motor, which is a physical system, and you have designed an impeller, which is a blade. The impeller is in the simulation domain and motor is a physical domain. So if you'd like to see that, since you have designed the impeller, you'd like to see that how my design is performing for giving a proper the airflow for giving the airflow. So you may have come up with the different designs of the impeller and plugged into these physical systems and see that one how these joint endeavor physical systems are with having the same performance of the physical systems, how the total systems give you the performance. That is called the augmented reality. Next slide, please. Now these days people are also use this conversational AI, which is called the chatbots. You might have seen that when you are purchasing something, some of the websites have come up with the chatbots, or foreign universities, if you inquire about the foreign universities, so they are having the chatbots. Just like if you write a questions, based on that questions, the AI is implemented, artificial intelligence is implemented, machine learning algorithm is implemented. From the strategic answers, they will give you the answer correctly. So Siri, Alexa, they are all like based on the concept of the chatbots. So now, if we would like to, the manufacturing of a particular process, when we inquire, when we adopt or acquire the data from the system, and we develop an AI chatbots on these, and then if someone asks that what is the performance of this particular machine yesterday, then immediately chatbot will tell based on that data acquired from the sensor that how is it going to perform. Is there any problem with that machine? The chatbot will tell like that. So these are the usefulness. Even the Indian government, during the break of this the COVID start of the spreading of the COVID-19 thing, Indian government came up with a chatbot called My Corona Help Desk. So if you ask any questions, it will give you the answer. So these are the things can be very much useful, not only in the non-manufacturing sectors, also very much in the manufacturing sector. Next slide, please. So my concern is that the Indian sectors manufacturing sector or the industrial sector can be boosted if we help the MSMEs to adopt this industry 4.0 very, very quickly. So we have to educate them that whatever the machines they are using, like they are using very age-old machines, the legacy machines, how those age-old machines or the old machines can be made modernized by retrofitting, not by changing completely, but changing in a very, very small steps, so that they can also adopt the automation in the baby steps and replace the parts, and make it more the automated and come up with an accurate product. So these are the active ways by which you can help these MSMEs. Keep this thing in your mind, that for the students, those who are aiming to have a startup, your product would be sold in the market if and only if it is a low cost solution and quality product. So every moment, technological solution, there would be n number of solutions, but there would be n number of patents. But your patent, your solution will be taken up if it is a low cost and at the same time if it is a quality. These days, because of this online platform, we are getting to know, we are all the time we are comparing different, the platforms, Amazon, Flipkart, then Snapdeal, this, that, and search for, when you fix up something in your mind that I would like to purchase this product, and then compare that who is going to give the cheaper price. So similarly, your the invention will also be there in the database, in the national database very soon, and then the startups, all the startups innovation should be displayed. And if a customer, if an industry people, if I would like to say that I'd like to adopt this thing, then this particular technology, I would see that whether it's a low cost or not. So this, the manufacturing, these MSME sectors has to be brought into our ecosystem. Ecosystem means that the coexistence of the different the stakeholders, like the academic institutes, research institutes, big industries, and the small industries. We need to work together. We need to build up an ecosystem so that whatever the technology is getting developed, that could be easily adopted by all types of the sectors. If I invent something and that is not takeable by our own MSME sectors, that means we are not helping our country to grow or to reach or to increase its GDP. So, and at the same time, we have to train our the MSME people. We have to educate them. What is CNC? What is the industrial, the robot? How do they perform? What is VR? What is hydraulic system? What is pneumatic systems? How they can be used? How the low cost sensors can be used to monitor the process? All these bits and pieces are to be training need to be given onto that. Yeah, I have just completed 1 hour, and in 15 minutes time, I'll be able to complete the remaining portion. And then 15 minutes I'll be keeping for the question and answer. In that way, I'll complete 1.5 hour time. So the option has now become mandate. Pre-COVID-19 era, as I mentioned, Industry 4.0 people were discussing and thinking that whether it is an option to explore, whether it is possible to be implemented, whether it is possible to be implemented for the industries which are having big pockets, or it is equally possible to be implemented in the MSME sectors. But now this option has become a mandate to deal with the dynamic supply and demand scenario. Every moment customers' need is getting changed. So how can I change my own industrial system to process to make it more resilient, more agile? So it has to have a flexible production line. It has to have some innovative products. Next slide, please. So I like this the topic this quote which has told by Einstein that in the middle of difficulty lies opportunity. So whenever you face any difficulty, you think you have a positive mind and think that there is a possibility, there is an opportunity. You see that both the quotes are same, like the Thomas Alva Edison quote and the Einstein quote. Now, what is our, whatever so far I have told, it is a philosophy. It is a GAN, like IIT professor is giving GAN on Industry 4.0 to do this and do that. Question may come up in your mind, what are you doing, sir? You are giving so much of GAN to us. Are you using this Industry 4.0 at your own place? So few of the slides will answer those questions, if at all it comes in your mind. So we are working in the real-time defect analysis and correction using image processing of a fixed. Can you display the complete slide? Yeah. So what we have done is that the real time. That means whenever the process is happening, what is the quality of the process? You do not need to know what is the process. I will not describe what is the process. Any manufacturing process, but here we have taken a fixed sensor weld process called the fixed sensor welding. I mean, it doesn't matter what sort of process it is. But what we have done is that we have engaged sensors in the process itself, in the different parts of the machines and the job, and we have collected the data on the real time. Real time, we have sent the data to the cloud to analyze that what is the trend of the data, and based on the trend of the data, we analyze that what is sort of defect is coming up. If any defect is coming up, real time we feed the data back to the machine that what are the parameters to be changed to make it defect free. So you see that the first part of the zone is the good weld zone and this last part of the zone is the bad weld zone. So by image processing, that means by capturing the image, this sort of surface defects, we have analyzed in the real time and also control that defect. We have filed a patent also on this. Next slide, please. So then we have, we have done it by using the sensors, which is the force sensor. Previous one was the image processing. Now it's the signal processing. So we have engaged the sensors, initially one sensor, and did the same thing, send the data to the cloud, analyzed it, and processed it. Next slide, please. So you see initially the welding started with the defects, and as progressed, so the data and it was monitored remotely. If you click into this demonstration, you'll get to see video should play. Yeah, video should play. And then you'll see that the students are sitting at BIT Mesra in Ranchi, machine is there at IIT Kharagpur, and the performance is going on at the IIT Kharagpur itself, and everybody can see what is the quality of the process. This is also we have filed a patent on that. Yeah, you can go back to the slide, and then from there you can So this is the welding getting done, and it has just started. So it will take some time in buffering, I believe. So so initially it was having some defect, and the machine changes its parameter. You see that deep welding is getting done. It started. Some defects are coming up. but machine changes its parameter, and finally we see that the defect-free weld has come up. Yeah. So put it in the presentation mode, and the next slide, please. This also we have filed a patent. Then we use that sometimes a single sensor may fail if we use a single sensor, and single sensor may not be able to capture data from all the parts of the machine, or all the the aspects of the product. So we engage the sensors, force, torque, and then power, and click that one completely. And we had seen that the multiple sensors acquiring information from multiple ways is helping the process understanding, process monitoring, and control. Yeah. So here also we have engaged the data sensors and send it to the cloud. And then two types of the real-time monitoring was done. One is the real-time monitoring of the process, and otherwise the real-time monitoring of the health of the machine, which we call is as a digital twin. So some of the sensors data, some of the sensors data we used it for the health of for predicting the health of the machine itself. Yeah. Next slide, please. This also we have filed a patent. You see that very beautiful the picture. Initially there was lots of defect, and the machine change. If you look into the machine parameters omega and then V, it changes continuously to come up with a defect-free the product. You go back to the next slide, please. And you see that if we use the single sensor, of course the time takes less. Multiple sensor time takes more, but that time factor is not very severe. Whereas we are getting, when T stands for the torque sensors, F stands for the force, and the P stands for the power sensor. Different sensors are using, having the different capacity level, but the number of predictions, it too. But when you use all the three sensors together, torque, force, and then power, which has been represented as TFP, and the number of predictions is much less as compared to when a single sensor got used. So that is a immense potential of this thing, and this also we have filed a patent. And this work we have done it with the Tata Consultancy Services. They are our industry partner. Now they are working hard to come up with the actual commercialization. Next slide, please. We have also developed the digital twin. As I mentioned, that we engage sensors for oil quality, oil level, what is the RPM of the machine, what is the velocity, force and power, turbidity of the oil, temperature of the oil, and what is the flow rate. So all these sensors, they got engaged, and then data collected, and then we applied the machine learning algorithms there to come up with the digital versions. And it is also telling us that how it should work and all. There is a small digital twin, audio digital twin developed. I am requesting Dr. Kumari to click that one to give you some idea about how it is working and all. So this is the data-driven model. As I mentioned, that the digital twin can be from both data-driven and then physics-driven or the simulation-driven. So both the data and the simulation-driven can be the used. We are also working on that. If it is not opening, so just go to the next slide, please. Next slide, please. We have also used image processing techniques to the product, the quality. This was some industrial product. So what they were doing is that there were lots of rejection in the product. They're very, turnover is quite high, around 1800 crores. But they were using the manual method to inspect the quality of the product, and that used to get done in a batch wise, like one product, one check out of 100 jobs. So, but there was no the online or the real-time system. We engaged very, very low cost the camera, which is the webcam, by using the webcam. But since the webcam image quality was not good, so we engaged the implemented artificial intelligence to acquire better information even out of the low-cost images. Images are taken out of the low-cost camera, and came up with a the prediction of around close to 98-99%. Next slide, please. You see the image processing, we got the accuracy up to 95%, but when you use image processing along with that artificial intelligence, the accuracy increased 99%. Without changing the infrastructures, that is we use the low-cost camera webcam here itself, only 900 to 1,000 rupees cost. Next slide, please. Now, the Center of Excellence at IIT Kharagpur, which has set up in 2018, it is an ecosystem. This Center of Excellence is set up with the help of the Ministry of Heavy Industries, and we form a consortium of industry members. 6 industry members are there, 4 are the private sectors and 2 are the public sectors. So 4 private sectors are the Tata Group members, Tata Sons, Tata Motors, Tata Consultancy and Tata Steel, and 2 public sectors is the HEC Ranchi and BHEL Delhi. So along with that, we started our journey. It's a very costly project. You can see, you can read out from the numbers itself. And then we are also engaging the startups in this journey. So the startups are also coming up. A lot of inquiries took place, but before the COVID, now because of the COVID, startups are also facing difficulty. But I'm sure that when these pandemic situation gets eased off, erased off, and then the inquiry level will be more, and then participation level will be more. Next slide, please. So the purpose of this, the center, the vision of this center is to inculcate the modern concepts that we have mentioned, modern concepts of this industry 4.0, so that we can add value in terms of the manufacturing process. We can make the manufacturing process more innovative, and for this we need to develop this ecosystem, as I mentioned, big industries, small industries, startups. We need to also discuss and talk about the international expertise, which we are doing with WMG, Waring Manufacturing Group, which is the world's largest manufacturing research center. We are giving training to the industry people on a regular basis. We have given training on the CNC. If you are interested, you can also inquire. Next training would be on the robotics. And while doing that, whatever the innovation we are coming up with, that innovations are also getting secured by filing patents. We have already done with the Tata Consultancy Services. So these are the vision and the mission statements of the Center of Excellence. These are not only the statements, each and everything we are, the following and implementing. Next slide, please. So this Center of Excellence is working mainly on the 4 research areas. One is the research on the materials, research on the automation, research on the additive manufacturing, and research on this Industry 4.0 or Industrial Internet of Things. So the big industries, which is the original equipment manufacturers, they are giving problems to us. So the Center of Excellence faculty colleagues, which spans from computer science, electronics, mechanical, manufacturing, metallurgy, industrial systems engineering, mining engineering, and others, material science as well. So we are working on those industrial problems and giving solutions to the industries. And we are also bringing or requesting the MSMEs to come up so that they get to know what is the technology being adopted by the big industries and how they can be in the supply chain of the big industries to deliver their product. Next slide, please. So we are, in addition with that, we are creating an innovation lab where anybody can come up, startup, MSMEs. This MSME Innovation Lab has got huge infrastructures with some basic facilities, and also the facilities which are very, very high cost and sophisticated. Most of the machines are first time in our country. So I'll give you glimpses of some of the machines and its capacity so that you'll get to know what would be the level of research that we can carry out or execute by using these facilities. Next slide, please. Quickly, yeah. So this is a hybrid additive manufacturing facility. So it can print, different materials. We do have the scanner which will scan any job, give you the coordinate geometries of that product, and you can very easily print it. Once you can print, you can do the mechanical testing. While doing the mechanical testing, you can see how the deformation is taking place. The cost of the additive manufacturing facility is close to 9 crore. Cost of the UTM is close to 2 crore. Then we have got a city, we have placed a purchase order for the CT scan machine, which can scan the job and give you the defects of this one, which is costly around 6 crores. This will be also the first time in our country. Additive manufacturing will be the first time in the second machine in our Asia, first time in our country. And we do have these 5-axis CNC machining center, and first time in our country, which is a robotic vibration testing. That means a robot will be there, which will be scan the object, which will give you the coordinates of the vibrating objects, and get to know which part is getting affected and all. And we do have a next slide, please. We do have a the 6-axis, the KUKA robots for the friction stir welding, costing 2.5 crores. This is also the first time in our country. So very accurately you can do that job. The machine has been installed. So if you can click, you can get a quick glimpse of that. And during this operation, you can also acquire the data, force data, FX, FY, FZ, and also MX, MY, MZ, and that will also help you to the process. So this is our robotic facility. I think because of the bandwidth, yeah. Oh, good. Yeah, you can close it off. Next slide, please. This is a wonderful thing which I have mentioned. I think I request you to play the video. The robot will scan any object. If you give a vibration, that means if a car is there, you can simulate the road condition, the bump, hump, the potholes, and all these things. And then if we can, and then which part is getting affected, how long, what is the endurance limit of that particular component. You can scan it by the robot, for a long duration, and that will give you the idea about how it is happening. We have just, machine has come up, it has not been installed, but the video is from the machine manufacturer. But it's very interesting. You see that one, you'll be amazed to. These are the 3 scanning vibrometer. So the 3 scanning vibrometers can scan the object. You can give a continuous excitation to any job, and then that vibration. You see the robots are moving, so it can go to any part and scan that vibrating object. This is not the video from our lab. This is video from the manufacturer. But they have used 2 robots, but we have purchased 1 robot and 1 track. So that is sufficient for us, which will scan, just do the laser scanning of the vibrating object and give you the mode shape of the vibrating object. Yeah, next slide, please. So you see the infrastructure that we are creating to take the manufacturing research to a new dimension. So this is more, there are different other types of the machines which are also very, this thing. So I would not like to. This is a complete robotic welding solutions, fully sensor integrated, Industry 4.0 compliant. We are going to have MIG welding, spot welding, TIG welding, and also 6 kilowatt laser welding, and the cladding. We have placed the purchase order. Very soon it will come. So here you will get to see that all robots working together, and then you can see that the robot to robot coordination, robots performance, and all these things that could also be done. This is an upcoming facility. We are giving training to the industry people, training on CNC, workshop and industry 4. We are planning with workshop and industry 4.0, AR/VR in manufacturing, short-term courses on the advanced welding techniques. These are all lined up, got held up because of this COVID. Because of giving training in a virtual mode is a difficult job, but we are already started exploring. Very soon we will come up with a virtual training on or training on CNC in virtual mode. We have already given some of the glimpses of our training program. The CNC. We initially did it for the weekend training program, 3 weekends. Then we have done it for the what is that? The training program for the 5-day training program and all. Next slide, please. These are all. You see, the students are taking the thing. Some of the students are the graduates, like the Bojoti Panda, who is also present, was present today as one of the attendees. So he is a student of your college. So he is giving training on the CNC. Next slide, please. This is the workshop on metallography given by the industry person, the well-known, renowned person, George Vander Voort. There is a very big metallographer. So he came all the way to IIT Kharagpur, give for a 1-day workshop on metallography. So even the faculty members of IIT Kharagpur registered also, in addition to the students. Next slide, please. This is the glimpse of the short-term course in our boardroom on Composite 4.0, how Industry 4.0 can be implemented in the composite. You see the industry, large number of industry and outside universities were present in giving lectures. Next slide, please. Our COE dream is something which is different from the other places, other research institutes. We are aiming to convert our experimental or the academic research to the market acceptable product. That means we would like to do the applied research so that it can be very easily taken towards the market. So it is you can say the upscaling the research center or the catapult research center, where the educational institutes research can be implemented in the industrial scale. That's why we have procured our machines of industrial scale in nature. Generally, in most of the cases, IITs or the research institutes, we procure the machines which are lab scale. But the lab scale, when you do something in the lab scale and if you like to do the actual, the job, then you need to upscale it. Now, for upscaling, you need to have that upscaling infrastructure. So that is becoming sometimes becoming very, very, the hindrance or the obstacle. And with the dream, like we'd like to become a catapult center for upscaling the academic educational institute research to a market ready product. We are moving in this direction. Next slide, please. This is our industrial research and innovation lab, 40,000 square feet industrial set. So I'm pretty sure, I'm not boasting, but I'm pretty sure that if you go inside, you'll fall in love with that place. It's a very huge infrastructure, lot of scopes for the interns and then research, the students. But we are all very, very focused. So this is developed and constructed in IIT Kharagpur in a record time, one year, 2 months time. The place didn't have a single tree. This was a dump yard. So I had chosen this space because I didn't need to cut any tree. And so that now the dump yard has been converted to a manufacturing research center. Next slide, please. So the vision of COE would be possible if and only if agar tum saath ho. That means the industry, academia, everybody, if all of us work together, then only we can fulfill the dreams of the COE. We are paving our stones for this to achieve to this, the goal. We are moving. We have created the infrastructure successfully. Now, gradually, we need to work more and more and in a focused way so that we can fulfill this, the dream. Thank you so much. If you have got any questions, you can ask me.
Thank you so much, sir. It was really a nice presentation with the elaborate way of Industry 4.0. So we have 4 questions in our chat box, sir. If you kindly address, then the questions are. First question is asked by Divyajyoti Jena, and his question is: How can robots be used in this COVID-19 period in medical sector?
Yeah, robots can be. That's a very. I do not know whether it's a. This is a question which is my dream. I do not know how you have read my dream. Has anyone told this thing that we are working something on the robotic field? If it is not a got up question, so then I would say that it's a great question. And thing is that these days the doctors are also getting scared to treat the patient. Patients are also getting scared to visit the doctors. It is a very peculiar the situation, and especially for the investigations which are related to the areas like the mouth or the ears or the nose and the throat area. Those inspections can be very easily done by the robots. We are already working on it. Not only working, we have already designed a robot which can go inside the mouth of a patient and then capture the images of the oral hygiene. And we are also developing the image processing, the algorithms to come up with what is the condition of the oral hygiene of a patient. Doctors would be sitting away from the patient. Doctors can see the images taken by the robots. At the same time, the independent of the doctor, the robot itself, by using the image processing, the algorithm, robot itself can also be able to the comment on the condition of the oral hygiene of the patient. This is just one example. There are n number of examples. Even for if you take the USG, if you take the other sorts of investigations and all, very easily those can be done by the robotic the facility. But this is as a first step to go ahead with. We have taken up this project, and the students, interns, and the technical staff, they have completed in this lockdown period when we got stuck up, and then the new normal situation came up. Then we thought that we should do something for the country, and since we are unable to visit to the lab, let us complete the design aspects first. So every Saturday 3:30, all the interns meeting are there. So we used to discuss, and finally we came up with a complete design, the structural design also. What should be the robots, the thing and all, what should the motors would be fixed, mounted on the different joints. So we have designed that one. We have also, I think we have procured the motors as well. We are placing the order for the materials. As soon as the institute gets opened, we will start fabricating at our own place only. So this will be completely in-house developed robots for the medical field, for inspecting the oral hygiene of a patient.
Okay, thank you, sir. Sir, the second question has been asked by Subhasis Mahapatra. How can robots are used in industrial sector?
You see, I have already mentioned that I've given an example. Like robots means for automation, for repetitive jobs, and that too for accurately. If you would have followed the slides carefully and sincerely, you would not have asked this question. Like friction stir welding, I've given an example. I've also given an example of the robot scanning the vibrating, the objects. Now the robots, how can you measure the level of the vibration of an object, for 7 days continuously? How can you do that? Now, if you engage a robot, you can scan that object at different parts, and you can excite that objects to vibrate it at a different vibration level, and that will also, that the robots can help in acquiring the data. Robots are used for the automation. That is the simple repetitive jobs can be done very easily by the robots itself. If you would like to pick up some job from a conveyor belt, jobs are coming up on a continuous basis. The picks and place can be done very easily by the robot. If you would like to inspect the weld quality when the welding is getting done, how to inspect the weld quality in the real time. So that can also be done. I have given an example that was non-robotic, but that could be done very easily by the robot itself. Yes.
Okay, sir. The third question is asked by Amit Raj. How the industrial revolution from Stone Age to Industry 4.0 affected the environment and employment specifically in India?
I've already told that the MSME sector is, that has got grossly affected. Industries, that the already shut down. Okay, there are some jobs, some products, as I mentioned. These are people are purchasing products. Having that the basically getting panicked. They are purchasing the product more and more in number, which they do not need actually. So there are some objects which are getting procured by the consumers, but the industry is not able to supply that. Why? Because the industries do not have the sufficient manpower. They were sufficient manpower, and at the same time they do not have the automation. Now, since the people, those who used to work there, they have come back to their own place. You have seen that there are special trains which were, they just, ran because of bringing the workers from the workplace to their native place. So now the workplace is empty of the manpower, skilled manpower. The workplace is also empty of not having the full automation. So the automation has to be brought in the manufacturing sector quickly. So in that way, presently it is getting grossly affected. The MSME sector, they are also not having the skilled manpower. So they need to be educated. They are having the less manpower. So because of this COVID, so unless the COVID goes off, or unless they adopt the digital tools, or they adopt the Industry 4.0, so they will also suffer a lot. They are suffering. A lot of industries got shut down, and industries got shut down means that the jobs are also getting affected. I do have the data that large number of people, the parents of the students and all, they have lost their jobs. Even the salaries got cut down. So it is, not only the industry, everybody is getting, affected. If I take my own example, my own family example, my wife is a doctor. Now she has shut down her, the chamber outside. So because of to take the, the safety measures. So if you think in terms of, her employment, her own, the self-employment, income and all these things, that has come down drastically. But this is life. We have to be positive. We have to go ahead with, and we have to be resilient and agile. The time and again, I'm using the same term, that we need to think of that, how we can take this forward. Now, industry, if they are procuring only one job, they need to think that with the existing infrastructure, with the use of the automation, how they can come up with the different types of the products. At least if one product gets affected, the other should be there in the market. Okay, so these are the things.
Okay, sir, due to time constraint, we'll only take one more question, and the last question. And it is asked by Vijay Pal. Which software is used to manage big 3D design for 3D printing? Because making a building with it will need a lot of small thing, and managing them will not be easy for us.
Yes. 3D printing software which Dubai or the China people have used, that I do not have any answer. I have given an example to show the potential of this technology in the construction sector as well. Now, which software China has used, and Dubai has asked China to use that software, frankly speaking, I do not have any answer on that.
Okay. Thank you so much, sir. Due to time constraint, we are not taking any more questions, because here the participants are very eager to ask so many questions, and due to time.
So 1 hour 30 minutes constantly I'm the talking and so I think we should give a stop here now.
Okay, thank you so much,
sir. Our next eminent speaker is also there, Professor A.P. Harsha sir from IIT BHU. Sir, good morning, sir.
So thank you so much, sir. It was really a nice presentation, and I hope all of us have learned so many things, and it will really beneficial
There is
for
an immense,
all of us.
immense scope. There is an immense scope, definitely. So now the people need to take. But one thing is that any solution, we can talk big, but that will not serve the purpose. That will not serve the purpose or serve our country until and unless it's a low-cost solution and accurate solution. That's the thing. And then our research should be only for developing or coming up with the technologies which are low.
Thank you, sir. Thank you, sir. So our next speaker will be Professor A.P. Harsa from IIT BHU. Let me introduce him to the audience. Professor Harsa received his Bachelor of Engineering in Mechanical Engineering from University of Mysore, India in the year 1991, and completed his Master of Technology in Industrial Tribology and PhD in Tribology from IIT Delhi in the year 1997 and 2004 respectively. Currently, he is a professor and head in the Department of Mechanical Engineering, IIT BHU, Varanasi, India. He had several years of teaching and research experience in mechanical engineering, with particular research emphasis in materials tribology and biotribology. He has published more than 70 research papers in journals and conferences. He is a recipient of Royal Academy of Engineering Major Research Award by the UK in the year 2008 to 2009 on the project entitled The Development and Validation of Novel Lubricant to be used in the testing of biomaterials employed in total joint replacement. This award allowed him to carry out research work on biotribology at Newcastle University, UK. He had also worked as a guest scientist at the Federal Institute of Material Research and Testing, Berlin, Germany in the year 2011, 2014, and 2018, respectively. He is a life member of Tribology Society of India and Indian Society for Technical Education. He has handled several administrative responsibilities at institute level, such as chairman, Senate Postgraduate Committee, chairman Annual Report Committee, convener Department Postgraduate Committee, member Senate Education Policy Committee, member Senate Election Committee, vice chairman of GATE, member Department of Faculty Committee. Other than this, he has lots of extra responsibility also. So I hope with this introduction, and I would like to invite Professor Harsa sir.
Thank you. Thank you, Boye. Thank you. Thanks for your nice introduction. So I'm going to start my presentation. Can you able to see the slides?
No, sir, not
Hello?
yet. Not yet, sir.
Just a minute. I will do that. I will do that now. Now you can see?
Yes, sir. Yes, sir.
Okay. Thank you. So shall I start?
Sir.
Hello?
Yes, sir. Yes,
okay.
Sir.
So I thank Dr. Boye for giving this opportunity, and also I am thankful to Dr. Kanchana, so who is also an instrumental in establishing the contact and requesting me to deliver the presentation on this occasion. So today I'm going to speak about some fundamental aspects of biotribology. So I do not know much about the audience here, but certainly you might have heard what is this tribology. Tribology deals with friction, wear, and lubrication of the interacting surfaces in relative motion. So it is obvious that when you apply all the aspects of tribology on the bio application, then we can create another class called biotribology. So the subject has got so much of importance these days because of the fact that we have some disease, and these diseases also related to our action. So therefore, the biotribology is one of the important field of engineering, and you will understand how it is important. So though you may not be, might not have heard about this term, but I will introduce to this term, and you will try to understand how it will be effective in our human system. So I think this is a national seminar on future trends in mechanical engineering. So not necessarily in these days mechanical means in one discipline. We also look for other areas of engineering, and also you do not know that you also know that mechanical people are the one who are also contributing in the other fields of engineering. So this is very interesting thing. Just see one by one. So what is this biotribology? So tribology deals with friction, wear, lubrication, and all these terms when it is applied to the human system or the biological system, they come across with the term called biotribology. This word was coined by the famous professor called Professor Dawson in the year 1973. He is from the University of Leeds. So I'm fortunate to meet him once during the conference during my stay in UK. So this topic, the biotribology, when it was introduced, people were not aware that how tribology can be practiced in our biological applications. But certainly, you can make use of the knowledge of the tribology, and you can always design the joints effectively, artificial joints, and so that you can increase the longevity of the patients. So you may be knowing that the tribology begins in the morning when you brush your teeth, when you wear your clothes, when you wear your shoes while doing some walking or maybe running or jumping or anywhere, you will be there to an interaction. These interactions create some sort of a friction and wear, and also sometimes we require a lubricant for our smooth movement. Some of the few typical examples which I listed here, that is wear of dentures, wear of replacement art valves, tribology of contact lenses, wear of screws and plates in bone fracture repair, and of course tribology of natural seminal joints and artificial replacements. So you can understand that what is this natural seminal joints means, like our knee joints, hip joint, or shoulder joints, or elbow joint. In all these joints, you are enjoying a different degree of freedom, but you may not be knowing what the God has designed for us. The God has designed a beautiful lubricant which will lubricate for an entire lifetime. Provided you are, as long as you are healthy, you will be enjoying the different degree of freedom. So the seminal fluid is a very important lubricant the God has designed. So we have to make sure that we are healthy all the time. And in case if you come across with some certain disease, certainly you get a different pain, joint pain, shoulder pain, and hip pain or anything. In those situations, these days you might have seen that the replacement is the only alternative for enjoying your degree of freedom, or maybe you want to extend your life. So the replacement is the only option for us. So when you classify this biotribology, we come across with the skin tribology, oral tribology, tribology of tissues, and medical devices. So I will be speaking more on the joint tribology because we'll be more interested on hip joints, knee joints, and other joints, which is having the some importance with reference to the biotribological aspects. And similarly, the other aspects, skin also it is very important these days because we are always use different cosmetic fluids for uh, to take care of our skin and other thing. And those situation also there will be an interaction. It creates another tribological issues. Like that oral tribology, of course, we have a number of implants, tooth implants and all. Sometimes we use dental restorative material, and these situations we come across with these two terms very commonly, that is joint tribology and oral tribology. Because our body is the one which takes the things from outside, like foreign implants or foreign devices inside for some reason. But body has to accept that because in vivo conditions are different than the outside conditions. So in vivo condition is related to the inside the body condition. The body is being designed in a particular fashion. So obviously, whenever we receive something from outside, we try to reject it because we do not want to have it because we are always more accustomed to the natural things. So anyhow, the joint tribology is more extensively discussed today. So you might have seen that what you can say that implants where the tooth implants are being put, it is drilled and it is drilled in the bone, and of course we will be putting a capping because we want to save your tooth. These days people do not want to lose their tooth, they are always try to save it. So in this situation you can understand that body fluid interact with the metal, so it can become corrosive and it can create the secondary issues. See, another issue is in the knee joint. You can find that it is a seminal cavity, or we can say that it is an articulate cartilage liner. Inside that soinal fluid is there. Soinal fluid is non-Newtonian lubricant, which is designed like which is existing in the body. So obviously, the soinal fluid is going to lubricate the two surfaces, that is two bone in between, and it is being separated by the cartilage liner. Inside the cartilage liner we have the sonar fluid. This sonar fluid is essential for our smooth movement like flexion, extension, and so on. Similarly, you can also find in the shoulder joint the similar kind of arrangement is there, and there also you have the sonar fluid. And similarly, you can also see in the hip joint where you will be finding inside the cartilage liner the sonar fluid is existing. So once the sonar fluid is healthy, you don't have any problem. So you can enjoy all degrees of freedom. You will be keep moving from one place to another place. You will jump everything. There are situations as we have seen in the aging population, and we get age associated diseases. Joints will wear out. Joints wear out means cartilage liner will wear out. So there are situations we find that tribologists can help, particularly in increasing the life expectancy of the joint in a way that you can improve the uh, life of the person or extended life of the person. There are 1.4 million joint replacements are happening all over the world, and successful procedure means you can increase the number of the number will be keep increasing, and of course a majority of articulation these days will be finding metal against the polymer. The reasons will be discussed later. Okay, why this metal against the polymer? So this is the importance of biotribology because we want to see that help the aging population, particularly extending their life by designing the good knee joints and hip joint. Okay. So now, when you look at your body, when you look at your body, you can see that ball and socket, hinge joint, and again ball and socket, and hinge joint again here in the knee. And of course, there is some gliding action is also happening at the fingers, and even in the some elbow cases, hinge and gliding. So these are all being related to the mechanical joints, so that we can easily design the artificial joints. So the one of the important thing is these are all load bearing members, like load carrying bearing, like load carrying in the sense these are all we consider as bearing, and they will take up the load. It will take the load effectively. So the load is carried by this joint, and of course the how much load it is going to be taken, that is also an important issue. Now you look at the types of movement we enjoy. When you look at the movements, for example, hip joint, flexion, extension, abduction, adduction, medial rotation, lateral rotation, circumduction. You can also see in the knee joint, flexion, extension. And similarly, you can find in the shoulder joint, same thing will happen. So whatever the type of movements you are enjoying, all because of the fact that your sonal fluid is effective in lubricating the two surfaces. So therefore, we are enjoying this movement. So earlier I said that what all our load-bearing members take up the load. So if you try to understand the gait cycle for one gait cycle, you will come to know that what is the maximum of force being exerted at one point of time during the movement of our one uh, or maybe few steps or one cycle of completing the one complete cycle. So in those situations, you will be finding that about 3.33 times the body weight, which is going to act on the bearing member. So obviously, if your weight is 70 kg, it is about 3.33 means 2100 Newton is going to be acting over the joint, and this 2100 Newton is not small. It is going to exert a pressure about 2 megapascal. Sorry, about 2 megapascal. So the 2 megapascal is also great stress on the human joints. So there are situations we always get some sort of a disease, maybe over a period of time because of the age factor. Sometimes age is not an issue, but still people get disease. So therefore, if you look at these three slides, normal seminal fluid, it is there in the membrane, and so you will be enjoying very good degree of freedom. But if you look at the osteoarthritis case, where the cartilage liner wears out because it's the age dependent condition, so due to that, there will be rubbing of the bone. Bone ends rub together, and the patient will get a significant pain. If you want to, because we don't realize the pain, because you have to ask the person, maybe your old parents must be staying with you, or maybe your grandfather or grandparents. You try to ask them, like if they are suffering from some sort of osteoarthritis, to ask them what kind of pain you suffer. They will explain it is so much intense that they will restrict their movement because they don't want to make a movement. They know very well that they get a pain. So in those situations, the patient will be resting on the bed for a long time, and he will get another secondary problems. So if you want to overcome from this problem, the only solution is going for a replacement. So there are situations, the rheumatoid arthritis is also very much common. There are, why it is saying that sometimes patient will come across with the joint pains for some reason because of his what you can say, that lifestyle practices, whatever he is adopting because of the overweight or anything. Sometimes you will be finding that the cartilage liner is being swollen, and you will be seeing that some sort of a bone like swelling, and particularly at the joints. So this is a situation. It is an age independent condition where, irrespective of the age, the people come across with the rheumatoid arthritis. So these days, the younger patients are very much common because rheumatoid arthritis is very common, and swollen sonal membrane, and it is going to create a some sort of a bone erosion or anything, and again the solution is going for a replacement. So I explained to you about the need of joint replacement, about osteoarthritis and rheumatoid arthritis. You can have a look later on. Now, the total hip and knee implant replacement. See now, the solution for us to satisfy the patient is going for a replacement. The replacement can be uh, artificial hip joint. So artificial hip joint is, we have the stem and the neck and femoral head, and we have a polyethylene liner. I will tell you why this liner is being used. There is acetabular shell. So the stem goes inside the femur bone because we have our hip joint is having the femur bone. So the stem goes inside, And we have the neck and femoral head. It is going to be fixed here, and of course, established shell goes inside the pelvis. So the femoral head and the established shell is being separated by means of polyethylene liner. We can always go for metal to metal contact, but there are some issues related to that. I will dwell in the next slide. See, the other joint is knee joint. We can find the femoral component. We have the tibial component. In between that, we have the polyethylene inserts. So again, these two bones are being separated out. So femoral, tibial component, and femoral component is always the polyethylene insert. See now, when you look at the normal joint and artificial joint, how it is different. When you look at the normal joint, it is a conformal type of contact where you can find that the ball is being covered with the cartilage liner, and you have the thigh bone, and of course the socket lined with the cartilage liner is being supported by means of pelvic bone. But when you look at the artificial joint, it will be entirely different. It is not conformal contact. It is a non-conformal contact because ball on a hemispherical cup, and it is going to create a non-conformal contact situation. So the contact situations are different. Therefore, you can understand that artificial joints are not same as of normal joint. They are different. So they are different means their behavior is also going to be different when you put inside the body. When you look at the total hip replacement, what is happening when you try to put it inside the bone, the femoral femur, we call it as femur bone, and we try to put a stem inside, and we have the cup another side, it is going to be reached by pelvic bone. What is happening here? The femur uh, uh, stem has gone inside the femur bone or a thigh bone, and the modulus value of the bone is different than the modulus value of the stem. The stem modulus value is maybe cobalt chromium or maybe titanium or some other material. So the modulus values are significantly different from the bone. So this is going to cause a problem because the load will be always transferred on the higher modulus value of the material. So in those situations, your bone will become weak at one point of time due to stress shielding effect, and it will become brittle, and catastrophically it will fail. And this catastrophic failure causes the secondary problem to the patient. So you can understand that how to bring the modulus value of the bone to such a lower level to at par with the metal. It is also another challenge before you. So therefore, one of the challenges bringing the modulus value of the bone, after bringing the modulus value of the stem at par with the modulus value of the bone. This is one of the important issue here. As I said earlier, artificial joints are not the normal joints because just for our human being satisfaction, we are going to do that activity. Okay. So this is regarding the hip replacement. We have the other type of, as I said earlier in the previous slide, the stress shielding effect is one of the important issue here. So obviously, we have to save the bone, because if at all if the bone become weak, then obviously the patient will be permanently rest on the bed. So he cannot make his movement very easily. So in order to save the bone, there is a Birmingham hip resurfacing has come, where you can see that the change in the design. Simply, it will be fixed like a pin, and cup will go to the pelvis. You can see that typically it is arranged inside the body like this. So this will create a easy movement for the patient. But this all depends upon the skill of the surgeon. If the surgeon skill is not good, then again it may fail also. but these are all expensive. This is a very young design. I can say that is a very young design in the artificial joint. It is going to the pelvis, and this is go to the femur bone. So this is a new design in the artificial joint. Now we have the different type of hip prosthesis. We have metal on metal, metal on polymer, metal on metal hip resurfacing, and ceramic on ceramic. Just a minute. We have the different processes because we have to change the design. When I start using, when people start using metal on metal, they come across with the problems like metal to metal interaction. As per the tribology also, it causes the rubbing. So therefore, the metallic ions will be get liberated. Metallic ions, metallic particles, and these particles will go into the bloodstream, and also it will go and deposit in the kidney and the liver and etc. in the body. So it was causing carcinogenic. Recently, there was an article published in the Hindu newspaper about the company called Zimmer or some other company which supplied the artificial hip joints, and the surgeons in India, without educating the patients, they have replaced it. After some time, about 2,500 patients came with the secondary problem of this kind, carcinogenic effect. Now they are having the, either they are suffering from cancer or maybe they are restricting their movement and so on, because whenever it is being put inside the body, the patient should be introduced or mentioned about the problem involved in the particular type of device. Otherwise, these kind of problems do exist in the situation. Why I'm saying that the metal on metal is interactions is should be prevented. So therefore, the people started putting ultra-molecular weight polyethylene or cross-linked polyethylene as a liner in between the two component, that you can understand what I'm saying. So you might have seen here there is a terminal head and acetabular shell. In between, I'm placing polyethylene liner. Here also polyethylene inserts I'm placing, mainly to separate the metal to metal interaction. And also to an extent, it will use the cushioning effect and so on. So metal and metal resurfacing can also be used, the one which I previously said, and ceramic can also be used. But the drawback with ceramic is it is going to create a squeaking and expensive. Of course, it is highly brittle. At one point of time, it can cause the catastrophic failure. So the choice is left to the patient, the one they want to what they want to have, and also depend upon the activity of the patient. It also depends upon the life expectancy of a person. If he is young, he maybe if it is 50, he may have to live for another 3 decades. So we try to put such a joint which can give the life expectancy for another 30 years. Suppose if the patient is already 70 years, he may not live for more than another 2 decades or maybe 1 decade. So accordingly, the particular joint has to be fixed. So why I'm saying that the type of joint which is to be used depending upon the activity of the patient, and also it depends upon the ability of the person to have it, because this cost is also going to be affected. So therefore, metal on metal is create a lot of metallic particles. It is highly dangerous for carcinogenic effect. So try to overcome from that by having the polymer liner. I am not saying that polymer liner will prevent the wear, but certainly it creates the wear, but it has to an extent that not created the carcinogenic effect. So therefore, of course, the metals are very good in reduction of wear, but the problems is with reference to the secondary effects. So therefore, ultramolecular weight cross-linked polyethylenes have been used. Ultramolecular weight is a polyethylene, is a simple polyethylene have high molecular density, and it is a medical grade material which give us the good wear resistance property. And these days it has been exposed to the radiation dosage, so therefore we get another class of material called crosslink polyethylene. So the wear reduction is in about 50 to 80%. It has already been placed inside the body, and laboratory examinations have proved that it is one of the promising material. So therefore, metal on polymer, crosslink polyethylene is also very much popular in use. Metal on polymer, of course, it is also being used in many situations, particularly ultra-molecular weight poly. Then metal on metal resurfacing, it is all depends upon the skill of the surgeon. So different designs are available. It all depends upon the skill. So we try to see that the surgeon skill is highly dependent. So now you can understand in the different types of joint their advantages and limitations. So now when you form the bearing couples, you can form any combinations can be possible. Stainless steel, cobalt chromium, alumina, zirconia, aluminum composites. So you can make different combinations for the cup and different combination for the head. So ultimately, you can use as a material for the implants. So you can find so much in the literature. So now, in this case, is mechanical properties, which I was dwelling earlier of biomaterial. The bone as a modulus of 10 to 30 gigapascal. This is most important, 10 to 30 gigapascal. When you try to use cobalt chromium material, the modulus value is 230. You can understand how many times it is greater. It is about 6-7 times greater than that of the bone. That is the reason for the stress shedding. That is, the load is always transferred on the higher modulus value of the material. So it causes the brittleness. This brittleness create bone weakness. Okay. So brittleness is leads to failure. So people are working. Is it possible to bring down the modulus value of the material to this level? That is 10 to 30 gigapascal. But it is a great challenge because modulus is the property of the material. So therefore, they try to create a blowholes, microstructures, all micro pit holes or anything, and they try to create similar to the bone and bring the modulus value to the smaller level. So they are working on it, but I don't know how far they are successful at this stage. So this is the important issue in the bone. Okay. Now the other issue is lubrication regime. See, the body is provided with solenoid fluid. The solenoid fluid is a non-Newtonian fluid. Whenever there is a mechanical weeping action, you will be finding that shearing of the lubricant takes place, and ultimately we find that shear stress is not proportional to the shear strain rate, and like water or anything. So therefore, you will be finding the situation of smooth movement and so on. So therefore, the solenoid fluid, what kind of lubrication regime it is forming between the joints, we do not know. People just speculate what type of lubrication regime can be possible. So this is a fundamental equation. It is being defined by the Ambrock for the non-conformal contact. It is a lubrication parameter. The minimum film thickness we can calculate by using this equation. Geometrical factors of the contacting surface, where you will be using the viscosity of the lubricant, entraining velocity, modulus value, again geometrical factor, load factors. And taking into the account of all these things, connecting to the effective surface roughness, lubrication parameter can be defined. Please note that this we are trying to speculate for the different type of joint inside the body. but inside the body, once if you are going for a replacement, the sonar fluid is no more existing in your body, particularly particular joint, because you are removing the cartilage liner and placing the new joint. Obviously, the body fluid will try to take care of your lubrication. That is one of the important. So, the body fluid, obviously, bloodstream or anything which flow around the particular device, which help us. Okay. Now, people have worked. What is the best diameter I can keep? Femoral head diameter. It's a very great confusion because and the clearance is always required. So metal on metal, ceramic on polymer, metal on metal, again metal, ceramic on ceramic, different types of uh, diameters can be possible. So people have worked with reference to the type of contact and their and diameter and metal on metal and mean effective pressure. You can understand that mean pressure will be more less in case of polymer, mean pressure will be more in case of metal by using the Archiani equations. And the clearance also has influence. The clearance with diameter can also influence on the value of A. That is contact width. So contact width also will be changes with the type of material. Either it may be polymer or it may be metal. So contact width in this case will be smaller in the metal. Polymer it is about 8. So this value can be easily calculated by using the what I can say that equations. So then after that, we try to examine what is the film thickness it will get formed. The film thickness also going to change with the clearance. Clearance, you can understand what clearance I'm talking about. Clearance between the ball and the cup. Different clearance, different diameters. And obviously, the minimum film thickness will be affected by with the diameter, the film thickness in nanometer size. And film parameter lambda also will be affected by clearance. And again, with the diameter. So as you can see that either fluid film lubrication, mixed lubrication, boundary lubrication can be possible with reference to different diameter. And you can see that here it's more interesting. At a smaller diameters are more beneficial. Like keeping a smaller diameter means about 32 to 36. You can see that film parameter is achieved about 10. It is in the case of mixed lubrication regime, but it is still preferable because you cannot have the situation where you can go for a better lubrication regime. So film parameter we try to increase it, but it is very difficult to keep what you can say that this lambda can be easily achieved because lambda is dependent on the many geometrical factors, body fluids, and roughness parameter. Because polymers are not possible to finish to the smooth level. We always get a rough surface. When you see any cup, the ball is here. So obviously you can find that the cup inside surfaces are rough. So you can understand what I'm saying. This is a surface. This is a ball. The inside surface is cup. Because polymer liner, the roughness will be more. It will get effect of the overall what I'm conveying that the film formation, lubrication regime it is get forming all because of the effect of diameter of the ball and the surface roughness and other features. Next is geometrical characteristics. You should know that the surface roughness parameters are very much important. All our artificial joints being designed to what you can say that take up in the good lubrication regime. It is being designed to take up in the what you can say the thin film. So therefore, surface roughness is about 4 nanometer is being maintained. So therefore, RA value, RQ value, and all will be very much important because RA value is a normal value, but RQ value should also tell about the surface feature. So the surface feature in the sense the same value of RA, you can get a different same surface surface picture. Maybe it will be like this, something like this. The other surface may be like this. Same value of RA. So therefore, RA value may not be giving full information. We will be taking the square of that value, that is root mean square. RQ, there are other parameters like RZ, Rmax, RT, and so on. But we go for a three-dimensional structures. So three-dimensional features will give us more versatile information than the earlier one. So I was mentioning about the femoral component, acetabular component, femoral roughness, acetabular roughness, the lambda value being calculated by various researchers considering the combinations of the materials. So the lambda value uh, is less than 1, equal to 3, or maybe, so you can understand that still it is a speculation. There is no guarantee that the particular lubrication regime is operating. So rather we can say that whenever you go for artificial joints, we assume that it is a boundary lubrication or a mixed lubrication regime. So what is boundary lubrication regime? You can understand lubrication regime. Fluid film liquid. So basically this is reference to the interaction of the two surfaces. Boundary means asperities are meeting each other. In mixed, partially the load will be taken by the asperities and some amount of lubricant. Fluid film is completely separating the two surfaces. So it is being correlated with the Sommerfeld number, considering the viscosity of the fluid and entraining velocity and the load. So we can find if lambda is less than 1, then the boundary, if the lambda is varying from 1 to 3, it is mixed. And if lambda is 3, more than 3, it is full film lubrication. So this is lubrication regime is formed under the various situations. Now, beware of artificial implants. So what is happening? There are situations, sometimes we will be finding uh, particles, third body particles entrapped between the two surfaces, and it create a problem with reference to the looseness of the joint, or aspetic loosening of the joint can be possible. Aspetic loosening are the, what you can say, this osteolysis are the main problem with reference to the looseness of the joint. So this is happening because of the wear of the joint. Wear particles will create a third body problem. So therefore, we have to overcome from this one by designing the joint properly. We can minimize the wear. So the adhesion, abrasion, all these mechanisms are very much common in the wear of these particles. So it is very predominant. So we try to see that the volumetric wear is 30 to 100 millimeter cube per year. This can be measurable one. You can see that in metals it is very less, but it is going to create a problem. Carcinogenic effect. Please, in the case of ceramic, it is about 0.05 to 0.1. This is being measured in the millimeter cube per year. In the linear rate micrometer per year, it is 100 to 300, 50 to 150, 2 to 20, and 1 to 20. This can be quantifiable by using the radiographic instruments, and particularly whenever we come across with the term called periprosthetic surgery. There are situations sometimes joint fade. People try to retrieve the joint and try to measure what is the volumetric wear which has happened over a year. Or sometimes we use radiographic instrument by using the follow-up situation and try to measure the quantification of the wear. See now, as I mentioned, osteolysis is one of the important problems because of the wear, that is looseness of the joint. So we always try to see that how best we can test in the laboratory scale. We always go for a laboratory wear test. A reliable wear test is required because varieties of designs are there on the hip joint and the knee joint where simulators are available, and we try to simulate for the body condition, and ultimately this problem can be overcome, osteolysis problem. the biotribology, substantial amount of research has been devoted for testing of this material to minimize the wear, or maybe you can say that to find the life expectancy of the joint. So a lot of work is being done on the biotribology. So now we can see that one of the important issue, natural human deep joints is a ball and socket. Artificially stimulator is also ball and socket. The diameter is here is more, it is less in the artificial joint, and of course the velocity is same, flexion same, motion is also same, loading is also same. Temperature also we can keep more or less same, but here temperature will increases as the things are operating over a period of time. It will raise up to 70 degrees. Volume of the sonar fluid inside the body is about 2 to 4 milliliter, even less than that. So it is not ethical for us to take out the sonar fluid from the body and put it inside and try to make a measurement, because it's not possible to collect such a huge volume of biolubricant. That is 200 to 500 millimeters. Some instruments have been designed to have with a small fluid. Viscosity, it is non-Newtonian. This one, my sonar fluid, but it is a Newtonian because you use water, saline fluid, or maybe cow blood serum by Sigma Aldrich. They use such liquid for testing inside in the laboratory scale. Replenishment is continuous, and of course here it is at interval you have to take down because degradation is faster. This is a simulator which you can see, the complex simulators. I will show you some of the simulators at the end. In vitro testing is a challenge because we have to simulate for the movement, lubricant involved, temperature, load, frequency, and so on. But still, we are successful in having the what you can say that different types of devices and try to test in the laboratories. A reliable in vitro test device which accurately mimics the in vivo condition. In vitro means laboratory scale. In vivo means inside the body. We have less complex screening devices like pin-on plate, pin-on disc, all these things, but it is a continuous sliding motion. The wear factors which you obtain, it is not the representative of the one which is seen inside the body. So it is obtained about 10 to the power of -7 or -8, and it is generally 2 order or 3 order less than that of found in the in vivo condition. So we are not interested in simple devices like pin-on disc or a pin-on plate. So people initially they were using this kind of device, continuous sliding, reciprocating, but later they realized that multi-direction is most prominent because our body is also always designed like that. So the pin will be rotating here about its axis, and the table will be reciprocating. It's a small device, so some force stationary. So obviously, in vitro wear testing is one of the thing which is being done for the smooth movement of the so for smooth assessing of the screening of the material. In bidirectional machine, we try to see that the pin is always going to follow the different path like this, or a straight line, or maybe it is going to be like this or like this. You can create the path. So such kind of machines are also available. You can see that it is a reciprocating and oval shape or a double elliptical shape or a triple elliptical shape. This can be possible, you know. These kind of devices are available these days in the market. You can buy and try to see that. But the only intention is why it is being tested. For example, if you test it continuously like this, the strain hardening will be going to happen in the polymer. I mean to say that strain hardening will create some sort of a shielding for further wear of the material. So therefore, it is not acceptable. So therefore, they try to have the multi-directional motion. Therefore, always the pin to face the new face. So this is a simple circularly translating pin on this machine. It was developed by Psycho, a great scientist and biotribology from Sweden. He has developed so many test tricks. So here we have the 50 cups. Even you can also have 100. I mean, two type of test tricks are available. These are all the solid fluid being put inside the system, and of course the cup contains the lubricant about 20 to 30 milliliter, very less, but it is surviving for a 1 week time because we have to conduct the test at least for 5 million cycle. It comes to 7 weeks or 8 weeks time. Continuously, the machine should operate. So this is assembled view. We have the test pins being used in the particular situation. So this is regarding the load carrier model and all these things, and water is being continuously circulated to remove the heat. There are other machines like random pin on this machine is also available, but only few stations are there because we need to have a large number of stations. So random motions also helpful to see that the pin is always move in the fresh path and give us the representative wear similar to the body condition. So this optical micrograph before testing and after testing, you can make out that it is completely plain surface we are finding. This plain surface indicating that the all surface is being worn out, aspirate is being worn out, and plain surface is being obtained. Lubricant for in vitro testing, because another challenge we always face is how to test the lubricant. The lubricant which we use is a not a solenoid fluid. We use in the laboratory scale, what you can say that cow blood serum, calf serum is being used for testing. It is as per the ASTM standard, ISO standard. But human body has a very less amount of solenoid fluid, 2 to 4 milliliter. But body has, sorry, for simulators it requires 40 to 600 milliliter. So various researchers have adopted different types of lubricant. For example, non-physiological fluids are possible. Some physiological fluids are also possible without protein. Water, deionized water, saline solution, ringer solutions, and so on. Physiological fluid is the one with the Bowen serum with the protein. Because why I'm stressing this point, the lubricant is one of the important issue for testing. If the lubricant is not chosen properly, you may not be getting the representative value similar to the body condition. Principal constituent of the lubricant, if you look at, you'll be finding the solenoid fluid, it is 970 gram per liter of water, protein is about 17. In the case of Bowen serum, it is 60 gram. This is the difference. So you have to bring down the protein content also. But you have the other residues also, chloride, sodium, potassium, everything is also available in the cow blood serum or bovine serum. You know what is this bovine serum? Bovine serum is basically when they cut cow or bovine, they take out the blood and process it for testing. So sometimes the countries like India, ethical issues will also be there. So now, if you look at the composition of the solenoid fluid, healthy solenoid fluid is 10 to 30 gram per liter. Hyaluronic acid is the one which is helpful for maintaining the lubricant in the joint. Phospholipids are helpful for bond lubrication. But if you look at the osteoarthritis case, the protein content will be keep increasing. That is the reason the patient will come across with the problem with reference to the kidney also. Whenever the joint pain is there, so because solenoid fluid increases the protein. Once it is more protein content in the blood, the load will be more on the kidney and this create a problem. Therefore, they are being advised not to take much protein. hyaluronic acid is there. So you can find out the difference between the sonal fluid, healthy sonal fluid, and the deceased joint. There is a difference, and this difference also going to affect on the our testing. I mean to say that what I mean to convey that our bovine serum is not the sonal fluid, but still we have to use it because we don't have alternative. Because as per the standard, the protein content in the sonal fluid is about healthy sonal fluid is 17 or 20, but it is about 60% here. So we have to reduce that protein content for testing. So what we do, that is Sigma Aldrich is the company which supply the Boyne serum. It says that's 45 to 60 gram per liter of protein and remaining some albumin, globulin and all this is protein content and some salt and all is present similar to our body sonal fluid. When you try to test what is the effect of this protein on the wear, you can understand that about 20% the wear rate will be keep increasing, and thereafter protein increasing the protein content causes a decrease in the wear rate. So therefore, in the laboratory scale, we try to reduce the protein content up to 20%. So therefore, you can understand that how difficult it is. We don't have to use sonal fluid. We have to go with the buoyant serum, but buoyant serum is not a sonal fluid. Buoyant serum is just like a water, and but of course it has a protein content in it. So therefore, protein has to be reduced to our sonal fluid content. That is happening by using the diluting with the water. By using the deionized water, you can dilute it. So now the other issue here, the wear of biopolymer. We use cross-linked polyethylene and ultramolecular weight polyethylene. Of course, cross-linked polyethylene, so far it is performing well. It's a very recent polymer because the radiation dosage has been given to the ultramolecular weight polyethylene mainly to increase the wear resistance property. So, once you expose it to the radiation dosage, there will be some change in the microstructure, or maybe cross-linking is going to happen and improves the wear resistance. But mechanical property is being lost to an extent. So therefore, you cannot expose to a greater extent. You can expose to a smaller extent. So therefore, you have to be careful for whenever the ultramolecular weight polyethylene is exposed to the radiation dosage. It has been optimized over a period of time. So therefore, we have seen that cross-linked polyethylene so far it is doing extremely well in the laboratory conditions and also it is inside the body. So now you can see that how the wear factor will be affected by increasing the radiation dosage on the ultramolecular weight. It is in the kilogray scale. You can find that the wear factor will be reduces when you expose it to radiation dosage 150 to 100 kilogray scale. But if we expose more, it will deteriorate mechanical property. That such kind of reports are also available. So therefore, you have to optimize about 50 to 60 or 70 kilogray scale it is being exposed. So cross-linked polyethylene is excellent with reference to such level of exposure. So we have done some studies by exposing such polymer to the radiation, and we did different tests considering the different arrangements, and of course maintaining the same contact pressure as that of body conditions and maintaining the similar protein content about 22% or something like that. So we have seen that the ultra cross-linked polyethylene has significantly reduced the wear factor. Remember that we have tested 50 samples. 50 samples. You know, this sliding distance is about 80 kilometer. Test is completed after 3 months. So you can understand the level of work involved in this getting one set of 3 months for one set is 6 months. So totally it is a 6 months work given us the simple graph. But ultimately it shown a meaningful result. Cross-linked polyethylene is a wonderful polymer as compared to a trimolecular weight polymer. Same kind of test we have done it for the other test situations also, but other cam and follower kind of arrangement. We can make it like different pattern of movement, and that's given the meaningful result. So ultimately, you have seen the percentage of reduction is 80 to 78 to 80%. 80% reduction is very great in the with reference to the SAN factor, and therefore the cross-linked polyethylene is excellent. So we have also seen some of the in vivo examination, that means that taking the patient to the radiographic technique and try to measure what is the thickness loss over a period of time. So we have seen that cross-linked polyethylene is extremely good here also. Only ultra-molecular weight polyethylene is more. So therefore, so far cross-linked polyethylene is doing extremely well for a period of time. There are situations that whenever the periprosthetic surgery happen, people try to see that what is the shape of the particle they see. Is some sort of fatigue failure, rolling, and agglomeration of the particles are seen. So same kind of thing after testing, people have seen how does the particle looks like. It is similar to the one which looks inside the body. So why I'm saying that a simple pin on disc machine with the small modifications, one can possible to have a multi-direction motion by means of cam and follower arrangement, and this can also give us the representative test similar to the uh, what you can say that simulators. So one of the important factors here, what are the challenges here? The lubricants used for polymer based testing, bovine serum is not the sonal fluid. We have to go for a less expensive serum, and whether to add some additives in the lubricant for testing and try to find the alternative biopolymers which is better than the cross-linked poly. Like that, we have several challenges here. So we need to see that those challenges can be met in near future. I will try to show some of my videos which shows the what you can say that test we have done it in some test rig. For example, in the three-station simulator, which is normally, can you able to see? Hello.
Yes, sir. Yes. Yes, sir. Yes.
This is a three-station IP simulator where you can find that the ceramic ball is being tested, and we have the cup for lubricant. It is running under the dry condition. So this is one of the type of simulator we normally use for screening the ceramic balls or anything. You can understand it is a multi-direction motion because of cam and follower arrangement. Okay. Now I will also show you the other test rig which I was telling, very simple test rig where pin is rotating and the lubricant has been put, and it is also going to create a multi-direction. So you can see that the pin is rotating about its axis. There are 4 stations, and also the table is reciprocating. This can also be possible. So this is the simplest situation. One can see that simplest test rig you can also explore at the laboratory scale. See, this is a 12 station pin on disc machine. You can use it just. You can see that it is a 12 station test rig where pin is rotating in a multi-direction path. There are 15 stations of this kind. It is there. This is another actual simulator where you can find that the simulation is happening under the for the testing of the knee joints. I can show you for knee joints. You can find that sorry. You can see that ball and a flat surface is running. This is another situation where you can find that a micro separator, instead of using polymer, people are exploring a very thin layer to separate metal and metal. It is continuously, it will run for a millions of cycles. So micro separation can also be possible. This is a super CTPUD is being used. The one which I was telling you, uh, which I used it in my previous. 100 station is there. It is completely robust equipment. Repeatedly it will run, give us the good outcome. You can understand how does it is working. All the pins are rubbing against the disc, and of course the water jacket is there. The fluid is going to prevent any rise in temperature, and this is one of the testing useful for testing. So these are all the some of the test rig it is being used for screening the biomaterial. I think you can understand the complexity involved here, and we have a lot of challenges with reference to lubricant and try to find alternative polymer, and even if you want to look for the different devices and so on. So these are the challenges included in the biotribology. If you have any questions, please raise.
Thank you, sir. Now, all the participants, those who want to ask question, please unmute yourself and ask questions.
No questions?
Sir, in the chat box, one question is there.
Mm.
Sir, what is the diathrotial uniaxial joint?
Diathrotial?
What is the diathrotial
Uniaxial joint?
Yes, sir.
Can you spell out?
It is DIATHRODIAL.
DIA?
THRODIAL.
Is a very, actually, see, medical terms are very strange type. Like when I was started working, I was also facing similar problem. Diathrotial joint is also again our hip joint only, because it is being put in the other formation, like other term. Because our hip joint and all is being considered the uh, uh, same time, like a hip joint itself. Sorry, knee joint itself. Okay. Diathrotial joint is most common is movable type of joints को diathrotial joint बोलता है. ठीक है. All movable joints will be called as diathrotial joint. Any gliding joints, hinge joints, pivot joints, or maybe your saddle joints, ball and socket joints, all these things comes under the diathrotial joints. The joints which is having the cartilage liner, we call it as the diathrotial joint. ठीक है?
Sir, if anyone interested, please unmute and ask your question.
I think people are getting the new things, because these days people talk about the robotic other things, they can easily catch, because the medical things, particularly this kind of work, require understanding about our own self and try to understand how the joint perform. I think the questions are not there. I'm very
Yes,
happy,
sir.
but some questions are there. You are absolutely right.
Sir, one question.
But these questions are not. Diathroial uniaxial joint is answered. Engineer, gentlemen, please mention your good name. Who is this man? Sandeep Boy.
Sir, I have one question.
Okay, I think all questions are
Sir,
not
Rajendra Behra,
relevant to me.
sir, Rajendra Behra wants to ask one question. Rajendra, can you ask your question?
Definitely.
Sir, my question is, which joints are there in the picture that you have played the video?
The videos indicates that, see, all screening of biomaterials require some test rig. You got it? So, for example, the ball on a socket. So, one of the test rig I shown you, ball on a socket for screening the biomaterial for a particular application, because our joints are kinematic in nature. Like, all joints are kinematic linkage. So, therefore, accordingly, for example, if you have a hip joint, it is a ball on a cup. So, it is a typically point contact. For example, your knee joint, it is a line contact, because it is just like, you can assume that two gears meet each other, then you can form the line joint, line contact. Like that, each contact situation created different kinds of test rig. So one which I shown, for example, for knee joint screening, ball on a flat surface, that is for the polymer, it is being tested at the high adjacent contact stresses. Similarly, ceramic ball on a cup arrangement. And there are the last one I shown you, that is CTPOD. It is meant for screening the biomaterial for the hip joints. Stress situations, type of motion decide the type of test rig to be used. I have shown you few representative test rig to understand how the different test rigs has to be used to simulate for the body condition. Got it?
Yes, sir. Thank you, sir.
Rajendra,
Yes, sir.
thank you. Any other question, boy?
I think no question. Dilip sir will wants to ask any questions. Yes, Dilip sir.
Okay, please.
Good afternoon, sir.
Good afternoon.
Also, sir, good afternoon, sir. Sir,
Good
you have
afternoon. Please
done a
proceed.
lot of yes, sir. You have done a lot of work in tribology areas like biotribology. So here I have a question about: have you studied the microstructural study on this joints?
See, whenever the joints microstructure study is not possible, because the only thing is we can test in the laboratory scale and try to show some of the information regarding the materials aspects. Suppose if you are talking about the periprosthetic failed joints, that is a very great challenge. Like artificial hip joint, lot of papers are also there. Whenever the joint fails, they take out the joint and try to see what reason it has failed. So many research papers are there, you can have a look. But the microstructural details, in the sense like bone related characterization has been done, sonar fluid characterization has been done. This kind of information is already available in the literature. So I think those information I've already I told you clearly. Because people are working in the laboratory scale and try to report their result, and try to because the designer will be looking for a laboratory values and try to implement it in a design. For example, you are a designer who designs the hip joint or knee joint. So obviously you require the information about the material, information about how best I can design to make the joint smooth, because so many issues are already there, because it should be accepted inside the body. The cobalt chromium, ultramolecular weight, cross-linked polyethylene, these are already tested well. It is well accepted by the body. So therefore, the standardization has been done with reference to the selection of the material. Now the challenge is how best I can increase the life expectancy of this joint by properly testing it in the laboratory scale. That is a good challenge. So people are working on the new test rig, new lubricant, new material, and so on.
Sir, can you
Good.
optimize these parameters, sir? Sir?
Definitely, if you can able to, and if you can able to standardize all these parameters, one can easily work on it to standardize this thing, because people are working continuously to for optimization. How best I can, because the cost of the test, cost of the testing is increasing these days, because testing is not a simple thing, because testing is also require a lot of efforts.
Yes, yes.
So therefore, whenever you are come across with the newer material, you have to test it in the laboratory, then only it will be used in the body, because using the inside the body require a lot of certification, lot of testing. That is what the challenge is.
Okay, sir. Thank you, sir.
Dr. Boi.
Thank you, sir.
Thank you.
I think,
Thank you, sir.
I think with no more questions, we'll conclude the session. Thank you so much, sir. It was really a nice presentations, and hope some of us have get a quite idea about this biotribology. And thank you, sir. Thank you so much, sir. And
Thank you. Thank you. Boi. Actually, I'm having busy schedule because the faculty recruitment is happening in my institute. I have to sit every time for a long time, because every day I am attending 4 presentations, and of course it is a responsible job. So in between I have a class, all these things. So anyhow, it is a great opportunity. I thankful to both of you, Dr. Kanchana and you. So both are taken a good initiative to arrange this kind of seminar online. You have find out the opportunity. In fact, I wanted to come to your place somewhere in the March. So now it has happened in this way. It's good. Uh, we shall see some other time to meet you all in your campus.
Yes, sir, definitely.
Again, thank you, Boy.
thank you,
Thank
sir.
you.
So
Thank you once again.
Thank you, sir.
Bye.
yes.
Thank you.
Bye bye. The feedback form has been shared with the chat box. So participants kindly fill the feedback form. So we have a lunch session now. So after the lunch session, and the next afternoon session will be started at 2:30. So the same link you can join, and at sharp 2:30. So we have post lunch session. We have 2 more session. Thank you. कंचन मैडम ये लिंक तो शेयर कर दीजिए अंदर.
हाँ. Hello. Sir, already links are shared in this chat box as well as in WhatsApp. Okay. So they can use both the links for the feedback form for the session 1 and session 2. And next at sharp at 2:30 we are going to start the next session, session number 3. So all are requested to join before 15 minutes. Okay. Thank you.
Thank you.
Hello, hello.
Kanchan madam. Hello.
हाँ सर
Sir join କରିଛନ୍ତି?
नहीं सर जॉइन तो करी नांती मु फोन करथली करूचंदी कहले 5 मिनिट रे
आज्ञा
करन तो तपरे स्टार्ट करिया हां
आज्ञा
ଏବେ ତ ଆଉ 7 ମିନିଟ ଅଛି 6-7 ମିନିଟ ଅଛି
ओके ठीक ठीक ଅଛି।
Hello. Hello. Hello.
Yes sir, yes. आज्ञा welcome sir.
Oh yeah. Good afternoon.
Good afternoon sir. Good afternoon sir. I think sir your audio is quite audible.
Hello, am I audible?
Yes. Yes sir, yes sir.
Yeah.
You are audible sir. So I heartily welcome Professor Santosh Kumar Sahu sir. He is associate professor in mechanical engineering department at Indian Institute of Technology, Indore. He has received his bachelor degree from UC Bulla, currently Basut, and completed his master from IIT Bombay and PhD from IIT Kanpur in the year 2009. Prior to joining at IIT Indore, he has served as assistant professor at NIT Raulkela during March 2008 to October 2009. His research interests include reweighting of hot surfaces, quenching of hot stationary and moving surfaces, heat transfer enhancement with nanofluid, heat transfer behavior of gaseous flows in micro devices, pool boiling heat transfer impinging jets, heat exchanging equipment, phase change materials, synthetic jet, flow through corrugate tubes. He has published one Indian patent, 54 international index journal paper, and 60 articles in international conference proceedings. Besides contributing 5 articles in the edited book published by Springer, he has guided one postdoctoral student, 7 PhD students, and 2 MTech students, and 9 PhD students are currently working under his supervision. He has received the prestigious IUSSTF Research Fellowship by Indo-US Science and Technology Forum for Engineering Sciences in 2011. Under IUSSTF program, he has visited Purdue University, USA during September 2011 to January 2012. In addition to this, under OBD fellowship, he has visited Purdue University, USA during October 2019. Dr. Sahu has carried out various research projects funded by DST, CSIR, SCRB, IUSSTF, India. He has served reviewer of 30 international journal, several conference proceedings, and PhD thesis examiner of various NITs and IITs. Currently, he is serving as head of the mechanical engineering discipline at IIT Indore, and he is IIT Indore GIAN coordinator since February 2020. He has served as chairman JE during July 2014 to July 2015. Today, his topic of presentations will be on jets impingement, cooling, modeling, and experiments. Now I will hand over and invite Professor Sahu to carry on. Thank you, sir.
Thank you, Professor Bhoi, so for the nice introduction. So it is my pleasure to be here through online. So it is a nice opportunity that I am thankful to the coordinators for giving this opportunity and to share our experience and research experience on different aspects. So this talk basically, this is based on this jet impingement, and just I am sharing the screen. So here probably this thing, some internet issues are there. So let me share the screen. Okay, so before that, just I will keep on telling once this screen is shared, so it will come. Okay, so now I will share this screen and so it is fine. It is audio, like it is visible.
Yes, sir. Yes, sir.
Okay, so should I start the presentation if it is all right?
Yes, sir. Yes.
Okay, so as I discussed, like this talk is mainly focused on jet impingement cooling and what is modeling and experiments on that jet impingement cooling that we will be discussing. So let me introduce why this jet impingement. Like in this presentation, we will be discussing basically the jet impingement flow characteristics and the test facilities we have developed, and what are the different fluids we used, and results and discussion and summary of all these things. So first of all, let me introduce what is the jet impingement. This is one mode of cooling. We can have different modes of cooling. This is widely used because of its lower flow path, because it does not have this flow more flow path. and simple geometry, and we can have a significant amount of heat transfer by this jet impingement thing. And in many cases, we can have this uniform cooling on a hot surface. So based on that, we can have different parameters. They influence this jet cooling, that is Reynolds number, nozzle to plate distance, and radial distance, and fluid temperature, and curvature of the target, and roughness of the target, all others. So basically, what is the application? There are various applications we can focus on this jet impingement. Suppose we are using a gaseous fluid, then we can talk about food products. Basically, agriculture food products, they need to be dried before its storage. So that we can use hot air for drying these food products. Similarly, in textiles and paper industries, we can use hot air for drying and other purposes. And in addition to that, this cooling of gas turbine blades, that is kind of mixture, air and water, air is used. So jet impingement cooling is basically used. And in case of electronics cooling also, we will have heat sink embedded with this fan or like that. So here we can use jet impingement cooling as well. In addition to that, we will have metallurgical industries where processing of metals and other things, there we can use some liquid fluid and we can process the metals. Apart from that, we will have this nuclear reactor cores where emergency core cooling is very vital. Otherwise, it will lead to a catastrophic failure. So in such a case, we need to use some jet impingement mode of cooling to restore the condition and to bring back the normal condition of the fuel pins. So what are the coolants that one can use for jet impingement cooling? There are many coolants one can use, but because air is easily available, and so one can use air as the fluid. Of course, water has high conductivity and specific heat, so water can be also used. In some cases, there is a scarcity of water, so one can use air and water mixture, that is known as mist. In addition to that, people have done significant research on preparing a novel fluid, that is nanofluids. So where some amount of nanoparticle is added with some aqueous solution, so that can be also used as a fluid as a jet. So first of all, let me introduce what are the parameters that influence the jet impingement heat transfer. So in any case, we need to study the heat transfer in two different regions. So if I can say, suppose this is the hot surface, this is the hot surface, and this is the jet. So the fluid is issued from the jet and it travels this amount of distance before it hits to the hot surface. So there are basically two different regions, broad regions. This is one region we can say in the axial direction, and this is some sort of streamwise direction. So this is, suppose this is, we can just make this is the vertical distance and this is the axial distance. So in the vertical distance, we will have different regions. Suppose we maintain less amount of, suppose this A plus B, that is less, then we will have some kind of heat transfer. So basically what I mean to say is the heat transfer depends on this distance, vertical distance, as well as the heat transfer varies from this axial direction. In the stagnation region, this is the region that is shown in the red color. The heat transfer is very high, and it gradually decreases as we go from this level, that is the wall jet region. So it gradually decreases. And similarly, we will have, suppose the fluid jet issues from this side, then we will have potential core, and we will have this uniform velocity profile, and this velocity profile changes. And these are some vortices that are generated when it issues from the fluid. So this structure we are discussing, basically we can have two different fluids. One is the air and other is the liquid. So in both the cases, we will find different ways of velocity profiles. You can see as the jet issues from the nozzle, then it gradually diverges. Means it takes atmospheric air means the entrainment of atmospheric air takes place and it broadens. So we can say mass is included in the jet. Okay, more mass is included in the jet. So then the profile becomes wider as it goes away from the nozzle. But if you see in case of liquid jet, you can see that it is converging here. The width is much higher here at this jet exit. But as you go on farthest point, then this diameter is decreasing. So this is the basic difference if we see for the air jet and water jet. Here you can say, you can see if you apply Bernoulli's theorem, then you can find out like how this velocity increases as this height increases or whatever. So based on that, this area also decreases. So this is the basic difference you can notice. You can notice also when you take your bathroom, when you open the tap, you can notice like how the jet diameter decreases as it goes down. So heat transfer, that again can be classified based on this condition, whether this boiling takes place or there is no boiling. Like if the hot surface is significantly higher, then of course we will have some kind of boiling phenomena. So this boiling also they are classified as single phase forced convection, nucleate boiling, film boiling, and agglomeration of pool, radiation and convection. Based on the temperature, wall superheat, we will have different kind of boiling modes. So that also we can discuss. In addition to that, we can have some significant characteristic like what are the configuration or classification. When we talk about certain thing, then we consider its classifications or configurations. Basically here we will have like how the jet is classified. One is free surface jet, another is plunging jet, this is submerged jet, and it is confined jet and wall jet. So this is free surface jet. Here you can see, hello, free surface jet. So this is the liquid is the fluid here, air is the surrounding medium, and this point is known as stagnation point. This is free surface jet. Now, in case of liquid plunging jet, you can just imagine what example I can give you in the rainy season. Of course, now this rainy season is just going away. You can see in the rain season, when sufficient rain takes place, our surface is wet. Okay, some water layer will be there on the any road or any surface and on any ground. So you can imagine if some raindrop falls on this fluid layer, how it looks like. So it will plunge. So this is liquid and this is the liquid layer. So it will make a small plunge. So this is known as plunging jet. Okay, already liquid is there and you are forcing liquid on that. And this is submerged jet here. Submerged jet means the fluid and this thing, they are same. Okay, air and air. So this is the submerged one, and this is confined one. Confined means this is the nozzle and this is the hot surface. So there is a confinement. It is not free. So this is the confinement. So based on this confinement distance, the heat transfer changes. And wall jets, they are already horizontal flow of fluid takes place in this case of wall jet configuration. And these are the some of the applications that we discussed already, like how this takes place. This is a photograph of a steel plant where this steel sheet that is moving. You must have visited any steel plant. You can see how this ingots there, this thickness is reduced, and after that people do some kind of, here you can see like these are the sprays or water thing. Basically they are sprayed or they are impinged from the top and bottom, because we need to maintain the heat transfer in both the surface, top and bottom. So both the sides cooling takes place, and this is moving in this direction. So this is one way of application of these are basically some kind of jets, planar jets and like that. So this is jet impingement cooling in a runout table, and this is the hot strip and it is moving. So the cooling takes place from both top and bottom, and this is the rollers. Because of this roller friction and this heat is generated, so we need to reduce this temperature, and jets are used to maintain the particular temperature. In addition to that, we need to maintain the mechanical properties, the rate of cooling that decides the mechanical property of the hot metal. So we have our control. So that way we can control the rate of cooling. In addition to that, we always need to know what are the mechanisms of heat transfer and how we can control and how we can assess why the heat transfer is higher, why the heat transfer is lower, what is the reason behind that. So for that, we need to know this velocity profiles. When some jet is coming or jet is issued from nozzle, then we need to know what are the velocity profile here and how this velocity profile takes place at some particular distance. So this is a vertical configuration. With this liquid jet and top jet, they are maintained perpendicular to each other. And this is the top side, and this is the bottom jet. This is the hot plate, and this liquid is forced to impinge on the plate from the bottom side. That depends on the application. What are the applications and which way it is convenient. So always we cannot have a top side cooling. Sometimes we need to have bottom side cooling also. So based on that top jet and bottom jet, of course we will have different heat transfer mechanisms in top jet and bottom jet, because of gravity, you can say here gravity makes a role in case of top jet, but in case of bottom jet, you see gravity is against this force, so velocity will be reduced here. So that is the basic difference in top and bottom. In addition to that, this liquid will be accumulated here in case of top jet. When liquid is striking on this top plate here, then some liquid will be accumulated on this surface. But in case of bottom jet, immediately the liquid will fall off. So there is no accumulation. In many applications, we don't have sufficient space. So sometimes we need to make the inclination. The jet is inclined to the hot plate. So this takes place like that. And here, based on that, whether we need higher heat transfer in some particular side or lower heat transfer in some particular side. So all other things are considered. So we can adopt a inclined jet. Here we can say this is the moving thing. Just now we discussed a hot rolling mill here. Then this hot steel that moves and the liquid jet impingement takes place. So in that condition, what will be the mode of heat transfer? So that is the case how this velocity profile looks like in this case, moving surface. As we have discussed this mechanism of heat transfer here, in case of boiling, when the hot surface is temperature of hot surface is high, that is basically in case of steel plants or steel industries, this temperature is quite high, metal temperature. So in such a case, we will have different modes of boiling: single phase, forced convection, and nuclear boiling at this region, forced convection and radiation, like that. So this is in case of top surface, and this is in the bottom jet condition. These are the different modes of boiling that we can observe in case of jet impingement. This is just we will give some examples how this jet impingement takes place. This is the facility we developed at Kharagpur during our PhD. Just I am sharing here. This is the setup we have developed. This is based on the Bhabha Atomic Research Center, this sponsored project, this advanced heavy water reactor. They are adopting now for power production. We will have 54 fuel pins. So these 54 fuel pins, they are arranged in 3-piece circles. If you can see, this is the end plate. So there are 3 different piece circles. This length is very small, 100 mm, something like that. So here we need to arrange 54 fuel pins. These fuel pins, they represent uranium fuel rods. The diameter of each fuel pin, that is 11.2 mm, and this is up to 3 meter height, and they are heated something 400. So the purpose of this experiment is to assess. There is a central coolant tube. This is the central coolant tube. So water is injected from this central coolant tube, and it cools the fuel pins that is surrounded in this thing. So we need to assess like whether this water that is coming out from the central coolant tube can reach to the farthest location. And in addition to that, when it is cooling, a lot of steam will be generated, and the steam will have upward movement and the liquid will have downward movement. So there will be a counter current flow phenomena, and how this thing affects the heat transfer rate. So all those things we have studied. Here what I want to focus, like when the water comes out from the central pipe, here some holes will be there. 6 different holes will be there at different axial location. So they issue just like a jet. So we need to study the jet characteristic. So this is the configuration here. These are the fuel pins, and this is the central coolant tube here. The water will be injected from this coolant tube, and it can hit this fuel pin, and next it will come to like that. So this is the cooling of a typical cooling system of a advanced heavy water reactor, how this jet impingement is applied in different fields. So these are some of the findings, how we can get the temperature at different locations. We will have this 54 fuel pins and some 400 thermocouple, 300 thermocouples were there to monitor the temperature. Now coming to the surface that this we have developed at IIT Indore. So here this has this provision of moving thing. The surface can be moved. So by a stepper motor, here this is the bed, and these are rollings by which under which this can move. Okay, so this stepper motor is used to move the surface, and this test specimen will be placed over the surface. And this is the arrangement of water injection. It is injected from the bottom, and this test surface, that is a very thin foil of 0.15 mm stainless steel. So that is heated by Joule heating. We can ensure some kind of constant heat flux for a particular region. This current will be something around very high, 140 amperes. So we could able to reach around 500 degrees centigrade by Joule heating, and some other parameters are used. So this is the fuel that is injected, some gear pump arrangement, and this whole system is purely it is automatic. We can included all the parameters through computer. It can be controlled through computer. Once this fluid supply system and its velocity and its fuel injection time, liquid injection time, they can be controlled through computer. So that we have prepared. So this is some sort of maintaining this distance, vertical distance, and based on this experimental investigation, this is a liquid impingement from the bottom side, and water is used as a fluid, and stainless steel is used as a test surface. The temperature was maintained something 500 degrees centigrade. It was heated by Joule heating, and the temperature measurement was made by using a infrared thermal imaging camera. So that can measure up to a temperature of 200 degrees centigrade. So this is the photograph of a thermal imaging camera. Here you can see different colors denote temperature, a different temperature. This is the scale in the side. This is the scale. So this is the scale, and temperature corresponding to that temperature is shown. Here you can see that yellow color that shows something 500 degrees centigrade. And this some color black kind of thing that shows something 100 or 45 degrees centigrade. This photograph, that is after liquid impingement. But if you can see this figure, that is without impingement. You can see like how the jet appears with respect to time. This is the thermal image. You can see that the jet spreads, and this temperature gradually, this temperature will be very less. And here, this is the photographic observation. When this jet impingement takes place, you can see like here it is some kind of circular thing, and this is the liquid phase. Two different regions are observed here. This is the liquid region, and this is the dry region. Of course, some fluid will be spluttering here, droplets. And with the progress of time, this diameter of the wet region that increases, so that there is a distinct region that is known as wet front that progresses with respect to time. Here, that we call as wet front. Wet front, it moves with some velocity. That we will discuss later. This wet front movement, that is a typical characteristic with the heat transfer behavior. And this is the way this wet front is propagating. And this is the area, and some liquid falls like that here. And here in this curve, we try to plot a boiling curve here, like this heat flux distribution with a radial distance. So this is the radial distance. Here we can say like different regions like boiling, transition boiling, and nuclear boiling. This is the nuclear boiling, and this is the wet region. So this is the way we can say like a variation of temperature and heat flux. This is more important, like in any experiments, we need to measure some temperature, any data. So here in this experiment, we were measuring this flow rate, we were measuring this temperature. So once you know the temperature, once you collect the raw temperature from this thermal imaging camera, then those temperature data need to be used to find different performance parameters. So here we can say this performance parameters, that is heat flux, heat transfer coefficient, and other rewetting parameters are there. So how we can find out? You know temperature on the surface, but how you can find out heat flux, a different thing. So for that, you need to develop a model, or you need to balance this heat. So here we can have some model we develop. You can develop a model, like you can make some heat balance arrangement. What is the heat generated, what heat stored? So these tests are done in the transient condition. We heated the plate. After attaining something 500 degrees centigrade, the power was switched off. So gradually the power was switched off. So then it is a transient mode. It cools in a transient mode. So this is the way we calculated this different heat losses through different modes. We will have radiation here, top surface, and we will have some conduction. Plus in this side, we will have convection to the ambient condition, and we will have convection to the liquid. So that is more important, like how much heat is transferred to the liquid and how much heat is lost because of some other things. So we took a assessment based on like if it is less than 5%, then we have neglected. But this is the way we calculated this radiation loss and convection loss and other parameters. Then we could able to find out the heat flux distribution in this formula. So then these are the some kind of results. We can have this maximum heat flux distribution here, how it moves from the radial distance, and this is highest at the stagnation point. That curve one can see, like at z is equal to 0, the point at which the jet strikes, that is known as stagnation point. So here we get the maximum heat transfer because the momentum and everything is high there. Then gradually this heat transfer reduces as we go away from the stagnation point here. And this is the maximum surface heat flux like that for different Reynolds number and Z/D here. And some correlation we proposed based on the test data. This is we discussed, like we were discussing this Pecklet number. This is the significance of wet front velocity here that I was discussing. When you saw this diagram, there is a particular wet front that propagates in particular direction. So that is known as rewetting velocity, the wet front that travels, or wetting velocity. So that wetting velocity, that plays a significant role in cooling behavior. So this is this wetting velocity that is represented by a Pecklet number. This is like this U is the wet front velocity, delta is the thickness of the foil, Cp is the specific heat, and rho is the density, and K is the conductivity. So here we can have all these parameters. This rewetting temperature also we calculated, So rewetting temperature means at what temperature the wetting of the hot surface takes place. Because for that I will give one example so that you can just make a guess. Suppose there is a very hot metal and you take and you will have a pool of liquid in a bucket. So you suddenly dip that hot rod inside the liquid pool. So immediately the liquid cannot wet the hot surface. So there will be a vapor blanket that will be generated and that will prevent the liquid contact with the hot surface. So as the process continues, then this vapor blanket will collapse and this rewetting of the fluid to the hot surface will take place. Means what I mean to say, there is wetting, rewetting and non-wetting. Like that it takes place. Immediately liquid cannot wet the hot surface if the hot surface is, so the temperature of the hot surface is significantly higher. Then we will have this is a moving surface. As we discussed, like if the plate is moving, how it affects the heat transfer rate. So here we considered that this jet that is issuing with a nozzle with 1 mm diameter and the plate velocity is 0 to 40 mm per second. This is the moving bed. Here this is the moving bed and it is moving. These are the linear rails and this is screw here. So it moves with 0 to 40 mm per second and the surface temperature is something 500 degrees centigrade and this is the jet velocity. Reynolds number is varied between 2500 to 10,000. So these are the conditions we considered for this thing. Here you can see what is the basic difference here I want to point out. If the plate is not moving, then you can say a U-shaped curvature. The temperature profile will look like a U-shape. Okay, so just like U. But when it is moving in one side, when you get more fluid, then it is known as the upstream direction. Here you can see the more uniformity in temperature. What I mean to say is that at x is equal to x by d is equal to 7, the temperature will be something 150. And at x is equal to 0, the temperature will be 100. So I can say delta T is 50 for a horizontal distance of 7. Now you can consider this side 0 to 7. For a distance of 7, the temperature will be, here suppose here it is 100, here it is 350. So what is the difference? It will be 200. So here my point is, like if you have a lot of temperature non-uniformity, then your lot of problems will come, either in maintaining the material property or some other deformation, some other residual stress, or even cooling. So residual stress and metallurgical properties. So all other problems will come into picture. So in many cases, we need to maintain a uniform cooling. So that here we can maintain, there will be different components based on the applications. For some components, we need uniform cooling or faster cooling. In some components, we need not uniform, it can be done anything. So because we will have components, they will be made of different materials of different conductivities. So under that condition, we need special treatment for different components. So that can be adapted. Now you can see here thermal images. Here these are the thermal images, how it looks like when in a moving condition. You can see like these are the thermal images and the flow profile also that can be generated. So one can have different parameter, like one can visualize what is the mechanism of heat transfer and how it affects. Here we can say just I want to mention here like what is the role of moving plate velocity, this moving velocity or plate velocity. Here this maximum surface thing, this is the axial distance here. So the maximum heat flux that occurs at the stagnation point, and that is seen, that is observed when the plate is stationary. That is obvious. When the plate is stationary, the jet completely heats the surface and all the fluid they are utilized to cool the surface at the stagnation point. But you imagine, suppose your plate is moving, so there is a less amount of time that will be exposed to the jet because it will be moving. So not sufficient exposure will be there. So because of that, in moving case, suppose at x is equal to 0, I will call that is the stagnation point. So in stagnation condition, the stationary plate will have higher heat flux compared to the moving condition. But that always we don't need. Okay, we also need uniform cooling of this farthest location. So as we move on, you can see, suppose you are cooling by a stationary jet. So what is the distance here? The distance is 1.75 mm. With a distance of 1.75 mm, the temperature difference will be something, the heat flux will be, here it is something, say approximately, I will say 4, here it is something 4.2, here it is something 7 or 7.5. Okay, so it is, suppose roughly you say this is 4.2 and this is 7.2 something. It will be more than, so it is 3. Now you consider here the plate is moving here. So for the same distance, 1.75 distance, here the temperature is something 6.2 and here that heat flux is something 7.5 megawatt per meter square difference for a distance of 1.72. But here in case of stationary condition, it is some kind of 3 or like that. So you can see that what is the non-uniformity in heat flux distribution. That will generate a lot of problems in designing different aspects. So we don't need that. Always based on application, we need a uniform heat flux. We need to maintain a uniform heat flux distribution in some cases. So that is achieved in case of by moving plate velocity, which could not be achieved for a stationary condition. That is my message here. And here you can see like heat flux, how it is moving as the plate velocity increases, then we can have this heat flux decreases, maximum heat flux that decreases. Based on that condition, we could able to propose a correlation here. This is the correlation we can see based on the maximum heat flux, that is a function of Reynolds number, plate velocity, and axial distance x by d. So here what you can see, like the purpose of correlation, you can see like which parameter is dominating to determine the maximum heat flux. You can see that exponent of different parameters, Reynolds number, plate velocity, axial distance, how these exponents they contribute in for the maximum heat flux. Another important thing, like here always we talk about energy efficiency or cooling efficiency. When you see here in this curve, this plate velocity here, in the last curve I have shown this plate velocity and that maximum heat flux is decreasing. So one question somebody can ask, like whether we should go for a higher velocity or lower velocity. Of course, if you increase the plate velocity, your maximum heat flux is decreasing. That is what this curve says. But here you see cooling efficiency. Okay, in terms of energy or cooling efficiency point of view, like total the whole domain, if we are increasing the plate velocity, the cooling efficiency increases. So that is the point here, like it is certain advantage. Like all the things, whatever you get, whatever observation you get, they have different applications. So based on the application, one can adapt what is your purpose or what is your objective, like that. So always when somebody conducts experiment, we need to assess like how it is closely, what is the relation of this present experimental results with other experimental studies. Always they cannot match with each other because experiments are conducted under different conditions, like mode of heating, mode of method of heating and method of cooling, nature of test surface. All these things are different. That actually affects the heat transfer performance or behavior. but still one can compare, like okay, so this is the result obtained by this person and that is the result obtained by that person. So here we have considered a velocity ratio parameter, because in any case in model study or any other study we get some parameter. So this is the plate velocity and jet velocity. They can be like merged, and that is the ratio of velocity ratio, because different authors, they will have a different plate velocity and different jet velocity depending upon their availability of resources. So we can have a generalized parameter here, velocity ratio. So that we took, and we could find this maximum surface heat flux. So here you can see, like this is our experimental range, because our velocity ratio is very less. And for other cases, we can have this type of results. This is just a comparison how different results can be clubbed together. And this is the riveting time, and that also how it varies with the stagnation point that we studied. Now at this point, we can have jet inclination. Here, as we have pointed, many times we don't have sufficient space here. Based on the, we may not have sufficient space to accommodate different components, and many times we suppose there is a central region, and your right side that is made of different material, your left side that is made of different material. You need different treatment to the right side material, you need different treatment to the left side material. So you need more cooling to the right side and you need less cooling to the left side. So you can design your picture, like you can adopt a inclined thing. So here we will have a downhill direction, and here you will have a uphill direction. So this is the thing we can get, and this is the stand-up distance, jet inclination, how we can vary the heat transfer behavior based on the jet inclination. These are some of the parameters we consider: jet velocity and jet inclination angle that is varied. So these are some of the results. So thermal plots, thermal images that can be seen, like this is the central region, nearly isothermal, and you can see in case of inclined condition, this is the 90 degree, perfect 90 degree. We can have this kind of surface, and here it is 15 degree. So these are the photographic observations, and these are the thermal images. Here one can see, like this is the cooling time. Basically, this is the cooling time. Here you can see surface temperature and cooling. This curve is also important. Of course, we didn't discuss much on this curve. Like suppose a plate that is of 500 degrees centigrade, and suddenly it cools 200 degrees centigrade with some fraction of second, So that is the condition. So here we say that riveting takes place. Okay, the wetting takes place. These are the different transient curves for different inclination angle, and that we can. So here, what my point here is that, as you saw, there is a uphill direction, there is a downhill direction. Again, I will point out that with a fraction of time, suppose this is the time, it starts from 0.1 second to 0.3 second, you can see the variation of heat flux in the downhill side. It is somewhat uniform. You can say it starts from 6.5 and it ends with 4. So difference of 2.5 megawatt per meter square with a fraction of 0.4 second. But you can see the other direction, in the uphill direction. Here it is 6.5, and we compared to 0.4 degree. Here you can see like something here too. So what is the magnitude of heat flux difference with a fraction of time? So that creates a lot of non-uniformity in the heat flux. That needs to be taken care. Here we try to compare this jet results of jet inclination angle with other authors. So this is just a comparison. Of course, these conditions are different for different things. So one can have a trend matching up to this point, and of course here it is decreasing. So that is based because of different experimental conditions. This is some Nusselt number, that is a parameter which assess the thermal performance. That also we calculated in this condition. Here this is calculated based on the heat transfer and characteristic dimension and this thing fluid conductivity. Here one can see the variation of Nusselt number in one direction and other. This is the left side and this is the right side. And okay, so here one can see like downhill and uphill direction. One can see that the Nusselt number variation somewhat like more uniform in the right side, but here it is very different. It is divided, okay, with a distance of axial distance of 7, it is more divided, non-uniformity. So that is the divide we see here. So that one needs to take care. Now, based on this experimental data, we try to propose a correlation here, and this is the way Nusselt number is correlated with Reynolds number and other parameters. So here we can have these parameters, and we try to correlate with other parameters. This is some sort of wet configuration or wet front propagation in different conditions. So based on this temperature contours, we try to find out like how these things. So this is the movement of this wet front. Initial slide I have shown there is a circular pace, how it is propagating. So here you can see that is the propagation. Just I can give one example. Just you think there, you take a stone and there is a pond, water body, and you throw the stone. So what you observe, there is ripples of pressure waves or like that. So they propagate in different direction. Okay, pressure waves and waves, they propagate in different direction. So if it is jet is normal here, then your wet front, that is just like a pressure wave that propagate in circular direction. But if the jet is inclined here, okay, jet is inclined, this is the propagation of wet front. These are the axial coordinates. So this is the way it can look. So through MATLAB, based on the thermal images and the photographic things, we could able to generate this type of figures. Now this is a mist jet, how one can use mist jet. There are certain cases what I came to know, like in Rajasthan and other regions, where water is a problem in this western side, Rajasthan and other regions. Even if in MP, in Indore also we face a lot of water problem. Not unlike the eastern side and western side. Here in middle MP and Rajasthan, they have a lot of water problem. Water issues are there. So one can say, like, if there is a water problem, how one can use water as a coolant? That is a problem. We know that water is a good heat transfer fluid, but many of the industries in Rajasthan and other things, they don't have sufficient water, especially in the summer season. So, and you know, like if you are using only air, you will have, of course, get less heat transfer. If you are using water, of course, you will get more heat transfer. But many times that is not needed. We don't need that much of heat transfer, what water gives. And we don't need that less amount of heat transfer, what air gives. So we need to have a intermediate condition. We will have some amount of air, some amount of water. We will mix that. So that is known as mix. And we can have some moderate kind of heat transfer rate that is higher than air and lower than water. In some cases that is needed. We don't need that high amount of heat transfer what water gives. And some water scarcity is there. So there we can use mist condition. That also we tested how we can use water jet. And this type of jet many times gives uniform cooling. So that is the advantage here. This is the air atomizer spray. Like you can have a different kind of spray. How you can generate spray? You can taste it. You can think on your own. You can take some amount of water in your mouth and you can throw it. You can pressurize it and you can throw it. So that is, you will get, when you throw, you must have seen some beautiful color, rainbows and like that. So that is the spray. If you take some water in mouth and you throw away. So that is the spray. You are generating spray. Means this thing, they will entrain some water droplets, air droplets, and some bubbles will be generated. So these droplets, they will be in the suspension mode in the air medium. So that is the one droplet mixture we get. That also we call mist, based on the high pressurized spray. There is another way you can generate mist or this air water mixture. How? You can move two different fluids. This is a closed chamber here. The water is moving in the central pipe and the air is moving. This is the annulus kind. This is the annulus region. In the annulus, air is moving, and in the core region, central pipe, water is moving. So they will mix here, and some mixture will come out. This is air atomized spray. This is the nozzle. You will have a different pressure. Of course, we maintain different pressure. So basically what I mean, air water mixture, one is pressure based, and this is some kind of internal mixing nozzle. We have used internal mixing nozzle. We used to give different pressures to different fluids. This is the water and this is the air. So this is before performing experiments, we need to know like what is their behavior, flow delivery performance here. This mist loading fraction, that is expressed in mass of water and mass of air, and this is the pressure, and this is the mass flow rate. We will have a non-linear behavior. This is not like a single fluid when we consider only water or only air, how this pressure and velocity, mass flow rate, they are linearly dependent when the fluid is single. But when you mix two different fluids and where density is changing also, then we will have a very complex behavior. Okay, so that is what we get here. You can say like water mass flow rate, this is the air mass flow rate, and this is water. Of course, we maintain this constant water thing, and this is the thing, air flow, air pressure. So this is the result we get from a mist study. Here you can see it is more kind of some uniform cooling here. This is the photographic observation what we have taken here in the dry region, and this thing. This is the thermal image we could have taken. We could took during the cooling of the mist thing. And based on this cooling behavior, we could able to have this thing, behavior of surface heat flux and pressure variation, different pressure, air pressure, and we could try to compare our result with other authors. So there we will have mist loading fraction and maximum surface heat flux. So here you can say like this region we will have more heat flux at the stagnation region, and gradually it decreases as R by D is increased. But here we can have some kind of uniform cooling if this load fraction is reduced. Okay, so that one can choose based on the condition. This is also, we calculated different parameters. We developed a correlation with this riveting velocity. Pecklet number is the riveting velocity, and this mist loading fraction, its cooling efficiency we calculated. One can see like as we increase the mist loading fraction, then this cooling efficiency decreases. Here, this is important, like how, of course, we developed some theoretical models. So based on these theoretical models, we could able to calculate. So till now, I have shown the results of this thing like transient studies. In addition to that, we conducted some theoretical steady conditions also. This is the theoretical model we developed to see verify the experimental results. So here the summary of this model is we used a integral method for the analysis, and based on the result, based on the analysis, we can see like our model is very good here. So that I can show later on. We could able to correlate with the test data, and we could able to propose the correlation here. Yeah, this is the thing I want to say. Like the earlier model that was showing 27% deviation with the test data. But the present model with this condition, we could have this amount of deviation. So this is the better one. So for that, we proposed a theoretical model. So this is only 0.1% deviation with the earlier report results. So this is some kind of result we have shown for the air condition, air studies, air jet impingement. This is maintained at the steady state condition. Till now, I have shown the results with the unsteady condition where the power is switched off. But these results, their power is maintained during experiments, and power is maintained during experiments. So this is a steady state experiments. Air is used as a fluid. So this is the schematic diagram of this setup. This is the test foil, and this is a flow meter. This is the compressor. This is the heating unit, joule heating unit, and this is the camera, thermal camera that is used to measure temperature. This is the computer here. This is flow measuring device. So this is the nozzle configuration. This is the nozzle size here. Again, here we developed something model based on this thing. Hello. Hello.
Yes, sir.
I want to know the time, how much time I need to finish. So.
Yes, sir. 3:30.
Okay. So I need to finish within 5 minutes. Or what?
Yes. Yes, sir.
Okay. So
you might take 5-10 minutes extra, sir, because we have 30 minutes of question and answer session.
30 minutes.
Yes, sir. So next speaker will be started his lecture on 4. So,
okay.
So we can extend up to 4. Sir.
Okay. So I can continue because this is some more lot of slides are there. So just I was so I can extend, right?
Yes, sir. Yes, sir.
Oh. Thank you. So here, as you see here, we will have a data reduction part. As I told, when you take some readings, then that needs to be, you need to develop some model here. Otherwise, we cannot find the performance parameters. So here, this performance parameters, this is the heat transfer coefficient, heat flux here, and this is the way we took a control volume here, and we took this temperature parameters of that control volume, and local parameters are obtained. This is the way we calculated the losses and heat generation part. This is the heating, so Q is equal to VI here. V is the voltage and I is the current, and this Ti is the temperature, ambient temperature, and this surface temperature. So that is the natural convection is calculated here, and we could be able to. So this is the calibration of this IR camera. This IR camera basically operates based on the emissivity values. Before you need to know the temperature, you need to know the emissivity of the surface. So for that reason, we used a black paint on the surface because emissivity will be higher. So then we put some thermocouple on the test surface. There will be black paint and there will be thermocouple. So while doing calibration, we measure temperature recorded by thermal imaging camera and by thermocouple as well. So based on that, we could able to get that under which emissivity the temperature gives very close to the thermocouple readings. So this is the calibration curve we got, and based on the emissivity values, we could calibrate. Okay, for this emissivity, we can get the temperature that is very close to the thermocouple readings. So this is the contour maps for local Nusselt number, how it looks like Nusselt number values here. So here you can see different numbers are given for different colors here, Nusselt number values. So we can see this is the result of some other author here, Gulati et al. And this is our present results. What I mean to say here is that this is based on Z by D, means the distance between nozzle and plate is varied here. So when the distance between nozzle and plate is very less, L by B is equal to 1, the central profile that is very close to the nozzle profile. Here we have used a rectangular cross section. You can see it is just similar, that kind of thing. But as the distance is increased, nozzle to plate distance is increased, it will take a arbitrary shape, circular shape. So different things come into picture. So this behavior is similar. So that is what we try to point out here. This is some kind of validation of this present experimental setup. It is conducted under steady state conditions. So some standard correlations are there, light and wave here, and we try to compare with other experimental results. So this validation has been made, and we try to propose correlations based on our experimental result. Nusselt number, that is a function of Reynolds number, Prandtl number, and this nozzle to plate distance, and this is the axial distance here. Now here, this various different kind of additives are used. What is an additive here? Many times we are not happy with the type of heat transfer we get by using a fluid. Suppose we are using a water, we are using water as a fluid, then we get some kind of heat transfer. But we are not happy with that, or we need more. So what we can do, like we can use some different additives, like we can use nanoparticles, we can use some other surfactant. So these kind of things are added here. So this is the things like different additives. So these are the parameters they are used for finding the heat transfer rate. And here we have used the surfactant solutions here. 3 different surfactants are used. This is ethyl hexanol, 1-octanol, and this is SDS. So based on the surfactant, the beauty of this surfactant, that is they will have more spreading. Okay, you will have more spreading. So more wetting. More wetting means more fluid will be spreading over the surface, and the evaporation rate will be higher. So in that way, it promotes the heat transfer. So here we calculated the surface tension here, how the surface tension reduces by using the concentration, surfactant concentration. Okay, so this is the contact angle measurement here. This contact angle reduces. Okay, if we increases the surfactant concentration, the contact angle decreases, means it is kind of more spreading. The fluid will more spread, and it will come in contact with a larger region, and the thickness will be very small and more evaporation. So that promotes the heat transfer. Here, we have used the nanofluids as well in this case. So different nanofluids are used. Based on that, we will have Al2O3, CO, copper oxide, metals, and nitrates. So what is the beauty of nanofluids? So they are very particles of very small size, nano size, and when they are immersed in a fluid, they create a novel fluid. So their property is much more better than the normal fluid. The heat transfer behavior significantly increases because of this suspension. The mechanisms are described, like we can have Brownian motion here, and we will have liquid layering, and we will have thermophoresis. Here, like these nanoparticles, they are they increase thermal conductivity of the fluid, because these metals, they will have higher thermal conductivity. Because of this, some particle that is mixed with the fluid, we will have more surface wettability. Okay, wettability, this wetting behavior will be increased, contact angle will be reduced again, and based on the application, we will have different, you can adjust the properties. So here I will just go on describing the mechanism here in Brownian motion here. You can see different particles here. These are the metal particles. Their conductivity is significantly higher compared to the liquid. So sometimes they make a chain kind of behavior. They gather. Okay, this particle will be attached here. Initially, they will be moving here and there. Means some fluid motion will be there, and they will move here and there. So they carry significant amount of heat. Okay, so what the stagnant fluid will not be doing this, because of this Brownian motion, they will carry and they will transfer the heat energy in a different or faster way. That is Brownian motion. Other is this is liquid layering. Liquid layering means, I will just give an example here. This is the complete white portion, and this is some color, say some other color, blue, and this is deep blue. There are three different regions. This white region, that is the region we can say that is the nanoparticle. So of course its thermal conductivity will be higher. And this region, this is the liquid, pure liquid, and its thermal conductivity will be very less. Now, what about this intermediate region? Because some liquid will be attached to this nanoparticle, its thermal conductivity will be very high, this intermediate region. So this heat transfer takes place just like a composite slab. Okay, this is a composite slab, and you will have materials of different thermal conductivity. So heat transfer will take place in this radial direction. It is much faster because of this mechanism. And this is the region like thermophoresis, like this is a hot region and cold region. Nanoparticles, they will behave like that in this fashion. There is another thing, clustering, nanoparticle clustering. So what is that clustering? One particle will be attached with the other particle and they will make a chain. Okay, they will be like how I can explain you, like you see, like we put necklace. Okay, some ornaments necklace, you can see small beads, they are connected by a threads. So nanoparticles, they will be connected by just like a ornament, small beads. These are small beads, and if you connect by a thread, then they will look like a ornament. So what happens in that way? The thermal heat energy that is flowing because of this connectivity. So that is a clustering effect. So now we will have for any of the thing, like you can have to characterize what is the what is the behavior, how or why it takes place. So when we purchase this nanoparticle, you need to see that its size and other parameters. So in SEM is used to see the nanoparticle size here, Al2O3 and copper oxide nanoparticles. And of course, many of the values what I am showing here, that is company has given, SEM image we have given. This is the purity and diameter, all other things this company has specified. We believe that in that. So then we need to find out, like suppose you are preparing some kind of fluid here. Okay, you purchase a nanoparticle from some vendor. Then you have water in your laboratory. Then based on some mechanism, you will prepare the nanofluid. So that we prepared based on some chemical treatment if it is needed. So you need to prepare. There are certain procedures are there. After preparing the nanofluid, you need to do certain tests, like what is its shear stress and viscosity and all other parameters. Whether it is higher or lower, and how it varies with increasing temperature. So that can give you its behavior. So that we did by using. So this is the thermal conductivity behavior here. As this nanofluid, as we are increasing the temperature here, how the thermal conductivity increases. And if we are increasing the particle concentration here, how this thermal conductivity increases. So those studies we did here based on the like Al2O3 and copper oxide particles. So overall, we try to see what is the thermal performance of different surfactant additives and nanoparticle nanofluids. So then we could able to find out this type of behavior. You can see how this heat transfer varies based on this surfactant concentration. Here we can say experimental investigation of Al2O3 water nanofluids. You can see here by this is the Nusselt number here and this is the Reynolds number here. Of course, we know as we increase the Reynolds number, the Nusselt number will increase, because Reynolds number that signifies the amount of mass flow rate. As we increase the Reynolds number, then the mass flow rate increases. So for that reason, more heat transfer takes place. You can see this triangle, the triangle shows that Al2O3 water with 0.6 concentration. So here this concentration is higher, and this is the pure water, and this concentration is lower, 0.15. So as the concentration is increasing, then we can have more amount of heat transfer. That this curve shows like that, and this is like that also. Based on this different L by D, here it is shown that for different L by D how it is showing. Here one can see enhancement heat transfer compared to water is 60% and 144% for varying the concentration for 0.15 and 0.60. So 144 is a significant higher number. Of course, by L by D is varying, and this thing changes. So in this calculation also, in this study also, we try to propose a Nusselt number that is a function of Reynolds number, Prandtl number, and L by D ratio. Here one can see that role of L by D is less compared to Reynolds number and Prandtl number. One can see here, this is the thing of this exponent, the value of exponent that is given in this case, 0.453 and 0.16. So one can see what is the significance of different parameters. That one can assess based on that further model or further calculation can be done. So here this is a different type of nanofluid that is prepared by using copper oxide water nanofluid. Here copper oxide is there, and the same analysis is done. Here this enhancement is something 62% and 14% for L by D is equal to 16, 6 for Reynolds number is equal to 500, and here it is L by D is equal to 12, it is 90% and 13.6 for this amount of nanoparticle concentration. So that is the thing we try to show here. Now here also we try to propose a correlation. Nusselt number is a function of Reynolds number, Prandtl number, and L by D ratio. This is the way it looks like, proposed correlation. So this aqueous surfactant solution and Al2 water, so that we tried different ways. Here, as you can see, heat transfer that increases with increasing this Reynolds number, and here also the heat transfer decreases with as we go away from the stagnation point. So this R is this 0 is the stagnation point, and as we go away from the stagnation point, this heat transfer reduces. This is the surface temperature, as this transient curves we have shown earlier also. So this one can see this thing. These are of course transient tests here. Here, this is the thing we calculated the thermal performance parameter that we have shown here. Surface characterization, what I mean to say here is that when we conduct some experiments, we test the object. Suppose you take a test surface we take all its parameters behavior before test, and after test also you need to do that analysis. What is the observation? Suppose for contact angle you measure before test, and after test also you need to measure. So you need to observe all those parameters. Here this is some XDS studies and some XCM studies and EDS studies. One can see this is the results of some other author, and this is the results of the present investigation. One can see here some white particles are deposited here. So that shows that nanoparticles here. This white means aluminum something Al2O3 that is deposited on the surface. And people claim that once you get this deposition, here you get deposition, then it will create a heat transfer surface, because you have a plane surface, but if you generate some kind of roughness or some conductive materials are deposited on the surface, then it will reduce your contact angle, and it will act as a heat generating points. So for that reason, heat transfer increases. That is what one can conclude here. Now in this case, we can see these are the results of contact angle. Here you can see only water. Here only water, one can see how this contact angle increases. This is 85 degrees centigrade, and this is 69 degrees centigrade with 69.2 degree. If this nanofluid is concentration 0.15, and this contact angle reduces to 54 if you further increase the nanofluid concentration, that is 0.6%. So what is the meaning here? As you increase the nanoparticle concentration, some particles they will be depositing on the surface, so they will have some disturbance, like they will generate some kind of thing, and more spreading will take place. So contact angle is basically reducing. If you see this diagram, this is the thermal image of pure water. This is the thermal image of the surfactant solution. 150 ppm is chosen, that is some optimum value here. And this is the thermal image if we are using Al2O3. Now you can see for the same condition, for the same time, the area of the wetted region, this black color, that is the wet region. So you can see for the same time, for the same Reynolds number, you can have more wetted region in case of Al2O3. That is more spreading here, and more region is cooled by using Al2O3, but could not be done by using water. The same thing is observed, of course, in the higher parameter. We calculated the wetted area here in this case. So that is the by using additives, the ratio is 2.7 here. Of course, at lower Reynolds number, but at higher Reynolds number, probably it does not affect, because Reynolds number, it has inertia force divided by viscous force. So inertia force is sufficient to spread the fluid. Okay, probably that may be the reason we don't get much area ratio, that ratio of area wetted and this thing between wetted, different fluid and pure water, that is not significant at higher Reynolds number. But in case of lower Reynolds number, the area of some different fluid with pure water is significant here. Okay, so this is the last study, so that we can discuss here. This is the synthetic jet. Till now we were discussing some continuous jets, but synthetic jet, that is synthetic. The name indicates synthetic material. We can generate synthetic. We use some polymers. Okay, this is the synthetic, means it is made somewhere. So this jet we are preparing. Okay, we are preparing from ourselves. How we can prepare? You can generate, you can fill you breathe, okay, you take some breathing or like that. So there is some mechanism, okay, something is pulsating, your heart that is pulsating, you take a deep breath, so something is squeezing, okay, so something is squeezing and it is taking air to your body, and then you are exhaling some fluid. So that is just like a synthetic jet. You take deep breath, some suction is created, and then you exhale. So synthetic jet is like that. Here, this is the diaphragm here, okay. Only what you need to do is you have to create a pressure here, like you have to vibrate this. So if you make a vibration, then you will create a lower pressure and the air will be sucked inside a chamber. This is a closed chamber. Then the diaphragm, when it is pushed, then it will exhale the fluid like that. So this is the way the synthetic jet operates. So this oscillation or vibration of the diaphragm, that we can do by a speaker. You must have seen that speakers that we use for listening music and other things, or a piezo actuator. So all those things can be used to give a actuation. Basically, this is a closed chamber and this is a small opening. So it will suck atmospheric air and it will eject the same fluid. So this is the way the fluid is coming out, and these are the some of the vortices that is generated from this surface. These are the different methods, so we can generate this synthetic jet. This is the speaker here, and speaker can be used as a actuator. We can actuate. These are the some of the results we got from this study. Nusselt number, average Nusselt number, how it varies, and velocity, how it varies. What I mean to say here is the study is like here the synthetic jets, they don't need any pump, they don't need any pipeline, they don't need any artificial thing. Only you need an actuator. Once you have an actuator, you can actuate certain membrane, and if that membrane is kept in a closed container, you can have a small hole opening. From there, you can operate the jet. That can be used for laptop cooling and other parameters. So these are the some of the results we got from this thing, and this is of course used for a lower temperature. The temperature here we consider it is 85 degrees centigrade. We use the stainless steel. So this type of results we got from this thing. It is a thing will be vibrating here. This actuation will be there, and we propose these correlations and some other analysis, power spectral density also we did. So I will conclude here, like based on this analysis. So of course we got different results. So we studied this thing, how this jet orientation and this jet angle, moving velocity, and other parameters like variation of Reynolds number, Nusselt number, and nanofluids, additives. So all those how like influence the heat transfer, and how heat transfer varies with respect to axial distance. So yeah, I would like to thank our friends. So just I am presenting, so I don't have much contribution. Of course, the credit goes to the students. They have only done the experiments and they have used the results. They have verified the results. So I am presenting on behalf of them. So my thanks goes to our students and other funding agencies. So thank you.
Thank you, sir. Sir, we have sir, questions in our chat box.
Okay. So,
sir, Mr. Om Prakash Chand has asked how the jet impingement cooling helps in wireless sensor networks.
Again, just repeat again question. I could not understand this thing.
Sir, how the jet impingement cooling helps in wireless sensor network.
Okay, wireless sensor network. Like That exactly we need to know, like wireless. I don't know, like which type of cooling they use, which type of cooling. I exactly could not visualize that. Like, let me clear. Like there is a physical system. Okay. So in physical system, if something is generating heat energy, and if we have some access of fluid to the physical system, then we can maintain the temperature of that physical system. So in wireless network or wireless system, if there is some physical system, suppose something is there and that is generating some amount of heat energy, then we can use suitable fluids to cool that surface. Some physical system should be there to receive the fluid. That is my explanation.
Okay. So any other questions can be asked by unmuting yourself. Participants can ask your doubts or questions by unmute yourself. Okay, if no questions will be there, sir, thank you for your valuable time, sir. Actually, with your busy schedule, you have given us time, and we are very much thankful for that. And it was really a nice presentation, and also lots of things or topics has been covered. I mean, lots of wide aspects has been covered through these presentations, and we are glad to know that it's very uh, knowledgeable things we have come across within this 1.5 hour. Thank you once again, sir.
So, okay, so thank you, Professor Bhoi, so for giving this opportunity to share our experience. So, thank you again, the organizers Professor Kanchan and others, Professor Trilochan. So, yeah, so thank you very much. So, possible you can share the video so that I can improve in the next presentation.
Yes, sir. We'll try to send that. Okay, thank you,
Yeah,
sir.
it will be always a learning thing. Okay, so yeah, then now I can conclude or
Yes,
thank
sir.
you.
Yes,
Yeah, I am disconnecting.
okay, thank you, sir.
Okay.
So our next speaker will be Professor Subrat Kumar Panda, sir, from NIT Raulkela, and let me introduce him with his small biography. Professor Panda has been working as an associate professor in the Department of Mechanical Engineering at NIT Raulkela. His expertise focused in the field of computational and experimental solid mechanics and smart composite structure. He has been in the field of teaching and research from last 10 years, and he has already handled a few research projects from different sponsoring agencies like DST, DRDO, AICTE as the principal investigator, amounting 98 lakhs. Additionally, he is active in the field of biomechanics and rehabilitation too. His field of research includes multi-scale multi-physics modeling of nanocomposite structure and structural acoustic material modeling. Based on his expertise, more than 8 PhD students have been graduated under the different fields of research as the solo principal supervisor. Additionally, he has supervised 32 BTech, 21 MTech, and 2 MTech research. He has already published nearly 147 peer-reviewed journal articles, both SCI and SCIE, and 40 national or international conference proceedings. He also filed 2 Indian patents as the outcome of the BTech dissertation as one of the mark of innovative research output. His research include area of renewable energy harvesting from waste heat vibration. His current research include biomimic composite material modeling to resist high impact as well as improve self-healing capacity of the parent structure as one of the co-PI under Imprint 2 project. He has received international award from Cosmic Outstanding Award 2017 in the field of applied research, NIT RAA Research Excellence Award in the Mechanical Engineering Sciences category, and Best Technical Paper 2017 and 2018, Institute of Engineer Odisha. Today he will deliver a talk on importance of simulation and modeling in the mechanical engineering, an overview. Basically, he will discuss here what is simulation, what is modeling, how the simulation and modeling are important in the field of mechanical engineering. Now I welcome Professor Panda sir. Good afternoon, sir.
Good afternoon. Good afternoon, sir. Am I audible? No.
Yes, sir. Yes, sir.
Okay. So thank you for giving me an opportunity to discuss. So I believe I should start. It is already, and it is very tough for the people, those who are listening, for a person who is Is it visible, sir?
Yes, sir. Yes.
It is visible, no?
Yes, sir.
So good afternoon. I don't want to take much time, as we have, I think, a very short period of time has been given, and it's a very, I just want to touch, as I said, it's overview. So overview is very difficult task for everyone like you and me, those who are listening to this, and is very difficult for the person who is source has no such issue to deliver the something, but the seeing those who are going to hear all this. And before starting that, I must be thankful to all the organizers who have given me a chance to discuss. Now, before going to this importance and simulation of modeling in mechanical engineering, somebody may think about why should I know about simulation and modeling as a mechanical engineer, or in particular the persons those who are associated the core engineering like mechanical, electrical, or civil. These are mostly practical oriented, or we know it is our basic idea. A basic idea says that it should be corresponding to some field work or something like that. Always it is, yes, it is true, it is very much true. But I think you also agree, everyone will agree on this point. So is it possible to, let's say, if I'm interested to test some material, I'm changing every day-to-day life, every now and then the material has been changing, its the different material has been associated or improved day by day to utilize in different field of engineering. Now let's say if 10 years back the material which we are using, our household things also, it has been, you can see all these materials has been exchanged, largely the materials has been exchanged by or replaced by new materials or new kind of materials. The fabric we are wearing 10 years back, I think you might have seen different kind of advertisement. And the fabric, if I'll say, I'm just talking about the households, if I'll go to the household. Similarly, if I'll talk about engineering or engineering material, It has also a very long standing from the very, if you go to the history or history of the material to the current state or the state of art, it has been changed a lot. If so, so every time before changing the material, it is not possible to just to start at the very first day, I'll change one material and start doing the production. Because by that way, most of us, we have studied, most of us, we have already completed our basic understanding, like mechanics of solids or design of machine element, where we understand how we design, or a design engineer, how it designs everything based on the basic some basic information. And when I'm saying the basic information, again, is a design engineer, when I say the design engineer, not a single person, or not, it doesn't mean to a single person, rather it is meant to a whole a group of people. Why so? If I'll say, if I'll just give an example, let's say I am talking about a aircraft, if I'll talk about a satellite, all this, or if I'll talk about just a automobile, a two-wheeler or a four-wheeler, if I'll talk about, then it is not only a single automobile engineering, it is not associated with only the single automobile engineering. It has been associated with the material engineers, it has been associated with the chemical engineers, it is being associated with the electronics engineer, because you have seen the automobile engineering has been shifted or transported or transformed from whole that means I should say, like earlier those are not automatic kind, or you can say the mechanical kind, has been transformed to totally automatic gear changing or power steering, like that. It has been more or less the most of the components has been automated today. It has been automated in the majority, 30-40%, 50% has been changed to automation. So by that way, or during this process, we know there are not a single material which is going to utilize, or there are not single constant is going to be utilized, and there are not single or multiple of constant and multiple of positions or multiple of conditions has to be implied on the system to achieve our objective. So when I'm talking about a system, the engineering system says it's an aggregation of all the engineerings. So before understanding the modeling and simulation, or before understanding to talk about the simulation and modeling, it is better to understand little bit on the system. What is system? If I'll go, what is system? If I'll first of all, I must know what is a system to whom I want to design, or a component of the system, or the part of the system has to be designed or has to be cover up. The term system has been, it is derived from the Greek word which says it's an organized relationship among functioning units or component. What does it mean? Let's say I have shown here one component or whole system of aircraft. You can see it has been associated with electronic system, internal fuel tank, main gear, wing tank, flaps, spoiler, jet engines, all this. Every single unit of that, it's a different system or a different unit has been aggregated to get a whole system or to get a whole aircraft. The whole aircraft here is some of the points has been only pointed out, like electronic system gone, nose gear, electronic system, internal fuel tank, likewise all. If you'll just join all these, so they are one kind of system. Again, inside that you can have a lot more can be there as a smaller system or subsystem of that. So to understand that or to design that, it is not possible for me. Like similar way, I have shown another example, like a satellite system or a small satellite which has been, you can see one spacecraft module is associated with that, solar array, sunshine door, like sunset door, like that. A number of subsystems are associated with a system to perform a complete work done, or to perform a complete desire what you design engineer wants to complete. It can be completed by a n number of subsystem to reciprocate the whole system. So system exists because it is designated to or designed to achieve one or more objective, as just now I said. So we come into daily contact with all this system, like transportation system, telephone system, account system, production system. So all our system, which is again have some subsystem, has to aggregately they have to do some kind to achieve the final goal. There are more than 100 definitions can be done, but in commonly, if I'll say in commonly, if I'll just want to say in one line, or just to want to express the system of it, or any system, if I want to say, so to have a common thread that suggests that a system in an orderly grouping interdependent components linked together according to a plan to achieve a specific objective. That means spacecraft or satellite has some particular objective, aircraft has some particular objective. It is performing a particular objective by taking the help of individual components. Then if I'm talking about the system, I think most of you or some of you have now started viewing or physically able to connect why a simulation and modeling is important. Before going to that, I want to show some more what is a model. So I am talking about simulation and modeling and their importance in mechanical engineering. First of all, to simulate and model it, I need I need to do with a system. And what is system? First of all, if I know, then what is a model? I think most of us we can agree on this point. Let's say if I am just now I gave a example like a satellite system. Is it possible that whatever the material, because the satellite when I'm talking about, it is going to space, it is leaving the atmosphere. When it is leaving the atmosphere, it is there is no you will not have any earth or you do not have any atmospheric level or environmental effect on that, but it has in a different kind of environment. Instead of having a high temperature, humidity, but it has to pass through that, and it has to work for a longer period of time. So it is not possible for us to every time to do the same or to manufacture or fabricate where there is a cost is associated. If it is a low cost or high cost, because engineers are meant to be known for the their design has to be economical in nature. In order to have economy in that, or any design has to be economy or economical, it has to be planned very fastly, and this is one part of the planning. You must have heard about production planning, and production planning is associated with the first kind. It's what is a model, or you need to reproduce or regenerate a model. What is the model? It is nothing but a simplified representation of real object or system of objects at some particular point of time and space for purpose of visualizing and its appearance or analyzing its behavior. What does it mean? Let's say most of you know, I'll come to that. A simple example, I'll start with a simple example, and it will clarify how the model can be, or how the simulation can help us to achieve the same. In this respect, first of all, if I'm saying the model, then what are the level of models, and what should be the our as a design engineer or as a engineer, what he expect or she expect from the model? What should be the level of models it has to be to perform? Then only it is let's say in this way, whether the model is good or bad or good or not, it depends on the kind of extent which it provides the understanding. If I'm representing a electronic system or a TV, let's say if I'm considering a TV, so whether a model of the TV, if I'm doing a model of TV, so it must have a good quality of picture. It should take less current. It should be it should having whatever in our mind. Let's say when we are going for a phone, to buy a phone, we normally see as of now today, we are seeing the first of all, if I'll talk about the safety part, the battery has to be very safer. The battery power mode or power should be very high, or it can keep the battery level should be high, or it should consume less battery on that. And the camera, as per the person or the observer or the consumer or the customer, based on that it may vary. So as a design engineer, without knowing the customer or consumer's need, you may not able to do the same. So the same mobile, or you see all these mobile working on the same principle, but having different kind of cost based on their kind of material, kind of applicability, kind of picture quality, kind of internal storage, kind of RAM, all these kind of things, or all this associated subsystem has to be planned very early before it comes to the market. So in this respect, if I'll say, all the models, whatever it is, it may be a mobile, it may be a TV, it may be a automobile, it may be a aerospace or aircraft, or it may be a spacecraft, whatever we are talking about, all the models are simplified, simplification of reality, whatever you have thought about, or the consumer or the customer who is going to take it out, and those who are the end users, according to them, we have to understand, or the design engineer has to understand, has a good idea on that, to exact copy the reality what is happening in there, or what is happening in the real time situation. It has to be taken care of. There is always a trade-off as what level of details included in the model. That means what the tiny to tiny part and bigger to bigger part has to be incorporated in the model. It has to has in the mind of design engineers, or the group of people, those who are going to produce, or to to give the final shape. They have to have all this kind of idea, then only it can be able to concurrent to the consumer's requirement. Otherwise, many people may not able to, like if you have before coming to the smartphone, there were only the Nokia who was 30-40% of the market. It was taken by the Nokia itself. Then first, if you think about the first mobile phone, Philips or Motorola, then Nokia came into the market, then these two are wiped out. Then when Samsung, when it comes to, or just changes to smartphone, at that time again it has been changed. The whole motto has been changed. Some Chinese company as well as Samsung, they have leading the market. Today if you'll see, a number of mobile companies are there, but a few mobiles are been, they are like in our Indian language, if I'll say, sasta sundar tikau. It has to be low cost, efficient, and it should be durable, or it has a good endurance, or people should accept the things or the particular product in a better way. So the design engineers, it is true for this mobile, it is true for a automobile, or it's true for a two-wheeler, it's true for a bicycle, it is true for anything or everything. What else we are utilizing that, and behind that what is happening, and how you are producing that. Now these are the two major points. That means too little details. If I'm during the model, to reduce the model cost, or to reduce the modeling time, if I'll take too little detail, the risk of missing relevant interactions, there is a risk always that I could not able to achieve. That means if I'm not checking the battery life, if I'm not checking the waterproof, if I'm not checking many things, a small to small tiny part if I'm not taking, okay, it is going, everybody is working, it is okay, and the batteries are already satisfying the market. So based on that, if you will not take, then there is a risk of missing relevant. Or the other way it may possible that too much detail, overly complicated to understand the model, or the design engineer itself, he will be in a, like as I have shown here, four different part or four different components. One is spacecraft, it is another is one is spacecraft, one tank, or is a naval ship, or a torpedo. I think Gaji, you might have seen that film. And this is spacecraft which returns back again. It's first time done by the Russia and American, both they have did. And after that, this spacecraft, one accident was there, Kalpana Chawla accident, if you have heard about. So after that, the new materials like graded materials or functionally graded materials has been come into the picture. Afterwards, it has been very rapid improvement in that. The functionally graded materials has been come into the picture, although there are some functionally graded materials earlier there, the mostly in biomedical engineering. Then it is shifted towards the structural or high performance engineering. Likewise, the concept has been changed slowly, it has been changed. So this is the all about model we are talking about, is a small line about the model. Then what are the types of model we have, or what are the kind of model we normally do? Either it may be a physical model, as I have shown four different figures of all this physics, or or a mathematical model. Either I can do a prototype, or to like if I'm doing some innovation, we normally do first some kind of either I can do the same thing by making it the whole structure, or I can make a mathematical model of that. Let's say, what is a mathematical model? If I'll say, like if I'm having a plate, or let's say, I can give you one example, like if I'm having a beam, and that beam I am going to bend. So what is the elastic curve is taking the shape, I can write mathematically, or I can do the same thing in a physical way as well. So there can be a physical model or a mathematical model. Then under this physical model, the scale model, that means whole scale I may not able to possible for me to do, so I'll scale it down or scale it more. If it is a nano scale, then I'll scale, I have to scale up. And if it is a very larger kind, like 5 meter long, 2 meter or 2.5 meter diameter, so I could not able to make that physical model immediately, so I can make a portable of that. That means it is prototype plants, or the whole scale model, or the full scale or large scale model, or mathematical model. Under this mathematical model, again some classification we can do, like analytical model, numerical model, or simulation model. Here in this talk, I'll prefer to fix my discussion into this numerical and simulation model, where we are working. Although there is some part of the analytical we have did, but I'm not going to talk about much on the analytical type of model. Now, examples of models in engineering, I can show you some kind of whatever the discussion I told you just now. In automobile engineering, all the automobile engineers or all the automobile engineering companies are normally prefer to see some computational fluid dynamics, or it should be the design has to be computationally stable, aeroelasticity, like that. All this studies has been done. It is also in a railway, in like now high speed trains are coming into the picture. Those are the computational fluid dynamics or CFD analysis has to be there. Like all these vehicles or from the automobile to aircraft structure, noise and vibration or harshness has to be taken care, otherwise it will create some sound unresisting sound to everybody, or every single passenger. Those who have traveled by air, they might have heard, might have felt the similar kind of situation. Or if you'll sit in a low cost car or a high cost car, you can see the interior design in such a way that it will have. Or if I just give an example, a common man example, if I'll say, if you are sitting in a sleeper, or in a train travel, if you are sitting in a sleeper, or you are sitting in a general, or you are sitting in a third AC or second AC, or you are sitting in a first class AC, so you can see the difference of the sound, how it is calm and quiet inside the AC compound. But similar kind of calm and quietness you may not get in either in sleeper, because of this noise, vibration, and harshness has been taken care there. Similarly, the stress analysis, also the structural part, those who are working in a structural part, they need to focus. Those who are working in a fluid, they are working, or they are just looking into the computational fluid dynamics. And those who are working in the multi-physical model, the combination between a solid and fluid, there is a sound with the structure. There is always mixed up with that. They are working, those who are working in multi-physics, they look into this. Or some part is they, here also the multi-physics come into the picture. Like stress analysis, only the structural part is taken care. Like crash testing, most of you have heard about 2 years back or 2.5 years back, all of the, or most of the Indian car designers has failed this crash testing, except one or two, like Ford has been owned or something like that. And if you have remember the last one means when it was launched by the Tata Nano was launched, it was the low cost car. When it was launched, at the time of launching, it was discussed that how Tata makes this as a smaller cost with a very low cost. Although it was not taken off the market due to the price, although the price was very less, and due to the salary has been increased by various people, and the consumers have higher capacity to spend, so people doesn't prefer much, or do not prefer much on that. But it was taken, other low cost has been import or incurred at the research and development or R&D. They have taken only front to front crash test, and they made the structure in such a way that it's a closed form or elliptical form, which is by nature or by physics they are strong enough to take care of their own structural strength or integrity, to maintain the integrity. Now, a similar kind, the thermal also, these are the kind of examples of model, why we need the model and why it is necessary to model it first and to go for design. Similarly, what is simulation? If I know the model, once I get the model, then what is the use of a simulation? Simulation, just it changes from mathematical or computational model to description of the system or the physical system behaviors based on the set of input parameter. What is the input parameter? What is the speed of sound? What is the speed of vehicle? What is the kind of road and where it is running, and what kind of environment it is going to work? Is it in a offshore kind of environment, or is a normal, or is a humid kind of condition? Likewise, all this environmental effect as well as the basic conditions. And like if I give a comparison in this way, just 2-3 days back, sorry, 1 week or 1.5 week back, there was something trending in Twitter, like Tata has got some truck to deliver. The war truck, which has been designed by Tata, our all this military truck, they have been the military truck or military, or one is civil automobiles, and some are defense automobile. Defense automobile has designed in such a way that they can take a tough situation like any kind of environment, as well as a road, as well as all this. They are always in a high mode of operation. So when they are under high altitude, high mode of operation, or a high impact loading, so if all this it is there, or you might have heard the term anti-ballistic tanks, all this kind of structure or structural component has to be higher end models to take care of all this kind. So based on the input parameters, a set of input parameter, so the simulation is just kind of imitation of the operation of real life process, or real life what is happening, how you want to design. Based on that, the simulation has to be designed or simulation has to be prepared. So behavior of system as it evolves over time is studied by the developing simulation model. The same thing whatever I have discussed, it has been listed it out here. This model takes the form of a set of assumptions concerning the operation of the system. The assumptions are expressed like mathematical relationship or logical relationship or symbolic relationship between the entities within the system. Like when I'm saying the beam is bending, if it is a cantilever beam, it is under a load at the free end, it is going to deform, and the deformation is like linearly varying from this point, some 0 to maximum. So it is linearly varying. So I normally write dy by dx, or we normally write it's a dy by dx. So mathematics gives us that relation. Or it's a simply supported beam, it is under bending moment or bending condition, it rotates, or it's take a new curvilinear structure, or it is the representation of that beam will be d square by dx square. So either it's a mathematical relationship and logical relationship. Similarly, the symbolic relationship represents or necessary to express a simulation model or to represent a simulation model. So what are the simulation steps? The steps involved in developing simulation model, designing a simulation experiment. That means if I want to model a car, so I have to take what are the components of that. And as I have shown a model of spacecraft or a satellite, as well as a aircraft structure, where you can take all different model. Let's say I could not able to solve the whole model at a time, so I can take the whole structure as a beam having different wings are also a different different beams. So I can analyze it differently, the whole structure, different subsystems in different way, and the whole structure in a different way. So what are the simulation model? Designing the simulation experiment and performing the simulation analysis are identify the problem, what kind of problem it is, and what are the how to formulate the problem or what are how to formulate the problem. When I'm saying, as I said, the whole structure I'll take as a single one, or a components of the structure I have to associate with that. collect the process real system data. That means, as I said, if it is a cantilever beam, so I have to consider a cantilever beam and it is loaded at a tip, or there are number of loads are acting, or a combination of loads are there, environmental change is there or not. All it has to be poured into the model, then to achieve the exact kind of behavior or exact kind of structural model we can able to structure or fluid anything. Then to replicate that, to formulate and develop the model and validate the model. How will validate? Normally we get some responses. Computer simulation says like this: if I'll put some garbage, I'll get some garbage. If I'll put some real time data or original data, I may get some real time or original output to that. So document for future use. Then we make a report, select appropriate experimental design, establish the experimental conditions for runs, perform the simulation runs, then interpret the present results. Whatever the final output we get, we can interpret according to our requirement or design. So the final one is the recommend further the course of action, what the kind of change is required, or if it is required, then where it should be. Like if it's the same thing, if I'll write in a flowchart form, it is looking like this way. The first stage it says formulation and determination of investigated objective, then determination objective and the time plan. Then there is a stage 1 and stage 2. Stage 2 basically give the, if model validation is complete, then it will give the yes, then it will go to the simulation experiment design and will finally get this output. If it is, I am not satisfied anywhere, so every time you can see there is a, if the model validation is complete, no, then we'll go to again subsystem or system determination. If it is the model verification, either I can change before the system determination or after the system deformation, because there might be some kind of change. That means the number of wings I have taken, or the kind of wing I have taken, the shape of wing I have taken, that is not correct. So I have to go system determination before the system deformation. But what are the kind of load, like below the wing there is a fuel tank, I have not taken into that into the consideration, then I can after the system deformation also extra load can be added to the system after the system determination as well. So based on my necessity, my requirement or designer's aspect, it can change. Similarly, every single point can be, there is a scope, you can change the model by which your model capability may the model capability is going to improve. It's all this process by which there is no such experiments are involved. Only a person or a group of person working in that, they can able to give their input and they can have a robust model or robust simulating kind of model has been developed to achieve the necessary requirement of the final design. So this is all about modeling and simulation individually. When I'm saying modeling and simulation, it's a discipline of understanding the evaluating the interaction of the parts of a real life and theoretical system, real or theoretical system, and designing its representation or designing its representation, how we are designing it, it's represented as the model, and executing the model or by utilizing the loading and boundary conditions and their dimension, by putting their geometry, material property, and we are finding out its structural responses or sound responses. Those are nothing but the simulation. So altogether, after knowing this individual understanding about the system, model and simulation, then how we can connect all this. So why the modeling and simulation is important? I don't think it is more required. Already we have discussed many times during the discussion of during the definition, because the description of the system, still I am just pointing out few points over here, because the description of the system behavior or experiment might not be feasible due to, if it is not possible to do the same, that means I could not able to make every time a spacecraft and send the spacecraft to space and then get back some response. So, or I could not able to make or change the material of the engine and I'll manufacture that if there is some faulty manufacturing, or if I'm changing the crank material, if I'm changing the piston material, it is not possible to do the same before doing some kind of or every kind of analysis for the sake of safety and reliability of the system. So if some inaccessible input and outputs are there which is not known to us, and we know the stress which is a unknown part, which is again an internal part of the body, and it is it is basically internally develops within the body. So it is not possible to maintain or to possible to understand by seeing the things directly. So these are the some kind of inappropriate things which push us or push the design engineers before starting any analysis or before starting any design. We must have to have an idea, or if you don't have an idea, then you go for a modeling and the corresponding simulation, then you go for the final fabrication and the final polished product or finished product. And cost of experiments, again, if it is too high, every time you may not use the all kind or every kind of material. They are not so much of easy to get and to fabricate also. So then these are the some kind of input parameters are basically give us a force, or gives us or force us to do the simulation and modeling. So experimental behavior might be obscured or disturbances are there. Then similarly, why simulation and modeling are used, I just say, just now I talked about, let's say, to test a system without having create a system for real. Building a real life system can be expensive and it take a long time. To take a whole bridge and to test it, that how much of load it is going to bear, it is not possible. Or if I want to, instead of creating a bridge, if I want to break a bridge also, so I need to know how many people are going to affected that breaking of the any structure. So it is not easy to directly, if will break, I go and I'll just, or a team will go and will break the municipality. You might have heard some of the time in Mumbai, in most of the rainy season, some building has got in a very bad condition. It demolish either its own, or beforehand the municipality take care of that and they demolish this kind of buildings. So they, before that, they do some kind of testing. I think most of you heard about the Nirav Modi's building has been demolished. Beforehand, they did some kind of by using dynamite, how it is going to affect everything has to be tested or checked. After that, it has been done. So it is not directly, it is not hit and trial method. So hit and trial you can only do in simulation and modeling. When you are going for a real life problem, there will be no such excuses after the operation will start. Now to predict what might happen, so that's why also the in the future, what is, if it is not so accurate, or if it is unable to give the accurate responses, the final responses, then it will may create some kind of panic afterwards. So to avoid that also, that means test, predict and train. This all three things basically giving the intuitive behavior of simulation and modeling, or it's necessary for any kind and every kind of analysis or every kind of production, beforehand production. These are the basic knowledge has the designer. Based on that, a system will be built up. So by saying this much, and one more, it is left is just now. All this, if I'll just add test, predict, and train. So by using this train three, I can investigate what is happening in the next step. So before going to that, or before going to just as I said, a bending flexor formula, all of us we know, and we know why the simple formula as I talked about. I'll start with a simple example. Like all of us we know bending flexor formula. What is that? Or it is called Euler-Bernoulli beam equation, and it is m by I is equal to sigma by y is equal to E by R. This is a very powerful equation for our those who completed only BTech or masters. We majority in mechanical engineering, those who have studied the design part, they know this is a very powerful formula, and this formula gives a lot of idea about a design of any object. When I'm saying a design of any object or material or component, this formula have enormous of use. And this why, if I'll say this equation also used in two half. What are the bending stress? When we study utilizing this. This is also represents the strength or load bearing capacity. Similarly, when I'm studying slope and deflection, I'm utilizing other half of the equation, which is talked about stiffness or deformation bearing capability. That if I'll talk about this, let's say the where m sigma are the externally it is creating due to either m or sigma. It is although it is internal part, it comes due to the externally applied load. Similarly, the m also, the bending moment which is creating within the body, it is also due to the externally applied load. These two are external. However, this IRY is associated with the geometry of the kind of material or the structure I am interested to find it out. And E is the material property. You just see this equation, all these two equations are based on, these are the input parameter and these are the external parameter. It has to be applied on the body and it is already within the body. So this all together will give you some idea about the, let's say if I'm giving an example. And one more is E into I, we use m by ei, normally we write it's E into I, which is called flexural rigidity. Again, you see flexural and rigidity, those are contradictory term with each other. Either the structure can be rigid or the structure can be flexible. So all this has to be taken care if I'm going for, like, let's say if I'm showing a beam or bridge, this bridge, all these bridges, all most of the structure wherever if I'll take, so we start with every kind and each and every design, we can start with the simple beam bending formula or beam flexural equation can be designed by using this. Now I can make it simple, or let's say if I'm taking either it's a cantilever beam or a simply supported beam or a beam with variable cross section. Likewise, I can change in between the beam, one more support is there. There are some continuous, earlier the beams of continuous beams has been used. Now it has been converted from continuous to section wise beam. So if I'll write like here, sigma is equal to m by I into I, and this is either it is written as J is the polar moment of inertia, and or it is Z or ZP. ZP is the polar moment of inertia, or only Z is the section modulus. So nowadays the design has been converted to every section, not a whole throughout the beam, rather we can take section. So most of the structure or high performing structures are based on the sectional modulus or section design. So these are the basic formula which is utilized. You may think, is it so that is a so small formula is being used? Yes, this is the formula everywhere is being used, but with a different form. How the different form will come to that. Just now you need not worry about. When I'm talking about the modeling, the whole car can be a beam. The whole car can be a beam having some cutout, and the whole car can be a rectangular plate. And again, the beam, if I'm increasing one of the dimension, it is one of the beam. If I'll define, beam is the structural component which has one of the dimension is large as compared to other two. That means the cross sectional area is small and the length is very high. We called it as beam. Now if I'll increase the length of the beam, and already the length is there, if I'll increase the width of the beam, so the beam converted to the plate. If I'll decrease the width of the beam from the plate to, or decrease the width of the structural component from plate to, it will convert a beam. So likewise, we can increase or decrease, we can change the model as well. So model has that capability. From the basic idea, you can increase up to high or from high to low, anywhere or anytime, every moment you can change the things, and according to your desire you can play with that. So the basic equation is this. The next is, when this is all together in whole every analysis, these are the basics we utilize everywhere, but we do not know or we do not find, is it so, is it going to utilize in that way. So one more case, most of us we utilize, or most of us have this idea, Hooke's law. Hooke's law talks about the stress is directly proportional to the strain when within the elastic limit or proportional limit. Again, it is true for unidirectional loading. It is not true for the multidirectional loading. Here we say this equation is only valid when the if the material or the beam, I am considering the material or a beam, I am applying the load in one direction and the deformation is only occurring in one direction. But it is true that if I am applying a load in one direction, the deformation may occur in all the direction, because not a single material in this world, which a real world it is existing, it is one dimension in or 2-dimensional in nature, all are 3-dimensional in nature. Let's say if I'm having a parallelepiped structure and I'm just trying to stretch the material in this direction, in this direction, if I want to stretch, so the structural component not only extend in this direction about its length, it is also going to decrease in its cross sectional area. So the decrement in the cross sectional area also creates this all confusion. So how to handle? Then next step is generalized Hooke's law came into the picture. That means if I'm taking a beam, I'm just putting a load in both sides, it is going to a new shape, and that can be represented as generalized Hooke's law. And generalized Hooke's law, instead of one equation, we have 6 different equations. 3 are for normal and 3 are for shear, and all these 6 equations represent. That means you just see, just now during the discussion of beam bending equation, we saw m by I is equal to sigma by y. So I, which is a geometry part, R, which is a geometry part, Y is a geometry part, but the term E we are considering, that E, whenever it is associated with geometry part, also deformation, epsilon x, epsilon y, epsilon z, gamma xy, gamma xz, gamma yz, whatever it is, any change is occurring in the geometry, the deformation occurring in the geometry, but it is associated with reciprocally associated with the property of the material. So geometry and property, the basic internal or input. Let's say if it is under a temperature condition, we know any conventional material, either it's a steel or it's aluminum or any other conventional material, copper, bronze, if I name it, every material have some kind of intensity or intuitiveness towards the temperature. If there is a temperature, it may it will be soft and it can deform easily. So there is a relation between Young's modulus and the temperature every time. And you can, if you have did some kind of wiring at your home by doing the electrical wires, normally to either we can use a knife to cut the copper wire outside of this cover, plastic cover, or we just to heat it and we just try to pull it. So after heating, it will easily that can be removed. So it will be that plastic or thermoplastic can be used, easily come out of that, or the rubbery type of material which is outside, it is easily come out of that. So all this day-to-day life we utilize, but we do not know that exactly it happening like that. If anybody, if you have felt like that, I don't know, 2 different same kind of or same size pot, if one pot or what same size of glasses have got into inside, they have been fixed, or it is mechanical fit like that, if they have been inserted with one one over the another, then if we could not able to bring it out, so we put it into hot water. You just put into hot water, easily it will come out. So one of them will be the one which is exposed to the hot water, it is going to swell, little bit swelling, so the diameter will increase, the inner one will come out. Or you put some hot water to that which is inside, that will also try to swell, so it will also easily it will come out. So all these engineering applications, these are the common application we do, but these are the engineering kind of application we are writing in terms of laws and axiom. Are you getting my point? Similarly, you may think of most of us now also, I am using a laptop, and I am using a laptop with all different kind of accessories, like a charger is there, I am having a mouse, and I am having a headphone. Everywhere number of wires are associated with that, and that wires basically we put into in a bend form. We keep it into in a bend form, not in straight form. And you may not aware about that, or if somebody knows, it's good, well and good, that before that you know what is the cost of charger. The original company chargers has little bit higher cost as compared to the general chargers, like common chargers, if we'll take it, because the common chargers don't utilize any research fund to that. That means the number of times it is going to bend, or number of times it is going to open, so it depends upon that endurance limit it can take, the number of cycle of bending. every time it has to bend, it has to open, it has to bend, and it has to open. If I'll ask you, if I'll give you a broomstick, and I ask you to break, normally it is comes to our mind, it is easy to break by bending. Nobody will try to stretch the broomstick to break it. Or if I'll give a scale also, steel scale like this one, if you can visualize, I don't know, if you want to give you to break it, so you will try to bend it. It comes to our mind directly. So every time we try, because it is easy to break rather than easy to break by bending rather than stretching it. And again, if I am getting a bending, some kind of bending very easily, if I'll change this shape, that means instead of this width, if I'll change the shape, you could not able to you just instead of the plate sorry, the beam or the scale I am talking about, you just see the width or the higher width part is easily bent, and the lower or the thickness part, if you want to bend that, you could not able to bend that. So all this kind of because of its geometry, as changes geometry, so geometry as well as property has a long standing effect on their design. So these are the basic equations which has been utilized and everywhere, and how you will talk about that. So now, based on this, so what are the kind of properties? I'll just go through the overview. First of all, I talked about system. Then what is simulation? The simulation and what is modeling? What are their importance? Where they have been used? And what is the basic equation from where it has been evolved? I have started. I have just talked about that. Now, as once I know the properties, then what are the kind of material? And many material I named it here, like either material classification can be of this one, you know, you most of you know that, most of you have heard about the material which we are using in strength of material. Either it is all the materials are isotropic and homogeneous, and all those isotropic and homogeneous, how they differ? Now in both the cases the properties are same. In one case, in isotropic material, they change the properties are going to change or varies as the space changes. From that means, if I'll take a beam, I'll take 4 points on that beam in different points, p1, p2, p3, p4. The properties may be equal in p1, properties may equal in p2, properties may equal to p3, properties may equal to p4, and the properties p1 may not be equal to p2, may not be equal to p3, may not be equal to p4. But when this p1, p2, p3, p4 all are equal, they will be called as homogeneous. That means if the properties throughout the volume are not changing, it is called homogeneous material. If it is changing somewhere, then they are called isotropic material. One is space variant and one is space invariant, and another is most common type of material, anisotropic, which is originally or in a reality it is always there. All the materials are anisotropic then isotropic, and one is orthotropic material if the properties are varying in perpendicular direction. That means in x direction, whatever the properties of the material are same in all point, and y-axis properties of the material are same in all the point in the y-axis. Similarly, all the points in z-axis, but j, x, y, z, the properties of x and properties of y and properties of z are not equal. That means they are directionally or perpendicular, mutually perpendicular direction, they differs. Then it is called orthotropic material. Or they can also be classified in all different kind. You heard about those terms: elastoplastic, elastic, plastic material, or ductile, brittle, tough or stiff, hard or soft material, likewise. So these are the kind of material property we handle a day-to-day life. Now, what are the types of material we normally use? The kind of material, conventional material, if I'll say, these are the sum of kind of metals or ceramic or polymers. These are the kind of materials are being utilized in the overall in mechanical or any kind of engineering, if I'll say, everywhere. Either it is iron or steel or alloys or superalloys or intermetallic components or compounds, ceramic, structural ceramic, or refractories. You, all of you have heard about these terms, or it has been utilized this way or that way. We saw these materials, but we do not know they have been classified in this way. Or electrical ceramics, chemically bonded ceramic, likewise. Similarly, polymers, plastic, liquid crystals, adhesives, all this kind of material. So when either using a single material or using a double material or using a combination of material, then the material properties differs. If the material properties differ, then the that is also called, the Hooke's law is also called the constitutive relation. They constitute that relation, the stress strain relation helps the material to constitute. What if I'll change, instead of sigma into epsilon, if I'll multiply with the temperature, then the value will change. If I'll multiply it with the hygral condition, then it will differ. If it is associated with some smart materials or some other kind of material, it will again differ. So based on that, the smart material, if the material which if I'll explain the smart material in this way, the material which do not perform, the stress is directly proportional to strain within the elastic limit, or they are not linear in nature. When the stress is directly not proportional to strain linearly within the elastic zone, that materials or those materials are called as the smart materials or functional materials. So every material has some functionality. If the material in a lower scale or lower range, if they can show some kind of functionality, they are more usable or more adaptable in the system of the material design or material modeling. Now in this direction, there are some more materials can be seen: electronic material, composites, and smart materials. So these are the kind of materials which are used in the design of the material design.
Hello, Subrat sir.
नेटवर्क प्रोब्लेम है मैडम
हाँ मुझे कॉल करो छे
आज्ञा
सुब्रत सर हाँ
हाँ कौन प्रॉब्लम है लगी
हाँ
मैडम
सर टिके डिस्कंटिन्यू हो गला
माने एबे फेर माने से जेतवाट पर्यंत कहितली से तळ पर्यंत देखा जाउतला ना देखा जाउ
स्मार्ट मटेरियल कंपोजिट जोटा लास्ट स्लाइड ता देखा जाउतला
अच्छा अच्छा ठीक ओके It is visible, no, madam?
हाँ सर इट इज
हेलो
हाँ सर इट 8 स्टार्ट करें
एठी आगु को जाई नथले एठी थला So these are the kind of materials. So sorry for the discontinuity. Now these are the kind of materials I was talking about, and directly I'll come to some of the material which got a good name, or people are very much interested to see those materials or utilize those materials. In that respect, if I'll say, first of all, first material I'm talking about, I'm trying to talk about the CNT, and some of the material, the materials which I am talking here, most or a few of the material we have utilized utilized or we have fabricated, and I'll talk very little on that, not much on that, and how you can model it, and what are the points we consider during the model has to be considered, or normally we take. Carbon nanotube is a catchy name. People are very much interested to know about carbon nanotubes, work on carbon nanotubes, and nano wherever you will write nano, wherever you will write bio, wherever you will write mimic. So people are nowadays, it has been in a trend. These are the trending kind of materials. So that's why I thought it will be easy, or it is necessary to talk about a little bit on that. So although the nanotube has been discovered early in 1991, and this is derived from graphene sheet, because whenever you, due to the allotropy behavior of the carbon, when you will open a graphene sheet, you keep a graphene sheet, you always try to make it allotrop, or to make it a bond, and that bond allows the material to be it's just looking like it's a graphene sheet, and these graphene sheets are, these carbon nanotubes are coming from this graphene sheet, and they have very good electrical properties, mechanical property, material properties. Single nanotube, if I'll talk about single nanotube, a single nanofiber have very good high property, or high mechanical, or excellent mechanical properties, electronic property, and they are 100 times greater than sometimes the multi-wall carbon nanotube and single wall carbon nanotube. How this nanotube formed, I'll come to the next. When I'll come to the next, I'll discuss about that little bit. And the tiny portion of the nanomaterials are used, the baseball bats, car, and in every way or everywhere you can find some nanotube material as of today, due to their specific strength is high, and they have been utilized because of their one major characteristic, like aspect ratio. They have very good aspect ratio, or they have very good stability in aspect ratio. If I'm going on decreasing the one of aspect ratio, talks about the ratio between the adjacent sides. If I'm adjacent sides, or the length is very huge, or L by D ratio, if I remember, most of you know L by D ratio, slenderness ratio, or L by K. Those are talks about the stability of the structure. If the structure or structural component are unstable, then they could not, or they are unable to take the load or they may fail in between. So they have very good, the nanotubes are very good in aspect ratio. They can take, if you go on increasing their length, it is not going to affect the structural stability. And a tiny part of that, again, it has been, as per our study, as per our understanding, or as per our modeling and simulation, we saw that single carbon nanotube or only carbon nanotube will make some structure, it may not work properly, or it could not able to give the kind of output you want. But it is very easy, if you'll mix with someone, it will give very good coherence between the structure or structural component, and they have very good property, structural property, electrical property. All these properties are very good. Now, carbon nanotube reinforced composite, as I said, we worked on that. This composite is looking like a layer wise composite. Here also we made some layer wise composite. Instead of carbon, either you can have CNT or CFF carbon fibers, or you can have CNTF also, carbon nanotube fibers, individual carbon nanotube fibers. And carbon nanotubes, if I'll go to the carbon nanotubes, I just want to show the things. I don't want to discuss much on that. Introduction to graphene, all this, just to have any look on the kind of material we are talking about. So these carbon nanotubes, as I said, this graphene layer always trying to take this kind of tube structure, and they have the very good stability, and that can be a multi-wall tube, or it can be a single wall tube, and they are existing in three major kind of either the graphene sheet. If you leave the graphene sheet, they can take all this, either one of them, the shape of one of them, either it is in 3D graphite form, or it in a nanotube form, or it is this is also called fluorine, and in a spherical form. Due to this allotropic form has a honeycomb crystalline structure, where each carbon atom makes a covalent bond with the other three. And we know, most of you have heard about or remember little bit on sp2 and sp3 characteristic of carbon. and sp3 or sp2, due to this hybridation of sp2 to sp3, or sp3 is the hardest form. I think most of you know the diamond is the sp3 form, is the hardest form, and sp2, from sp2 to sp3 easily it converts. And the carbon is the only material which shows the hardest and the softest. One is graphite is the softest, and the same allotrope of the same material. So that's why the carbon or carbon allotropes are much more utilization or much more interest to the structural people or structural engineers or the design engineers to have to obtain all this kind of property. Otherwise many other material they can have better properties, but it can change or it can switch from one to other very easily. So that's why this creates all kind of behavior. I'll show you some kind of carbon nanotube we have also made. If you are able to see, this is one kind of carbon nanotube with only carbon nanotube with very small amount of fiber is there. 0.2 or 0.4% carbon is associated with that, with the polymer composites. So all these properties, they are not very strong enough like other fibers, but if I'll join with other material, then it could be better, or it can give a better idea about the material. So now the mechanical properties of the graphene, I just want to show some. As I said earlier also, it has a capability, like a figure shows 1,000 watts, like a Chinese power says. So you can say a single carbon nanotube has a strong enough to take the electron from one atom to other atom and convert it into the electron. So that is why this carbon nanotube is
मैडम सार को टिके कॉल कर दियंतु सारंकर ये कटि जाइछि
हाँ जानी छी करूछि सर
Hello, Kanchan madam.
हाँ सर हाँ सर हेलो हेलो
हाँ मैडम आज सरला ना
हाँ सर सुब्रत सर फेर नेट कटि गला आपनकर
हाँ मु थिली सुब्रत सर थिले मु सुनुति कटि गला मझे मु लगे मु देखुचे बसछि जे मु अटेंड होलछि पूरा वीडियो रे नाही ऑडियो रे रो
हाँ 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 सर
हेलो
हाँ सर जॉइन करूछन सर मिनटे रहन तो
नहीं मु आपको मालूम करता बोलछि आप सॉरी जरे सॉरी কথা
हाँ सर
I'm sorry. Once again, I'm sorry. I have been trying my best, but so is it visible, ma'am?
Yes, sir, it's visible.
Okay. So I'll a little bit. I'll go fast. I don't know. Again, I took all this arrangement. After that, also I felt all these issues. So directly, as I have already discussed, so you can see uh, this is the main reason why people are very much interested. This one cartoon has been given, as I said, what is the strength of the carbon nanotube, and the basic necessity. One is the it has good stability, and the second is the very good. Its Young's modulus nearly about 1 terapascal, and I talked about the Erringen factor, or it's called non-local elasticity. Also, one kind of area people work on when people work on numerical modeling of the nanostructural component. They are also working in that part. We also worked on that very small part, though it is a very small MTech research, and all MTech people one of the MTech student has did. So all this kind of analysis also can be done in that. So now the nanotube, when I'm saying the nanotubes can be achieved or can be available either a single nanotube or a multiple nanotube, and the nanotubes are classified based on their angles. Angles of what the nano or molecules are associated according to the molecule angle. Also, they have been called as zigzag, chiral, or armchair, and this depends upon the chiral vector, this A1 and A2. Based on that, their capacity or strength may improve, or you can say tailor-made properties can be achieved. So that's why they one thing, they have a good capability of mechanical and electrical characteristic. They have good capability of conductivity, electrical conductivity, thermal conductivity. They have good capability of the changing their shape and to get a new shape with a new design constant. So this adaptability allows the CNT to have a better combination. So these are some kind of mathematical expression, as we are talking about the mathematical modeling. So mathematical expression represent the nanotube or nanomolecules, how they have been classified. So based on that, it is normally we write or represent in this form. Now these are the some kind of nanotube, as I said just now, talked about armchair, zigzag, or chiral, and they have been you can see from the very front or front of the front view of this different kind of nanotube. You can have a visualization or visual effect how the nanotubes has been changed or been looks like if I'll change the or if the angle is going to change, the hamada index is going to change. So general CNT properties they have, due to that people got much more, or designers got much more interest towards that. These are the very common kind of properties which has the carbon nanotube. And carbon nanotube, every time you can see this is the graphite, these are the nanotubes, and these are the diamond, and the very much a class of verification, a various class of the material or combination of the material can be seen here. So one more material is functionally graded material. As I said, the functionally graded material, I can show you some functionally graded material. So you means I can show you in figures only. But we did something with the grading pattern we have achieved by using a natural fiber. I'll show you the later on. So functionally graded materials are the advanced form of the layered composite. As during the discussion of the spaceship, I talked about that, or that is called re-entry. During the re-entry, the functional graded materials are very much important. And launch vehicles, the launch vehicles are very much important in terms of material and their design constant. So they are in generally a combination of the material. There are two different material can be combined with each other, and one is metal and one is ceramic. And the kind of the ceramic which is rich in one is rich in ceramic and one part is metal. So one is good in taking the temperature, one is good in taking the load. Or although the elasticity is higher here, but they are strong material. Ceramics are the strong material, but strong doesn't mean that they are tough. But designers interested to have, if the strength is little bit low, but if it is a high or it's a tougher material, it is more usable in design, mechanical design or any design. Why FGM? The large number of engineering components and the tools require material performance by varying. I can say you one example, like human body. Human body is made up of only the graded materials. If I talk about the teeth, If you have seen the Sensodyne advertisement says the core of the teeth is getting exposed when it is getting exposed to any kind of change of heat. That means either you are eating ice cream or you are taking the hot coffee or hot tea. So it sensitizes the core portion of the teeth. That means core of the teeth is very soft in nature, and but the outer part of the teeth is very hard in nature. Similarly, if you have talked about the bones are also as a mixing of soft tool and soft bone and hard bone, cortical bone. So all these are the graded type of structure. If I talk about human head, a skull, the front part of the skull is very hard, the back side of the skull is very soft. So normally you can see, you might have seen the people, those who are in karate, kung fu, taekwondo, they use the front part of the to break their to break bricks and all, the front part, not the back side most of the time, because it is hardest part of that, or it can take an impact very easily. But the back side, if you use some very impact, very strong impact load, so you may go to heaven, you will not be here. So all this kind. So body of gear also. Similarly, the human body, as I said, the body of gear or knife, all this has to a combination of the properties, and they need to complete a particular objective. So we need a different kind of material and their property, and to perform a particular kind of desired output. So all this kind, I just want to cover up the kind of materials, why people have failed to go for functional graded material. Here the weight, if I'll say, just see the weight of the steel, aluminum and FGM, it can be very less, whereas the specific stiffness, if we'll talk about, the FGMs are high, and the specific strength is FGM is high, and the thermal expansion is low. If the thermal expansion is low, then that means it is very good to utilize in the high temperature zone. It can be utilized with a high specific and high specific stiffness. Am I audible to everyone? No, I think it is audible and visible both. Is it?
Yes, sir.
Okay. So now the material properties, again the properties can be the different kinds of material model have been developed. As just now we talked about the common type of materials, or what are the kind of classification of the material. Then we talked about, we picked two different material. One is advanced kind of material, nanotube material. One is functional graded material. I want to talk about little bit how we model the those materials, or all these material property. Either a isotropic material we know how to do. We already know about Hooke's law, generalized Hooke's law. We can able to do the same material property in a modified form, can be utilized for the different advanced kind of material. And what are they? The rule of mixture, Halpin-Tsai, Huisia model, Moritanaka scheme. You may ask me what all these are the some kind of modified method or experimentally validated. Some methods has been you most of us know about empirical relations. Some of them are also based on the empirical relationship with experience and experiments they did, or they the terms has come between the from the experimental analysis and the corresponding numerical value, and they compared and they established these are the this all can be utilized, or one can be utilized. Moreover, the rule of mixture can rules in the most of the cases when we analyze within the strength of material approach or mechanics of material approach. And most of the structure we are talking about in a day-to-day life, they are working below the ultimate load. They are working in a safe load zone, so and within the elastic limit. So the rule of mixture can be utilized in our purpose, where when we are talking about that in a specific area. When I'm talking about the space science, if I'm talking about the aircraft, there might be some kind of change or some kind of variation of the material, and the model may be required. Otherwise, a common kind of material model or common kind of constitutive relation, common kind of geometry can satisfy or can give you the better result or the your expected result. These are the some kind of numerical methods are already available, or numerical models or empirical relations are already available to model these kind of materials. What is rule of mixture? I no need to explain more. Here, two different figures are explaining. One, when the load is applied perpendicular to the fiber, when the load is applied parallel to the fiber or along the load, along the fiber, then from there the rule of mixture has been evolved. And where this V, sigma, E, L, all are the PL, delta is equal to PL by AE. What the concept we know, if a single fiber or a single rod is hanging due to its own weight, and we find out the delta or deformation by utilizing the similar concept, here also it has been explained how the rule of mixture has been found. Similarly, for the CNT reinforced composite, it has been extended, the same thing has been extended here. One is CNT, one is volume fraction of CNT and volume fraction of the matrix material, which kind of matrix material you are using. Now, Halpin TSI model, just modification of E1, E2, NL or N delta T. This eta T is the efficiency, material efficiency component. I'm not going very deep into that. These are only the, for the, as I am saying, it is all are for the sake of information. And we did all kind of analysis. We performed all kind of analysis, and we find Halpin TSI, sorry, we find the rule of mixture and the common kind of nanomaterial or nanoparticle, other the good resemblance with the other, like Halpin TSI, Huisia model, Moritanaka scheme. We find Moritanaka scheme and rule of mixture is giving very close result to each other. And in some cases we may find, we have found some cases it is different. In the most of cases we got its good result. So Moritanaka approach, again Moritanaka approach is one kind of rule of mixture, as we are saying. Similarly, the Moritanaka approach also talks about, here you see some LK, K, L, M, N, P. These are Hill elastic constant. They have found out from the experimental data. And they have been utilized to modify the Young's modulus of the nanoparticle. And they can be also very good method, or Moritanaka approach is a very good approach for the nanoparticle kind of structure or structural component. In, like Hooke's law, Moritanaka approach is one of the approach by which we can find out the Young's modulus of a material which is not known to us or not easy to experiment. So you can numerically find out those properties very well, because properties I know. Properties, if I know the properties of the material, then I can, if I have the input parameter of the geometry property, both will mix, will give the stiffness of the stiffness characteristic depends upon both the property and the, because property creates the resistance of the material, and the resistance is nothing but the load bearing resistance or load or deformation bearing resistance. Either if it can able to resist the load, automatically it resists the deformation. If it is resist the deformation, it has a higher capability to take the load. If it has a higher capability to take the load, the design engineers will, that means it has a higher toughness up to breaking. So people or the designer will always choose that kind of material only for their analysis. Similarly, the Young's modulus and the bulk modulus, as well as the stiffness parameter, sorry, rigidity modulus, can be found out by utilizing these values. And some more has been shown for the combination of material property, when we need some combination of the when I'm saying this alpha, when we are talking about the alpha, basically talks about the constant thermal expansion or linear thermal expansion, and beta high-gral thermal, like high-gral expansion. Likewise, all these components can be obtained by using the Halpin TSI model or Moritanaka scheme, or Moritanaka scheme utilizes the Hill's constant to find out all these other properties or parameters. Again, randomly distributed material, here we do not know how the distribution has been occurred within this nanotube material, so we normally take as a random distribution. So random distribution of the material resemblance a isotropic kind of behavior, because within the isotropic material there is no such sequence of the distribution of the granules or the molecules within that. So there is also we consider as a random distribution. So it is well a resemblance to the isotropic material. Now some of the material properties which we have calculated just now I talked about. So rule of mixed Tanaka method, we found a very good behavior. All this kind of model we have implemented for we also published a part of that. So it is not matter we have not calculated the material properties only. We have calculated the vibration where we have utilized. Before going to the Young's modulus for randomly oriented material, we found out for longitudinal direction and Young's modulus for transverse direction and properties for the Young's modulus for the randomly oriented MWCIT. How much in this we have utilized in our if I am going on increasing the volume fraction of the MWCNT, you can see the elasticity or the Young's modulus is going on increasing. Again, it is not true. Some cases has been done, it is not true. Every time it is not that if you go on increasing, you will get an increment of the parameter. In reality, it is not happening. In reality, something other can also, you can see behavior may be observed, but in a typical manner, you will always find always increment. If I'm going on increasing the 5 or 10, it is going to increase. Similarly, the effective parameters of the FGM material can also be obtained by using rule of mixture as well as other behavior, like if I'm considering the material, what kind of material. You may ask, just now as I give an example of teeth or human skull. Similarly, I can say a bamboo stick. Most of you know about bamboo stick. And bamboo sticks are bamboos, bamboo. Earlier, people are utilized the bamboo sticks for the fishing rod, for the purpose of fishing rod. Now it has been slowly gone, and people utilizing composite bars. Bamboos are very much intelligent graded material. If you go from node to node or within the in between the nodes also, you can have, or within the cross section, they have different properties, different direction. So that's why it creates, or it gives a different kind of it has a different aroma for their application. So bamboos are also well known, one kind of ductile material, and it is utilized in the household as well as other purposes. Nowadays, you might have seen the design, only the design people. Design means I'm not talking about the mechanical design. The designers or industrial design, like we have a department like IIT Guwahati has a department, and some other like NIT, National Institute of Design. Those people utilize bamboo in different form. And nowadays, from the bamboo, you can see various household materials being made from the bamboos, because of its their own this kind of properties. Otherwise, it could not be able to possible to utilize. Some of the graded material I have shown here, like as I said, it's a teeth implant or hip joint implant. They are artificial hip joints, and they must be the biomedical application. If I'm talking about, the material must be porous in nature. There is a combination of metal and ceramic at a time, and they must be porous because they are within the biomechanical system or biomechanical, or I must say biological system. So there must be some porosity. They must breathe, or there some oxygen has to pass, and air has to pass, or water has to absorb. So there must be some porosity. So porosity is one kind of and you might, most of you have seen the advertisement of Horlicks. Women's Horlicks. It talks about women's Horlicks. When age 35 crosses, so the bone porosity increases or the bone density decreases. And bone density, when bone density decreases, the densities are directly proportional to the Young's modulus. And there is a function we utilize. So for that, the porosity can be also utilized or adopted in a numerical model in the form like this. It may evenly, the porosity may distribute within the structure evenly or unevenly. It can also again modified. The formulation or the material formulation, you can, here a 2D formulation has been shown. That means it is not only varying in thickness but also varies in X. That means the grading is varying, the graded structure I'm talking about. And the porosity, when I'm including the porosity, this lambda factor is called the porosity. And similar way, all this kind of porosity, if I'll plot that this way, if I'll drop one of them, that means X by A or Z plus H by Z plus H by N, or sorry, what it has written, z by h plus half plus z by h. If I'll drop this x by a, so only the material is going to vary or graded within the thickness. If I'll drop this one, I can only the variation along the length. If I'll just add y by b again, so it is multi-directional grading will come. If I'll drop this lambda, that means without lambda, it is without porosity, the material property is like this. That means if it is polynomial variation, if I'm considering. So all these kind of variations can be achieved, or you can numerically you can do. But somebody may ask, can we do the same thing experimentally? Yes, we can do. But up to here, or whatever the facilities we have, we can only generate up to cylindrical. Not in our lab, in other lab of NIT, we can do up to cylindrical kind of material. But experimentally, we could not able to. We have not did yet. Again, they can be the sigmoid FGM, one is polynomial FGM, or then it is sigmoid FGM again, based on the kind of relation PFGM, and the multidirectional material property variation use PFGM is extended for SFGM. SFGM, when I'm saying SFGM is just talking about the variation of the sigmoid kind, or that means the in earlier case it was varying with the polynomial relation, then further it varies with the sigmoid variation, and it is a one kind is exponential kind as well. So all these variations are there, you can change, or as I said, once you know the equations, you can play with the equation with your own according to your requirement. But it is not possible to get similar kind of the things in a real life situation. It may differ from there. And one of the method by which we can this one I'll just run 20-30 slides are there, I just want to talk about. If you want to get the material properties for any nano kind of material, one of the software is very much powerful software is called Digimat. We just now we procured a Digimat. I just want to show how you can do this simulation kind of modeling of this Digimat, or can be utilized the simulation kind of modeling by Digimat of multi-world CNT and SDP. SDP is high density polyethylene kind of thermoplastic composites. If I do so, there are two different way to find out this. One is homogenization, field homogenization, mean field homogenization. One is finite element homogenization. In Digimat, you can do mean field either MF or either FE. Both of them or one of them you can utilize to have a comparison on that. In this regard, this MF has it is utilized Mauritania and SWJD models to estimate the average stresses and strain field. Here we can find out directly the properties E1, E2, G12, nu. All these properties can be obtained by just considering a model. You start a model, you do your model new to start a model, then you analysis type, what kind of analysis and what type of scheme, what type of homogenization, what kind of order of the homogenization you want. Then you can take you just validate that. Once you put this material model, you can easily step by step you can find out individual material properties or stress strain graph. Or then you when you will make it composite also, you can multi-wall carbon nanotube indifferently, SDP indifferently. Then you mix this material, two different phase of material you mix, and then you can add different microstructural phase. You can generate the same material, and after making this material you can create this material, and you can find out the stress strain diagram and the corresponding properties and their corresponding stress strain diagram as well as their property. What else you want, you can find it out from here directly. One is MF method, other one is Digimat FE. And these are the but it has two major drawbacks. When Digimat FE I'm talking about is a meshing difficulty you may find, or realistic models, or it's called representative volume element. Representative volume element also a very good kind of method, but it takes very much high. This is the volume. After that you cannot take less volume of that. This is the lowest amount of the volume within which the how many number of molecules are there. The properties will be based on that. and you can use it any FE solver. Digimat can be after Digimat FE. You can either use their own solver if you have that. Nastran pattern, it is the, since it is MSC software, it utilizes the Nastran and pattern to find out their properties. Or you can directly go to this solver. You can take it to the ANSYS or Abacus. Also, you can solve there. There, how the steps normally it has been shown. Once I have shown by using analytical methods or analytical or numerically, it has been evolved. But you can find out by writing a code of this all property, or direct software you can use to find out the property. And we normally use the first one. Now you started using the second one. That means the Digimat. Just now we have started the similar process or steps. Will again you can follow for the microstructure, all this individual material, addition of different phases. Then after the phases, you can find out the different material and their corresponding, it's a single wall or multi wall kind. There are 340 or more than 340 materials in the library of Digimat. You can utilize of them, or if you need more material, you can ask them, they can add, or you can put it your own by asking them or to discuss with them. Is it possible? So here one FE model has been shown, either one module has been inserted. So similarly, a number of molecules, how many number of molecules you want in a particular RV, you can insert it and you can see how they have been distributed. I am saying, earlier I said it is randomly distributed. You can see it is randomly, or it is aligned in an aligned way. You can make it aligned, or you can make it random. Accordingly, you can find it a mesh. After that, you can then generate the mesh, and from the mesh you can able to get the stress strain diagram as well as the corresponding properties. This is one kind of material modeling I am talking about. Some of the research at NIT Rourkela, as I said, I just want to show some kind of what we did with the CNT, what we did, not much glimpse of that and their corresponding results. But